So what this workshop today is about, bringing together industry and academia, and to try to think and brainstorm about problems that are going to be uh, present in the future. As one might imagine, competitiveness in both manufacturing and e-commerce requires systemic robustness to supply chain uh, fluctuations, robustness to labor fluctuations and market fluctuations. And building this system which operates robots in places of humans or in places with humans requires integration of these systems with a multifunctional technology stack. What does this mean? This could mean perception, planning, control, and whatnot. And all of this requires careful thought. Some of these questions have not even appeared in academia yet. So what we're going to do today is going to spend about half of today's programming listening from our partners in industry, and about the remaining half in listening from latest advances from our academic partners. And the idea is to inform each other of what problems are important and necessary. And aside from that, we have also ensured that there is enough room for discussion. So we have two panels uh, where these will be moderated, each with five panelists, and audience will also get a chance to interact with these panelists as well in a live session. In the morning session, we are going to have a keynote by Matt Mason. He's a veteran professor at CMU and has been a core founder of Berkshire Grey, and he's going to talk to us about problems in warehouse automation. We'll also have another keynote by Professor Pieter Abbeel, who is at UC Berkeley and is also at Covariant. And he's going to talk to us about how to build general purpose AI robotics. In addition, we are also going to talk to Alex Harvey and Sandra Skaff from Ocado and NVIDIA, respectively, and they'll talk to us about what sort of problems they believe or they envision will present themselves in the next 3 years or so. In addition to our industrial partners, we are also going to hear from academics who are part of University of Toronto Robotics Institute about different topics varying from perception, control, and safety in both manufacturing and retail. Not only that, as I mentioned, one of the most exciting parts of the agenda today will be opportunities and challenges in industrial applications for robotics. And this will be a panel that I'll be moderating with a number of our speakers. At the same time, we'll also have an afternoon session where the panel will talk about potential solutions to these problems. How can industry partner with academia? What sort of translational technology and benchmarks can be built? With that, I would like to first of all thank our supporters and sponsors. We have Ocado Technology as our headline sponsor. We have NVIDIA as our partner spotlight, and Epson is our promotional partner. Without their help and support, this event would be much hard to execute. So with that, I would like to move on without taking much further time to our first speaker today, Igor Gilitschenski. Can we bring Igor up to speed? Wonderful. Uh, so for everyone, just in terms of logistics.
Can you guys hear me, maybe, first of all?
Yes, indeed. So before we move on with Igor, for everyone, we will have questions at the end of every short talk. However, you would not be able to ask them during the talk. Aiden, would you be able to bring up the question bar? Yes. At the end of the talk, a question box will appear, and you would be able to type in your questions and vote up or down these questions. And the moderator will be able to ask this of the speaker. At the end of this morning session, at the end of keynotes, you will also be able to ask questions of all the speakers at the panel. Wonderful. So I'm super excited to present Igor Gilitschenski. Igor is an assistant professor of computer science at the University of Toronto And he's also a consulting research scientist at Toyota Research Institute. Before he joined Toyota, he was at MIT, where he was a postdoc in computer science and AI research lab, where he worked with Sertaj Karaman and Daniela Rus. And prior to that, he worked at Autonomous Systems Labs at ETH Zurich with Roland Siegwart on robotic perception, particularly localization and mapping. He obtained his PhD in computer science working on nonlinear estimation at Intelligent Sensor Actuator Systems Lab at Karlsruhe Institute of Technology, supervised by Professor Hanbach and Professor Hulier. Uh, with that, I'm super excited to get Igor's perspective on interestingly titled talk, Home Alone, the challenges of indoor navigation. Over to you, Igor.
Okay, let me share my slides. Okay, it seems to work. So, Animesh, thanks so much for the kind introduction. As Animesh mentioned, my talk will be on the challenges of indoor navigation. In the last years, I've mostly worked on autonomous driving, and a lot of the push that we have seen in navigation has come from autonomous driving use cases. But there are certain challenges in navigation and in localization that we have, particularly when we go indoors. And today I will focus on localization and speak about some of these challenges. So what we try to do in localization is we try to mimic something that comes completely natural to humans. Humans are really good at knowing where they are. They are so good at it that this task sounds to us almost boring. We learn it so early that this is not a conscious process anymore. And we use for navigation two main organs. One organ is, of course, the eye, which does the most of the work. And then the second organ is one of the inner ear organs. It's the balance organ, which gives us inertial cues. And our brain automatically combines these two organs and allows us to get a sense of motion, to recognize where we are, and to navigate around in the world. And what we try to do in robotics is we try to mimic the functionality of these organs by combining cameras with inertial sensors that measure things like accelerations, gravity, and things like that. And you have these sensors are nothing special. Most of you have them probably in your pocket because your smartphone usually has both of these sensors. You could use stereo cameras for the purpose of this talk. To make matters a little bit simpler, I will talk about the simpler case where we just have one single camera. So let's see how this, to us, super simple process, how this process looks like to our robot. From the viewpoint of a robot, navigation and localization looks something like this. By the way, this is not only from the viewpoint of a robot, this is also from the viewpoint of your VR headset, or if you use your smartphone for augmented reality use cases. All these things use roughly the same technology. So you have some sort of detection of interesting points in the environment, and these points that are detected in the environment are then somehow stored, and their location is calculated, and they're used to create a map. We can briefly go through this through some detail because this is important to understand what type of problems we're encountering and how we are trying to solve them. So the very first thing we start is an image that a robot gets. This image typically has some particularly interesting points, and these interesting points are just points that are very distinctive. It's some corners in the image. So usually there are much more than visualized here. And we track these corners over time, and by tracking these corners, we can estimate the motion of them. And this happens by having camera images of the same objects, of the same environmental structures from different viewpoints, not just tracking these points, but then also knowing how they moved along in the image. And additionally, we can combine this with some inertial data to provide a sense of scale or to robustify our estimation process. So this is usually where what our inner ear organ is doing comes in the estimation process. And this allows us already to estimate motion. But we not only want to estimate motion, we also want to localize where we are. So if we turn a robot on in a space for which we have a map, we want to know have we been in that space before? Where are we in that space? And to this end, we need to create maps of the environment. And we have seen this process in the beginning, this map creation process. It again starts off by detecting some interesting points in the environment. And there are literally, in this image, it would be literally hundreds of points because there is so much texture visible, and these points are just corners. Then we try to describe these points. So there are so-called key point descriptors, and you can just think of it as a bunch of numbers that tells us how a particular area looks like. It's not the full image, but it is a very compressed description of the image. And then we create these descriptions for all the points in the image. We also create information about its 3D location, and all this information we store in a map. And now what we want to do with a robot is, once we turn it on, once we have such a map, is we want to do the opposite task. So we start with an image that a robot just seen, and we have already the map that we previously created. And now again, we detect the key points in the image by the robot. We again compute the descriptors, what these key points look like. And what our localization system is doing is it basically takes the key points that we have in our map and their 3D locations, and it compares them with the observations that we have in the current data stream of the robot. And this information allows us to obtain position and orientation of the robot in the environment for which we have a map. And something very similar, there are big varieties of this process, and a lot of research has gone into how to design particularly good key point descriptors. What are good ways of detect interesting points? How to do the search and retrieval process in the localization system. So a lot of this research went into these individual components. So let's take a look at what happens if we want to do what Animesh earlier described, if we want to let our robots out of the cage and to let them walk around freely in, let's say, a retail environment. Retail environments are surprisingly challenging, actually. A retail environment might look something like this. And if we have some sort of key point detections here, this environment would have a huge amount of key points. But we have a bunch of problems here. One problem is that a lot of the key points that we detect are likely not very persistent. So if we look at the product areas where we actually have the products, the key points detected there are some sort of key points belonging to actual products that might be bought by customers, they might be restocked, they might be rearranged, and so on. So ideally, we would want to provide our robot with a notion that these things are completely irrelevant to its localization task. Of course, there is a simple but expensive solution to this. We could hand tweak the robot to a specific environment, design pre-installed infrastructure so that it doesn't need cameras and that the map creation process becomes completely different. But in order to make a commercially viable product, we want to avoid as much of this environment tweaking as possible. So ideally, we would want to provide the robot with some sort of intelligence that allows it to reason about these things being problematic and not relevant. At the same time, we want the robot to know that maybe ceiling structures are particularly useful for localization. But there might also be some changes. For example, the lights might be turned off or might change color and so on. So we want our robot to be able to handle this type of challenges for localization in the wild. And today, I want to briefly mention two ideas that we use for evaluating this type of pipelines. First of all, I will talk a little bit about robust map creation, and second, about evaluation and maintenance of such maps. For robust map creation, our goal is how to find useful landmarks in dynamic environments under changing appearance conditions. So again, as mentioned, in the supermarket, you have seen it. We have the situation that there are a lot of things that may change. It is very similar in this lab environment where we did our work. There are also a lot of things that may change over short periods of time. There are useful landmarks, such as building structures that are likely to be persistent, and there are bad landmarks that belong to temporary objects, such as bottles, cables, pens lying around in the lab. And the way we do this is by training an AI system to tell us which of these landmarks are useful and which of them are particularly bad. And in this type of our research, we literally took a tablet that is equipped with the standard robotic sensors and walked around the lab and recorded multiple maps walking over a longer period of time through the same environment. And these recordings we could co-align in our system and create one big map consisting of multiple traversals. And based on these traversals, we could then match these landmarks and see how often did we observe certain things throughout our recordings. And as mentioned, building structures used to be observed often. Those are good landmarks. And people or clutter was observed only a few times throughout the recording at the same location. So we could classify those as bad landmarks. And then we could evaluate this in our lab data set. So the overall type of pipeline that is used here trains a classifier to predict whether these features are stable. In our case, we used a very simple CNN back then. These days, the systems have evolved, so there are much fancier classifiers. We had multiple traversals of the same environment, and then we could compute a stability score that allows us to decide what is a good and what is a bad landmark. And this score was used to train our classifier and to allow the classifier to decide, yes, I want to use a certain landmark for localization, and I don't want to use a certain landmark for localization. Now, once we have built a map, we want to know how good is this map. For driving, this is not as much of a problem, because in driving we traditionally drive on the same road and on the same few lanes. So if we know that it localizes to the same on these lanes in one and the other driving direction, we are kind of done. We only have to account for these changes in the environment, but we don't have that many changes in the viewpoints of the vehicle. The vehicle usually drive always on same lanes looking in the same directions. This is not the case for indoor localization. Indoor, a robot, particularly in large open spaces, can traverse these spaces relatively freely. But our map was recorded only through a limited amount of traversals. So what we would want to have is a system that allows us to tell, depending on which viewpoint and which location the robot is on, will the robot be able to successfully localize? And the way we did this in our work is to predict localization quality by simulating the retrieval process. We literally looked at our map and were able to query the map. What would happen if we position the robot in a particular location? Will the robot be able to localize? And we did simulated localization by scoring all potentially observed landmarks by the likelihood of their observation. And this ultimately allowed us to create a nice visualization. This again was from our lab environment that tells us not only at which locations a robot will be able to localize, but also which viewpoints are particularly likely for the localization to be successful. And if you design a robotic system that localizes, that is able to give you this information, you're now capable of adjusting and improving your maps. So in order to do this, you need a technology that allows for creating maps based on multiple sessions. And this type of work was, in order to enable to even do this research, this type of work was very engineering heavy, and we built such a system that does multi-session mapping. So where we have a robot or the use of a tablet or a VR headset traverse an environment multiple times, and then based on these multiple individual maps, we created a system that allows for building one unified map. And this system is called the MapLab framework, inspired by the name of a tool we used back then a lot. And what it does is it provides a bunch of tools for recording, processing, and manipulating multi-session maps. So it has a visual inertial odometry and localization front end, and it has a set of tools and algorithms to once maps are recorded, to actually manipulate these maps and to work on them. And this technology ultimately resulted in one startup that you can check out if you're interested in buying a localization system off the shelf, or you can check out the code base if you want to play around with it yourself. So I'm looking forward to your questions. This was a brief overlook of some of the things that we're interested in doing in order to enable indoor localization. And I hope I conveyed that this is a very interesting problem space to work on. And thanks for your attention.
Thank you so much, Igor. Are there any questions for Igor? Either? In the interest of time, what we'll do is we will move on to our next presenter, Angela Schoellig. And please reserve your questions for Igor during the panel session. Thank you again, Igor. Then can we move Angela to the stage? Wonderful. We now have Professor Angela Schoellig. Angela is an associate professor at University of Toronto Institute of Aerospace Studies, where she heads the Dynamic Systems Lab. She's also a faculty member at Pieter Institute for AI. She holds a Canada Research Chair in Machine Learning for Robotics and Control, and a Canada CFAR Chair in AI. Among the many awards she has won, she's the recipient of Alexander von Humboldt Professorship, a Sloan Research Award, and a MIT Tech Review 35 and 35 awards, among many other accolades she has won. And I'm very excited to hear from Angela, to hear about agile, smooth, and efficient mobile manipulation for task sequences, object balancing, and ball catching. Over to you, Angela.
Great, welcome everybody. It's such an honor to be part of this event. A big thank you to everyone who has been helping to organize the event and to all our industry sponsors. I'm presenting an overview of the research my group has been conducting that is relevant to manufacturing and retail. In particular, one focus will be on agile, smooth, and efficient mobile manipulation for task sequences, object balancing, and ball catching. My group focuses on achieving fast and accurate motions of robots and mobile manipulators in particular in cluttered indoor environments. And you see a mobile manipulator here in the right photo. Our work also includes indoor localization. This will nicely complement Igor's previous talk. And you see an example here in the image on the left. And we also have work on perception control and learning. We have experience not only with mobile manipulation, but also other relevant robot platforms for retail and manufacturing, and those include drones as well, as you see in the image on the left. So I'm very excited about applications that combine indoor mobility with sensing and/or manipulation. And these include warehouse management in e-commerce. And the few examples here already show you that robots will come in different forms and shapes, ranging from purely mobile ground robots on the left to aerial robots to robot arms. And other applications include retail, especially inventory management and cleaning robots. But mobile manipulation can be such a powerful tool in many, many settings in the future, including also environments such as hospitals or the home. So in my talk, I want to give an overview of ongoing research in my group. So this is kind of really the things we do right now. And I encourage you to then visit the posters and interact with my students during the social hour to learn more details. So the topics we actively work on include accurate indoor localization using ultra-wideband. And that is work by Wenda and Abhishek. Full body motion control for mobile manipulation, which is work by Adam and Xing Tong. Inverse dynamics learning for improved accuracy. You can ask Siki all the questions you have about that. And then self-supervision for robot perception and grasping. That is a project by Alan in collaboration with Epson. So let me start by talking about indoor localization, which is kind of a nice transition from Igor's work, because our goal is similar. We aim for reliable, accurate, and scalable positioning for robots in dynamic and cluttered indoor environments. Our goal is to exploit the complementary nature of low-cost odometry sensors with what is called ultra-wideband radios. And ultra-wideband radios, you can really think of it being basically an inexpensive indoor GPS system. And so the advantages that we see by combining these two technologies is that it's low cost, robust, and efficient. It's conducive to heterogeneous systems, so we can also mount these ultra-wideband radios to assets and tools, not only to robots and also humans. And it allows you to get not always perfectly accurate, but long-term and absolute positioning in an indoor environment. So let me show you an example how that can look like. So here in this video, you see a drone flying purely on using ultra-wideband, and it flies through this tunnel, something that's difficult, usually for a vision sensor because it's dark and no features. And so it's really a nice complementary technology. And so here you see a video that shows you a few more details about the system. So, the blue circles are the anchors, so the ultra-wideband system. We use this on a nano quadrotor, so it's really small and lightweight, this ultra-wideband radio. And we have a motion capture system for ground truth. And these low-cost ultra-wideband systems do have biases. And here we, in advance, try to learn these biases and then use them online during flight. And you see that in the dark blue circle, we do much better than a standard approach. And so overall, we can achieve with this kind of prior bias compensation and learning 14 centimeters of root mean squared error in closed loop flights, which is pretty good. And this does not use any odometry. So that kind of allowed us to get a sense how good can we get in an indoor environment with ultra-wideband only. However, a determining factor, especially in cluttered environments, is where to place these anchors in the environment. And so if you think of an environment like the picture here on the right, could be cluttered, right? An office environment, various obstacles. Where do we best place the anchors to get the best position accuracy? Because obstacles introduce additional bias on these ultra-wideband range sensing measurements. And so here you see a quick result that we got very recently. You see the gray and green areas are obstacles, metal ones and non-metal obstacles. And the dots around the area are the anchors. And if you use trivial placements like in the two left images, the red are the ground truth position of the robot, and the blue is what we get from our ultra-wideband system, so our indoor GPS system. So it's not perfect. These blue dots are scattered around the red. If you use an optimal placement, that's what you see here on the right, you see it's significantly better. So we optimize the position of those anchors, assuming we know roughly where the obstacles are, and that can improve the performance overall. So you can think of in your warehouse, at least if you know where your shelves are, you could optimize the position of the anchors. And so we can get, in this particular case, an accuracy of 5.8 centimeters, and it's 51% better compared to the trivial placement number one. So I showed you how we can optimally place those anchors. And now it is about how to then online fly a UAV and get pose estimation. And so for that, we look at a variational based approach where you estimate not only the pose of the robot, but also the positions of the anchors, the obstacle-induced measurement biases, and the measurement variances. And if you do that, you get a significant reduction of 55% compared to, an approach that assumes hand-measured anchor positions, as an example. And so here you see we can get below an root mean squared error of 10 centimeters in most cases. So this is kind of this again is only ultra wideband at this point, and gives us a kind of base level accuracy of position in an indoor environment. And then this can be combined, with vision and odometry to further improve performance. So our idea is really that someone goes in an indoor environment, cleverly places these anchors based on prior knowledge, and this gives you, and then uses ultra wideband in addition with other sensing to improve your localization performance in the long term. So that's one thread of our work. Another core thread is how do we do full body motion control of a mobile manipulation platform. And in that area, we look at model predictive control as an approach and have two different, sub-approaches. One is often we have hierarchical objectives, and these mobile manipulation platforms have many degrees of freedom. So if you look at the image to the right, we envision that you have a hierarchy of tasks and then use the remaining degrees of freedom. For example, the highest priority is avoiding obstacles. Use the remaining degrees of freedom of the arm, for example, to already go to the end effector waypoint number 1. And if while doing this, there may be still additional remaining degrees of freedom that allows us to move the base already towards our next task, the end effector waypoint number 2. So it's basically like you would do as a human. You kind of walk, and while you walk, you spread out your arm to cross something, and you continue walking, and you never stop. So, we basically, our goal with this is to have efficient task execution robustness while still being computationally tractable. And so here are some videos of some results. On the left, you see, our first work on the mobile manipulation platform and what it can do. Even if there are disturbances, we can kind of push this bucket around. So we have mobility and manipulation. On the right, you see kind of, think of a Vader robot that balances objects on a plate around obstacles or around a disturbance. And so we need the full body motion to do the task efficiently. And here's a video of the task prioritization where you see that the robot base, when I start the video on the left, can already move towards the second goal while, it is doing, for example, a picking or placing task. So you see, the end effector stays at a fixed position while the base already moves to the next position of the end effector on the left, right? And it's a smooth and efficient motion, while on the right, basically it does it sequentially, moving to a point, staying there, and doing the next task, which is pretty typical in mobile manipulation at this point. We then looked at how can we further improve the performance of our controller on arbitrary tasks. And so typically, the robot's arms and also mobile bases come with a baseline controller, which you see in the gray shaded box. But it not necessarily gives us the accuracy we want. And so we learn a green inverse model from data to further improve the performance of our robot. And so if we do that, we can get significant improvements, up to 62%, That is an example where we tried this type of approach on a flying vehicle. But overall, this works on any black box system, right? And any gray box you have that is stable, you can learn this green inverse model and improve performance by just adjusting the reference input to your baseline control system. And so the advantages of this method is it's generalizable to arbitrary trajectories. It's kind of an inverse model, and it's very data efficient and improves also safety because we better follow the desired output. So our goal is really that the desired output on the left is equal to the actual output to the right. And we did this for ball catching, where we have to be extremely accurate in time and space to catch a ball in time. And so here is a more detailed video, right, where we throw balls from different directions, and the learned robot motion, or the inverse model, it helps us to achieve 20 to 25% more successes during catching than without the learning. And you see it's very narrow, the cup and the ball, but we are not perfect. There are failure cases, and you see how challenging this task is. So here, we didn't predict actually the motion of the ball very well, and here the tracking of the base was just not as good. So finally, I want to just give a quick highlight what we are doing together with Epson. They really push us to achieve industrial requirements for robotics system performance in vision and grasping in real factory environments. And we look at this for a perception task, and we optimize performance by optimizing training data for the neural networks. And so here, an eye-in-hand camera is used. That's what you see on in the left image. So we look at the scene from multiple directions, and since it's a robot that moves the camera around, we know the transformations between the different images. And from that, we can get a very good, accurate multi-view estimate of a certain part, and we can then use that for supervision of real images from difficult viewpoints. Basically, we use a robot arm for perception, and then we get, the advantages are we get greater quantity of labeled data, and we can adapt to given runtime environments by self-supervision. And if you are interested, Epson has released a data set on this. And with this method of fine-tuning the neural network, we achieve reductions of false detections by over 50% and a reduction of rotation error by over 40%. So finally, I really encourage you to interact with my students during the poster session to learn more about fast and accurate motions of robots in cluttered indoor environments, ranging from our indoor localization to perception control and learning. All our research is found on dynsyslab.org. We also have a big effort in safe robot learning, which I haven't talked about, and you find everything at saferobotlearning.org. We are organizing a NeurIPS workshop soon. We have a review paper and open source code, if that is something you are interested in. Thank you.
Thank you so much, Angela. I think in the interest of time, we would like to defer the questions to the panel session. And can we bring Alex on stage, baby? Wonderful. I'm so glad to have Alex with us from Ocado. Alex brings over 10 years of experience in leading advanced robotics, machine learning, and simulation teams. Alex has played a very important role in developing Ocado Smart Platform for automation in warehousing, and in his current role, Alex oversees research, development, and support of next-generation systems such as picking in autonomous mobile systems that will power the Ocado Smart Platform. Career highlights for Alex include successful award of 2 EU Commission-funded research projects working with several high-profile European universities. Alex is a leader in AI and robotics, and his insights have been reported in leading media outlets such as QCCon London, Wired, and the BBC. And before he was at Ocado in 2010, Alex developed real-time safety monitoring systems for clients such as Rolls-Royce and Royal Navy. Alex has a background in aerospace industry, and he studied mechanical engineering and computer science in AI at Edinburgh University. Over to you, Alex. I think all of us are very excited to hear from you.
Thank you very much for that very kind introduction. Let me share my screen and then get on. I appreciate time is limited today. Oh, sorry, everyone. Right, sorry, old school. Okay, I am going to have to give this talk at a bit of a gallop. I've probably got too much content. So yes, I'm Alex Harvey. I am Chief of Advanced Technology at Ocado, and I'm going to be talking about pioneering the future of robotics at Ocado. So today in the talk, I'm going to discuss who we are, because I'm sure none of you have got a clue about Ocado or Ocado Technology. I'm going to talk a little bit about the Ocado Smart Platform and robotics for pick and pack. So yeah, we're not an academic organization. We are a commercial organization, and we are here to transform online grocery through cutting-edge technology and serial innovation. Ocado Technology is a really diverse group of engineers, encompassing all the kind of like spectrum that you can imagine: Java, software, robotics, embedded, machine vision, learning. We combine all the kind of competencies and capabilities that you can imagine in order to build this kind of end-to-end software and hardware platform that we provide as a managed service for international retailers. Our retailers, so hopefully for those of you who are located in Toronto, you might have seen Voila vans from Sobeys. So the Voila service is an Ocado online grocery service branded as Sobeys or Voila. And so this is the kind of the classic business model that we have as a tech company. We are providing the underlying technology to international retailers to help them dominate in their market and provide the best, most exciting propositions for online e-com grocery. Our development centers range throughout Europe and North America. As you can see on the map here, I won't try to cover them, but obviously we have one in Toronto, which is why I'm speaking to you today. Now, a difference between how Ocado does online e-com grocery logistics versus most other companies. So the conventional way is to have, everyone has suppliers and wholesalers. The conventional way is to have regional distribution centers that kind of aggregate, and then people do trunking on the back of an articulated lorry to stores, and then they operate something called in-store fulfillment, or where you, member of the public, can go in and buy your weekly groceries or your daily groceries, and then you'll see members of the company, let's say whoever, maybe Sobeys also have in-store fulfillment from us, but wandering around trying to fulfill and complete customer orders for online grocery e-commerce and then deliver to the customer's home. We don't do it that way. We have these kind of large, but it can be small or medium-sized, highly automated warehouses we call customer fulfillment centers, so CFCs. And I apologize, there's probably lots of Ocado terminology in here. And basically we use loads and loads of automation robotics to do all of the tracking of inventory. From the moment any item comes into the warehouse, it gets systemically tracked. As you are adding to basket on the warehouse, we are playing a game of traveling salesman with all of our vans. Because of our approach, where we manage inventory and have this hugely sophisticated supply chain and demand forecasting capability, again, heavily leveraging machine learning and AI, we are able to operate at less than 0.5% waste compared to the conventional approach, which is more like 5% waste. And our order accuracy is 99.9 something percent, again, which is far in excess of the conventional way, where they can't guarantee stock availability in the same way that we can. So the Ocado Smart Platform, as I've alluded to, is this kind of end-to-end e-com grocery logistics. It contains everything from mobile, we've got a puppy in the background, sorry, web shop, mobile apps, automated fulfillment, store pick, routing and deliveries. Basically, it's pay-as-you-go, effortless online grocery logistics for international retailers. So the OSP warehouse we have built over the years, so the most advanced and densest storage and retrieval system that is available in the market for grocery logistics. We used to build kind of classic warehouses leveraging conveyor-based technology and mini-load cranes, and they were very efficient, and we still operate them, but they required an awful lot of capital investment. And you had to basically build the entire thing in one go, and then ramp the site as hard as possible, because when you built it, you invest hundreds of millions, and then you open it with only a few thousand orders a week, and you're not making great payback. And so it was a challenge kind of operationally, and you really had to be kind of aware and knowing what you're doing and willing to invest the capex up front. So what we did is we disrupted that world, and we built our own automation, which I was heavily involved in. So fundamentally, there are kind of only a few components. There is the grid, so comparatively simple extruded aluminium. There are the bots that operate like rooks on a chessboard, moving in X and Y above the grid. And then there are containers, and the containers sit sort of stack neatly within the grid. They don't actually interact with the grid. And within the containers, you either have stock items that we are picking from, or customer delivery containers that we are picking into, ready for dispatch and outbound and to send to the customer. So here is kind of like a very simplified schematic of that. And yes, if we dive into the hive, it is the most automated and sophisticated. Grocery logistics is fantastically complicated when you consider the world of online logistics and retail. Grocery logistics, each of our baskets, a customer order tends to be over 50 items of chill, ambient, and frozen. We have to guarantee 1 hour delivery slots or less because we now have an immediacy offering. And so having to be really, really accurate and guarantee end to end the quality of the food and being able to maintain those different temperature regimes. Each customer item basket that we have could contain up to one of 60,000 different items. Right, so just think about that. Our customer containers can contain any combination of 60,000 different items that range from multi-packs of water through to bunches of bananas and everything else in between. And so typically when people look at a pick and pack problem, bin picking, they're always using kind of rigid objects that can have CAD models, but we aren't able to do that. So we're looking for generalized dexterous manipulation. So here are the bots whizzing around on top of the grid. They move at 4 meters per second. And pass with just a few millimeters in between them. The bots themselves don't pick the items, they pick the containers and take the containers to a pick station. So this is a grid in Erith that is in contiguous surface area, 3 football pitches, and contains 3,000 bots that we control in real time with ultra low latency. We even had to build our own RF system, our own RF simulations. There are so many things I could go into in this talk, but I'm going to have to skip over for time. So here is a human person picking. You can see at the top of the screen the white containers containing product. She is picking into the white containers that contain red containers. The red containers are the delivery containers. And you can see they're packing straight into plastic bags to aid in that kind of doorstep interaction. So the driver just takes the plastic bags and takes them, or paper bags, depending on your local territory. And you can see that the person is scanning, confirming each item that they're picking. And this is part of our assurance of stock quality and inventory control. So onto the hopefully more exciting part of the talk, after setting the scene of who we are and why we are in this space at all. So robotics, and specifically, whilst we do an awful lot of different robotic systems, the one I'm going to talk to you a little bit about today is generalized dexterous manipulation, which we simplify to call pick and pack. So, here we go. Here's kind of what everyone imagines when we're talking robotic manipulation for picking and packing groceries, the kind of most sophisticated end effector you can possibly imagine. But actually, when we started the journey, and today we have a number of these systems live in our operational warehouses, picking customer orders, we are already picking up to something like 50% of the range by volume. And here you can see the system's picking and packing like the human did. And so in this context, we have retrofitted the robot. And as you can see, it's a very simple end effector, so a suction cup. Even though we totally understand and expect that at the end game, when we are picking and packing 100% of the range as quickly and as efficiently and with the same level of quality as a human, then we're going to need far superior and more sophisticated end effectors. But like any good engineer, start simple and then iterate and add complexity as you go. Talking about complexity, so here is the output or one of the experiments from one of the Horizon 2020 projects that we did called SOMA about soft manipulation using object affordances and environmental constraints. And so you can see the simulation, the planner in the top right-hand corner, assessing the mango. We 3D printed mangoes because we didn't want to crush lots of mangoes, to understand the best possible strategy for using the container itself to aid in the grasp, such as we did there. We also not only use kind of discrete components as part of our end-to-end system. Here is an example from one of our researchers in Sophia using end-to-end reinforcement learning to pick and pack. As you can see, the items have been experimented on several times. So we're looking a little bit the worst aware. But as you can see, the fluidity of the motion is just incredible. And so this is an example where we have one system, but the system can either operate using kind of discrete components for grass generation, path planning, the packing complexity, or we can deploy the system like this using end-to-end deep reinforcement learning. And again, this engineer, a guy called Ivo Popov, fantastic guy over in Sofia, he was actually training the system in Erith from Sofia using Vive controllers and just a big TV screen, and able to get performance like this. And it's just incredible what we can achieve with the kind of the breadth of technology. And the goal for us is really being able to always make use of the latest advances in technology, but have systems where we can deploy and augment one set of approaches or architectural patterns with any other technology that arrives. We use huge amounts of simulation. Our simulations are actually emulations or digital twins. They can be connected to the physical world. We can use them to play kind of crystal, look into the crystal ball and look into the future. So whenever we build a warehouse, we stress test it with hundreds of days of running, many tens of thousands of orders. We look for the busiest Christmas, the quietest summer. And here we have the grid in Erith. And this is actually picking and packing using robotics on the grid. So not only do we deploy robotic pick systems under, in the pick stations to retrofit to humans, we also take advantage of the fact that we don't have to do that anymore. We can deploy the robot arms next to the bots and like this. I guess this model is kinematically correct. It has high fidelity physics and Gaussian distributions and probabilistic functions for things which are not guaranteed by physics, such as pick time, because pick time of a robot is not deterministic. However, we don't spend an awful lot of time on fancy graphics, I'm afraid, because this is like a tool for understanding what to do rather than for sort of like sexy presentations. So sorry. Another Horizon 2020 project we did was second hands. And so talking about sort of, whole body motion and inverse kinematics, here we led the program building this humanoid robot to proactively offer assistance to maintenance technicians. So it's learned the task, right? It has learned the outcome of the task that we're trying to achieve. It has an understanding of the capabilities, of the affordances that the robot has, and then is able to anticipate the need for help. Front door, this is not most unhelpful. And as you see, we have this kind of beautiful research where the robot is able to anticipate the need for help and then collaboratively complete a task such as removing the safety guard and moving it to a different location. So typically the engineers have to work alone, and so we noticed that they did a whole bunch of things which were not great in terms of their musculoskeletal health, such as stretching too much. As you can see here, the robot didn't anticipate the need for help quite as well as it should have done, and so the human had to command it to come over, a bit like Alexa. We are accelerating the efforts that we have been performing in this space with two recent acquisitions. One with Kindred AI, who are based in Toronto, and I'm sure hopefully many of you are aware of Kindred AI and the fantastic work that they do, and another company based in Las Vegas called Huntington Dynamics. So Kindred AI, proven production experience with 180 installations and counting. I think they've picked about 200 million items by now, incredible uptime, and amazing use of supervised autonomy for recovery and reinforcement learning. And then Huntington Dynamics have a revolutionary new approach to design and manufacture, such as cyclodal gearboxes printed in situ, fundamentally changes robot economics with 10 micron accuracy. So today we are using the UR10Es, but they obviously have a fixed form factor and have a certain price point. We are able to manufacture robot arms with Huntington at a vastly reduced price and even more capability, and are able to change any configuration parameter we want, link lengths, number of joints. It is fantastic stuff. Hopefully some of you will be out there interested in wanting to join Ocado Technology and the wonderful Kindred team that we have in Toronto. Please, either approach anyone that you know or log into our careers website to find out a little bit more. Thank you very much for listening, and hopefully I just about managed to stick to time.
Absolutely. Thank you so much, Alex. I think that was indeed
Thank you.
Thank you so much. I think the feeling of applause is something this platform brings back that other platforms did not have. I'm really loving it. This was a true whirlwind. I think Ocado is doing a lot of interesting stuff. Do we have questions? Aidan, do you want to bring this up?
Well, can I Do we have questions? Can I go to the front door? Just like, I know this is really
yes, please go ahead. Perhaps in the interest of time, let's bring John, and then questions for Alex can be punted to the panel session. So let's bring John on board. Wonderful. I think this has been such an exciting set of talks. Now we have Professor Jonathan Kelly, who leads Space, Terrestrial and Autonomous Robotics Systems Lab at the University of Toronto Institute of Aerospace Studies, where his group carries out research at the nexus of sensing, planning, and control. He holds a Canada Research Chair in Collaborative Robotics and was Dean's Catalyst Professor from 2018 to 2021. And prior to joining the University of Toronto, he was a postdoctoral researcher in the Robust Robotics group at MIT. Professor Kelly received his PhD in 2011 from University of Southern California. And currently, John's going to talk to us about a cheekily titled talk, EDM, Netflix, and Robotics, a distant geometric perspective on inverse kinematics. Over to you, John.
Okay, thanks so much, Animesh. I hope folks can see my screen. Can someone just maybe, Animesh, can you just verify? Hopefully it's visible.
I think you still need to share.
Okay, I'm trying. Let me try this one more time. Sorry, folks, technical difficulty. Let's just go back over to the, okay, I got it. All right, yeah, I'm embarrassed here to say I'm the guy who's having the issues with screen sharing, but fine. That's all right. Okay, so let's get started. All right, okay, you should be able to see it now. Great. Okay, thanks everyone. So yeah, thanks Animesh for the lovely introduction, and this is a great talk. Short one to follow Alex. I'm really glad Alex brought up the problem of inverse kinematics. So I thought I would go a little bit more on the theory side with this talk and just talk about one very specific thing that we've done recently in my group with two fantastic students who have led this work, Philip Maric and Matt Gamu from our STARS lab. We do a fair bit of work in collaborative robotic systems now and manipulation. From the perception side, from the control side a little bit, and also from the planning side. But today I'm going to talk about something very specific. And later on, Trevor, one of our other students, will be presenting in the poster session. So I encourage you to check that out as well. Something else we do with manipulator systems. So today, EDM, Netflix, and robots, a distance geometric perspective on inverse kinematics. Okay, so what is this? Well, I came up with a talk title, I confess, before I filled in all the slides, and I've stolen some of these slides as well. So let me just give you a very quick overview. So manipulators, Alex just showed you some great pictures, right? They are used for reaching, grasping, and working with a wide variety of objects. Typically, as Alex just mentioned, which is great, your manipulator uses a series of revolute joints that are connected by rigid links that are fixed in length, and they form an open kinematic chain. So like your arm, something that flops around until you apply torque to the joints. And the end effector is the thing that actually does the work, that has the gripper or something else attached. It's going to pick up your product and move it from place to place. So many of you, if you've studied kinematics, probably know about the problem of forward kinematics. So this is the problem of finding a gripper or end effector pose, so some 3D position of your hand, if it were in space, that corresponds to the position you reach when you set a certain value for each joint angle. So you specify the joints here, and the end effector position is something in this task space in 3D that is a function of the joint angles. So forward kinematics is nice and we'll call it easy, right? In the sense that the kinematic mapping it's nonlinear, but it's easy to derive analytically, and there's a nice unique solution for any input. So if I give you some joint angles, you immediately get the end effector position, assuming that you know end effector position and orientation, assuming you know the link lengths. So that's great. So for an open chain kinematic system, forward kinematics is easy. And although it's nonlinear, it's easy to solve. But there's a different problem that we have when we're trying to manipulate objects in general, and that is the inverse of what I just told you. So the inverse of forward kinematics is inverse kinematics, of course. And this is the problem of trying to find the joint angles that correspond to a given end effector pose. And so often what we'll want to do in almost all cases with manipulation is to know where we want to grab something, and then have to work backwards to determine how we should set the joint values in order to achieve that end effector pose. And this problem, it actually turns out, ends up being very, very hard, because now we are trying to go backwards from something in task space to a set of joints which live in the joint angles which live in the configuration space of joints of the robot. And of course, joints are revolute; they go all the way around usually. And so this is a much more difficult problem that admits possibly an infinite or maybe even an empty set of solutions, and you don't know in advance necessarily whether you can even solve the problem. So generally, the way this problem is approached in the existing literature and in actual application domains is to solve using local optimization. And in some sense, that's the best you can do. It's a strongly NP-hard problem in general for most manipulators that are redundant. So it's non-trivial. That's the takeaway here. If you were to solve an inverse kinematics problem, the first thing you would do is define your end effector pose. So if I want to grab a product in a warehouse, for example, or something like a piece of produce in a bin, right? I set the end effector pose, and then again, I work backwards. I've defined my goal of end effector pose, and then I try to minimize some cost function based on how close I can get the manipulator to that end effector pose using some type of local solvers. So sequential quadratic programming or something else, some other flavor that is subject to a series of perhaps equality and inequality constraints. And then once you've done all this with your local solver, you have to check that the resulting solution actually doesn't violate any of the constraints that you have. So in general, very, very tough. And important to note is that as you increase the number of degrees of freedom of your manipulator and or some of the other properties of the system, the problem gets worse. So when you add obstacles and other constraints, larger number of degrees of freedom, the problem gets harder. So today I'm going to pitch to you very briefly that maybe this isn't the only way you can approach this problem in the joint angle space. And so one of the interesting issues that arises in inverse kinematics is that you're trying to determine some decision variables that live in the configuration space of the robot, and that's this amorphous blob C, and that is the space of joint angles. And we know that the forward mapping, right, as a function of theta, the joint angles, is highly nonlinear. And because the constraints that I'm talking about are in operational space, in task space, where the end effector lives, there's a very complicated relationship between C and here what I have, like the stylized X. So this is not great. And so the question here is, can we do something different by looking at the problem in a different way that Matt and Philip have worked on extensively? Can we avoid this very nasty nonlinear map from configuration space of joints to task space? And so I'm going to tell you that there is a way to do this, and we weren't the first to think of it. Some earlier work by Porta in 2005 and even a little bit before that used something called Euclidean distance matrices. So I'll explain that in just a moment. I think when you see EDM, you're going to think, of course, dance music, right? This is not dance music. This is a distance matrix that is filled in with distances that are attached to the robot. I'll show you how this works in just a moment. And the problem we're going to solve is an instance of what is called the distance geometry problem. So this is going to be a different way of looking at inverse kinematics. A Euclidean distance matrix, which I'll show you an example of on the next slide, is just a collection of distances in the Euclidean sense between points that are arranged into a symmetric positive semi-definite matrix. And when you see symmetric positive definite matrix, if you've worked in the field for a while, you will note that there's lots of interesting things you can do with symmetric positive definite or semi-definite matrices. And so distance geometry actually ends up being the problem of localizing a set of points given pairwise distances between them. And it turns out that this problem in various forms or with modifications appears all over the place: computational chemistry, signal processing, acoustics, and it's been very well studied, but not really in the context of robot manipulation. All right, so what are we talking about? So I'm going to give you a very simple two-dimensional planar robot with, in this case, 5 joints. And I'm going to put a distance matrix down here, which has zeros along the main diagonal. And what I would do here is to add single points at the center of each joint. And then I would measure the distances between points at each joint. So if I put one point down, stick it at the center of each joint, and then I measure the distance to other joints, right? I get a matrix that is 0 down the main diagonal, because the distance between a joint and itself is 0, and then pairwise distances that are symmetric, because the links are at a fixed length, right? We're dealing with a revolute manipulator here, so the links are a fixed length. And so I'm filling in this matrix of distance values, right? And this is all happening in the same space, in the task space. So I'm dealing with distances that are not joint configurations. They are actual Euclidean distances in task space. And that's why this actually works really well. We'll see in just a moment for some more complicated inverse kinematics problems. So I continue along this way, and then once I have a desired, in this case, simply an end effector position, because we're working in 2D, I can fill in one additional value in this matrix, which is the distance I want between, we'll say P5, which is the end effector point, and P0, which is the base of the manipulator. And that actually fixes effectively the position of the end effector. And then I can try and proceed to fill in all these question marks. So how do you do that? Well, it turns out that that body of work I was talking about in computational chemistry and sensor and network localization has some very rich and well-studied techniques for doing what's called EDM completion. So filling in empty spaces in Euclidean distance matrices. And if I can do that, if I can fill in these spots, then I can actually, once I have the pairwise distances from this filled in matrix, I can go back and recover the exact configuration of the manipulator very, very quickly using a standard algorithm. So if I can fill in the matrix, then I'm basically home free. So I'm going quite quickly today, but I'd like to encourage you, if you're interested, to look at distance geometry in general. It's a fascinating topic. I didn't think in my academic career I would look at computational chemistry, and I've actually had the opportunity to recently. It's been really great. Also, what does this have to do with Netflix? Well, we're a bit beyond the old Netflix DVD packages that you used to get in the mail. Sometimes you still get DVDs, but most people just take their Netflix online. But with Netflix, what is the connection? Well, it turns out that many of you will have heard of the Netflix problem and the Netflix prize. It was a $1 million prize for improving the Netflix movie recommendation system. And it turns out that if you stack customer preferences in a matrix that looks just like a Euclidean distance matrix, where you've encoded consumer or customer preferences in a feature vector, you stack them all in a matrix. When you want to figure out what someone wants to watch, you want to fill in a spot in the distance matrix, actually, in terms of a point in feature space that identifies what the consumer you don't know about might be interested in looking at. And so very interestingly, the task of low rank matrix completion is actually very closely related, if you can believe it, in many respects to the problem of inverse kinematics in this formulation for high degree of freedom robotic systems. Okay, so I don't want to take too much time, again, as just to keep us on track, but it turns out that within this framework, one other nice thing you can do is incorporate some very common constraints into the system. So first of all, for a 3D, 3 degree of freedom manipulator, we would define the structure, we would define the pose variables we wanted, and then we're also able to very easily enforce symmetric joint limits and also to consider spherical obstacles in the workspace. And you can approximate any obstacle by a series of covering spheres, and so this actually works really well too for obstacle avoidance. You would then go through the process, you form your incomplete Euclidean distance matrix, you solve this, and there are some really lovely techniques from Riemannian optimization that take advantage of the Riemannian geometry of one of the manifolds that's involved here. And once you do that, pop, out comes a solution of the joint configurations you need to solve your distance geometric inverse kinematics problem. So we did an experiment with this amongst others, and we found that with obstacles in the workspace, we've just taken 3 common manipulators here, including the UR10 manipulator that we have in the lab that Angela had showed in her talk. And we tried to solve these problems using this modified distance geometric approach. And spoiler here, without going into too much detail, it turns out that if you use the distance geometric method, as the complexity of the environment increases, as the density of obstacles becomes greater and it becomes harder to find solutions, the distance geometric method actually outperforms one of the state-of-the-art local search methods by a fairly substantial margin in terms of both success rate and also solve times, in fact. So, okay, so that was a whirlwind tour of EDM's not electronic dance music, although I like EDM music as well. And I encourage you, just very quickly at the end here, if you're interested, to please visit our website, starslab.ca. I just meant to put down the URL here, but starslab.ca. Please check out this work. We have about 4 papers on it now. The most recent one's coming out at the IEEE Transactions on Robotics journal at some point in 2021 or early 2022. And with that, I will potentially take any questions, although we might be out of time. So thanks, everyone.
You certainly have a lot of fans, John.
That's just me hammering the. That's just me hammering the. The item again. So thanks, everyone. Sorry, that was very quick. I apologize. It's a lot of technical detail to digest, but
nonetheless, I think the talk was true to its name with EDM and Netflix. Fair enough. I think we will defer the questions to panel and move on to our keynote. Can we bring Matt on, Aiden? Wonderful. Great to see you, Matt.
I see myself.
Yes. Are you able to share your screen?
Yeah, let's see here. Let's see what I can do there.
Seems to work. Yes.
Well, I better hide that window.
Okay, now that things are working, I'm glad. So, for everyone else, I'm so very elated to present to you Dr. Matt Mason. Matt is a chief scientist at Berkshire Gray and a professor of robotics and computer science at Carnegie Mellon University. He earned a bachelor's, master's, and PhD degree in CS and AI at MIT, finishing his PhD in 1982. Matt has spent over 40 professional years solving unsolvable robotics problems and is an internationally recognized technology leader. Matt has more influential publications in leading robotics journal than just about anyone, and he wrote the book on how robots pick up things. He was the director of Carnegie Mellon Robotics Institute from 2004 to 2014. He is a fellow of the AAAI, a fellow of the IEEE. He's a winner of Systems Development Foundation Prize and an IEEE RAS Pioneer Award and the 2018 IEEE Robotics and Automation Award. Aside from this long list of awards, he also happens to be my academic grandfather. He has given us pearls of wisdom throughout our career. The one thing that I remember during one of our chats at some time is Matt said, you should definitely work on manipulation. Dexterous manipulation is a very hard problem to solve. Perhaps you will not make any progress at all, but you'll have a wonderful career nonetheless. Over to you.
Well, that's
Matt.
rather pessimistic.
No, I think it has been so fun. Manipulation is a very hard but equally interesting problem every day.
Well, thanks very much for the introduction. That advice to you sounds like some advice I got from Alan Newell a long time ago, where he said, pick a problem that will last you a lifetime. You pick a really, really hard problem, one that you're in no danger of solving. But obviously, that's not an attitude that works well in industry, right? So that's been one of the interesting changes in my life. So, and that's the general tone of this talk. I've been an academic for 40 some years, but for the last several years, I've switched to spending most of my time in industry. And so I'm going to try and figure out the things that I've learned and bring them back to you and show you something about what's happening at Berkshire Gray at the same time. So the first thing I want to do is just to kind of start us out would be to show you this video, and there's some music. This is so we're going to watch it now with the music, and then we'll go back and watch it again, and maybe pause it here and there so we can talk about what's actually happening in this video.
Just to let you know, Matt, I don't think the video sound comes over. So for now, this is fine.
Oh, really?
But feel free to speak later on.
So I hear that the sound didn't come across, so y'all missed that marvelous music. I even turned it down a little bit. I was afraid it was too loud. Well, so we're going to watch it again, but this time without the music. And so I can interrupt and unpack some of what's going on here. I don't think it matters that some of our other things have music or don't have music. Well, let's see. So the main point here is that it can handle a lot of different items. So you saw some tubes and envelopes and other things. Now, the main thing here, and I think it's something in common with all robotic manipulation videos, is sooner or later a human shows up and does stuff which a robot should find just humiliating, because humans are just so great at manipulation compared to robots. Somehow we as spectators, we don't even think about it, right? We see a human doing something comparatively amazing and it doesn't matter. And instead we watch the robots and we think that's cool. Anyway, what it's doing here is it's dropping these things through this device called a hyperscanner. And that hyperscanner can see the object from all angles. So it doesn't matter what orientation it is, it can see the barcodes. Now they've been separated, they've been identified, and they're being carried up to an area where a sweeper will push the object onto one of these so-called linear sort wings. So there's 3 linear sort wings. So that shuttle runs up and down the linear sort wing, and it can drop it either to left or right. And there's many, many compartments it can drop it into. And there you see another genius manipulation system doing the stuff that at the periphery of the automated system. So that's the system. You can see it's installed at FedEx, and it's running. They're running at several FedEx facilities, and I think almost all the systems I'm going to show you here are in customer facilities. I think there's one exception, but last time I gave a talk on this, afterwards I realized people had just kind of assumed that we were showing things that were working in our own facilities, but almost everything's in a customer facility. So what I want to do is start with a very brief introduction of myself and my story, and then go to the Berkshire Grey story and tell you, give you a quick overview of that, and then try and talk about what I've learned over the last 7 years that I've been involved with Berkshire Grey. So that's the plan. So my story, yeah. Let's see, it's pretty simple. I've been doing pretty much the same thing for 40 some years. I started out working in compliant control, which was different. And that one paper got more citations than I've gotten on any paper the rest of my life. So, you know, my whole life has been an embarrassment in that respect, or disappointment, I should say. But almost everything I've done, you could sort of call part of the mechanics of manipulation. Published that book 20 years ago, and that's been that's my whole story. Now, what you might notice is that there's no part of my story that involves either business or logistics. I mentioned Alan Newell and the advice he gave me about picking a problem. Another bit of advice he gave was to just stay away from business. You know, it's complicated. It's nice and simple to stay in academia, and I did that until 2014, as you'll see. Also, not part of my story is logistics, and so that raises the question why I'm here talking about logistics and why you all are here listening to me talk about logistics. I think a lot of times you can learn more from somebody who's a beginner, somebody who's just learning things himself. And then in explaining what he's learned, you know, sometimes that's a good way to learn. I see this in my office. Sometimes during office hours, students will come in and they'll ask questions. And if I answer the question, I'll give them a long-winded answer and they're kind of nodding but looking puzzled. And then maybe the student right next to them gives them a 10-second answer and they say, oh, I get it. And that's, you know, and so that's been my experience. Maybe this is like that. I'm still a beginner, still a student, but maybe I can relate some of what I've learned today. So, oh, and by the way, if you want, you know, real expertise, there's this fantastic textbook online, free online, and that's where I turn sometimes when I need some help with some details. Now, okay, as I said, I stayed out of business for most of my career. And it wasn't really that hard because when it comes to autonomous manipulation and commercial applications of it, I was just a pretty serious skeptic. And now, an exception to that is automated manufacturing. Automated manufacturing has been a fantastic success for autonomous manipulation. So yeah, that one's a good one. But there are many that have been floated over the years. Everybody's got a vision. One of the most prominent was that Bill Gates wrote an article in Scientific American saying we would all have robots folding laundry in our basements. Not going to happen anytime soon. There are many others, right? They're easy to find. You're going to have robot butlers, robots delivering the beer, robots cooking for you, robots doing the vacuuming. Okay, none of them come to fruition except, you know, the vacuuming thing turned out to be real. People kind of overlook it. I'm not sure why, but the Roomba was a huge success, and it is autonomous. And I'll say it's manipulation. It's taking tiny little bits of dirt and, you know, putting them in its stomach or putting them out, you know, in some waste can. So I call that a kind of manipulation problem. So I was wrong about vacuuming. There's one tiny niche of domestic service robotics which worked, but my skepticism has generally been justified. So that's where I was. And then what happened? Oh, I forgot this one. Yeah, Google, Andy Rubin. Many of you remember when Google acquired several robotics companies, and we were all wondering, you know, what was this amazing vision they had? Andy Rubin was the leader of it, and you know, what were they going to do? It was very exciting, trying to figure it all out, and we were all discussing, speculating on what Google had in mind. And then, as far as, you know, the answer never came. I still don't know. If anybody knows, send me a note, okay? Anyway, so I was a skeptic, and I can tell you at the exact time when I was converted, because Tom Wagner, who is the CEO, the founder of Berkshire Grey, showed up at my office. I looked it up on my calendar. It was May 6, 2014. Tom Wagner shows up. 2 hours later, I'm a believer. So, you know, for me, this was an epiphany event. And the word epiphany for me has associations with Christian dogma. So I'm sorry, this is a little bit perhaps sacrilegious to this metaphor, but this is this little cartoon of my epiphany moment. So that's Tom Wagner playing the role of God up there in heaven, and you know, hitting me with a thunderbolt, and there am I, you know, yeah. Sorry, I don't have words for it. I see the light, and I'm convinced, and at this point, I mean, I'm sorry if it begins to sound like a prayer meeting. I'm not sitting around. I'm not sitting around the registration cards or asking for donations or anything. Okay, but anyway, this was my epiphany event. 2 hours from skeptic, confirmed-ish skeptic, to total believer. And I was signed up. I may not have signed up on the spot, but you know, if you had forced my hand, I would have. I was convinced. So that's my story up to the point where I joined Berkshire Grey, and the Berkshire Grey event, you might say the epiphany event. Let me back up a little bit from there, and we'll come back, and I'll but let me back up slightly to tell you how Berkshire Grey started, because I wasn't there at the very beginning. So what happened was Tom Wagner was this chief technology officer at iRobot. He left iRobot in 2012. There's a blog post on the Berkshire Grey website that explains this in a little more detail. He fills a whiteboard with 45 ideas, and he works through them, and you know, very diligently exploring each idea, visiting people, looking into different applications, and eventually converges on one idea, which, you know, I'm going to call the vision. And this is the vision that I got at the Epiphany event. So I'll come back to that and give you some details of it in a moment. But let's see, just to finish this timeline, a year later, 2013, Tom founded Berkshire Grey, recruited a couple of guys, a couple of great guys. The three of them worked on it for a while. In 2014, he made a recruiting visit to Pittsburgh. That was when the Epiphany event happened. I joined, some other guys joined, opened a Pittsburgh office. Now, really the next event was 2018, 4 years later. We were in stealth mode until 2018. And it was only then that we emerged from stealth mode, told everybody that we were doing warehouse automation, which is what a lot of people guessed we were doing anyway. But and then just a few months ago, went public. We're listed on NASDAQ now. And then what? Because, you know, back there in 2014, when I joined up, I was looking at a public offering as like the prize, as the end game, but it's not. It's really just part of the beginning. And so, you know, we're going on. We're still growing, building new systems and so forth, but I'm not going into that so much today. Okay. Oh yeah, yeah. You know what? I was on the phone with Oliver Brock at University of Berlin. I think that gripper that we saw earlier, that soft gripper, came out of Oliver Brock's lab. So you've already seen some of his work in this workshop. I was talking to Oliver, and he says, you know, that's the first IPO in robotics of a robotics company since iRobot 16 years ago. I didn't know that. I don't think anybody at Berkshire Grey had actually thought about that, but looked into it. As far as I can tell, that is true. It's the first IPO since iRobot. The valuation when we went public was around 2.2 billion. So in the commercial world, I guess you call that a success. So how did it happen? What was this vision? What was it that what was the content of that lightning bolt that Tom Wagner struck me with in 2014? And the answer is warehouse automation. Now, I'm calling it that. I don't know. We don't seem to really have a good term for it. It's broader than just warehouses. It includes retail distribution centers, parcel package distribution centers like at FedEx or the post office, and lots of other things. But we'll just call them all warehouse automation or logistics. Now, at this point, you're probably saying, well, how could this possibly be a surprise? How could you have been a skeptic? Because warehouse automation, that's not a surprise that that's a good application for robotics. Well, for a lot of us, it was a surprise, even as recently as 2014. How could that be? Really, there's two things. First is, I just had no idea how big logistics is. Okay, the whole, when you look at the whole distribution network and all the warehouses and the retail facilities, and it is ridiculously huge activity. The other thing is, I'm embarrassed to say it, I thought it was kind of a solved problem. And I've talked to others that viewed it that way. The reason is that Kiva had recently made a big splash showing off this really amazing system where they have these little mobile robots that would pick up shelves and carry the shelves to the human. It was a goods to human system, and the humans would pick from the shelves and do order fulfillment. Amazon acquired Kiva for something like 780 million, something like that. And so Amazon started doing fulfillment with these Kiva systems. And it's kind of like, I was kind of under the impression that Amazon had taken over retail distribution and Kiva had solved Amazon's order fulfillment problem. So, problem solved. And that turned out to be very, very wrong, very naive. So, so why is warehouse automation such a great app? This is basically the vision that Tom Wagner gave me. And if you want the details, you can find a lot of this in the investors phone call when we went public, which is still available online. There's a pitch there significantly similar to what he gave me. So the first thing is, and I can't remember, somebody pointed this out earlier in the session, warehouses, automation of warehouses is almost negligible. Very few of them are automated. So we saw a beautiful automated warehouse, or at least some automation in the warehouse in the Ocado talk. But very few of them are automated. The labor spend in warehouses is very high. I'll give you some numbers in a moment. And in particular, picking of items from shelves, from bins, off of a pallet, it's spread all over the place. It's almost always manual. So that's the first thing. Now, the second thing is that e-commerce is driving all of this in a direction that's, it's making the problem much, much greater. If you look at this phenomenon, you think about what's going on with e-commerce, it means that work is being shifted from consumers to warehouses, okay? And so now it might be labor shifted from consumers to labor in warehouses, but to the extent that we can automate the warehouses, it's a shift of labor from manual to machine. And, you begin to think, it might be similar, who knows, we've got a long way to go. It might be similar to the agricultural revolution. Well, probably not, There's not a lot of us that spend our whole careers filling up our refrigerator or shopping in grocery stores. So maybe not as big as the agricultural revolution or the industrial revolution, but it's another, I think, historically significant shift of labor from human to machine. And the third thing is that this trend puts an incredible amount of pressure on retail establishments. Our customers believe that warehouse automation is for them an existential issue, and that's not an exaggeration, right? Big retailers, Sears, have gone belly up because of trends in the retail distribution. So all of these things make warehouse automation a really compelling case for automation in warehouses. Here are some of the numbers. I already mentioned I'm not a businessman. I barely know what a total addressable market means, but in the pitch, you would see that the total addressable market was identified at 280 billion. Most of that is labor. Some of it is also in material handling equipment. And so it is a big problem, and it's accelerating. Now, I think everybody knows that e-commerce is big. And we've all seen the impact in our own lives. We've seen stories about retailers going belly up. We see the growth of Amazon and other e-commerce providers. But let's think about it in detail. How big is it? What do the numbers actually look like? I made this vague chart just to get you to think about it. What percentage right now do you think e-commerce is of total retail? And here's the answer. When I saw this, I thought I must have gotten the wrong chart. But e-commerce is growing rapidly. It is accelerating rapidly. The changes because of this are enormous. And yet, it still has a long way to go. Its share of retail might have doubled in the last, I forget exactly, 7 or 8 years, whatever it is. But it can double again, and it could double again, right? It hasn't nearly taken over all of retail. So I don't know how much of retail it can take over, but looking at this chart suggests that it has a long way to go, and the pressure for automating warehouses is going to continue and even accelerate. So that's pretty much the whole pitch. And that's the vision, okay? That's why we need warehouse automation. So that was my story. That's the Berkshire Grey story. We're going to shift gears now, and I'm going to talk about manipulation. Now, there are many systems. So if you went back and if you could crawl all over that system that we had installed at FedEx and look at everything, you would find an amazing number of different technologies. And so, manipulation, computer vision, every different aspect of software engineering, machine learning, AI generally, motion planning. The list just goes on and on. But I think manipulation is the heart of it. I also think it's the most exciting part of it. And so I think it's actually central. What is manipulation anyway? If you think about the definition of manipulation, if you just look at the word itself, and if you look in a dictionary, sometimes the definition is it's what you do with your hands. But if you're in robotics, that's not a very good answer, right? And sometimes we manipulate things not with our hands, we manipulate things with chopsticks or with a forklift. So really manipulation is moving stuff around. What is logistics? Logistics is moving stuff around. It's about moving stuff. In this case, it's about moving stuff from the producers to the consumers, from the factories or the farms to the consumers. So it is a form of manipulation. So then that suggests that you kind of take a step back and look at the whole thing. Don't just like go in there in the warehouse and look at what one person is doing, picking stuff out of a bin and putting it in a box. Take a step back and ask how they're solving the big problem. One of my mistakes when I thought possibly warehouse automation was a solved problem was I was just up so close. I wasn't seeing all of the manipulation going on. So if you step back, well, let's do it by looking at one specific object. Let's suppose you have a mint, or rather you want a mint, okay? You want a mint. And let's say you're in Atlanta. I'm in Atlanta, so let's say you're in Atlanta, but the mint factory is in Minneapolis, 1,000 miles away. So what are your options? Well, okay, you call up the factory and you say, I want a mint. They say, no problem. We've got a courier standing by. We're going to hand him a mint. And tomorrow or the next day, he's going to hand you the mint. It'll cost you about $1,000, right? Couriers cost something like $1 a mile. I read that somewhere. Okay, that's not how we do things, right? How do we do it? How do we avoid paying $1,000 for a mint? It's ride sharing. Okay, that's what it is. It's ride sharing. When you have 1 mint in a courier or in a truck, it costs too much. So what you have is you have this distribution network, this big network, right? There are nodes, which could be warehouses, can be stores, could even be the consumer's home, could be the factory, could be the farm, right? And then you have edges, which are highways or whatever. And your mint is going to travel through this distribution network from, let's just call them all distribution centers, from DC to DC. And ideally, it would always travel on a fully loaded truck, okay? And now the cost is reduced all the way to 3 cents. A mint can go all the way from the manufacturer to you, and when you pick it up in the grocery store and pay for it, it costs you about 3 cents. It's an amazing gain you get from amortizing the cost of the transportation over all of the stuff in the trucks. Same thing with the transportation network, right? If you think about this, you know, when you fly from one place to another, you might go from node to node if you can't get a direct flight. And when you get to a node, an air terminal, right, they unpack the plane, except you unpack yourself. And then you sort everything, only people sort themselves. And then they load the planes, except you load yourself. So, you know, the differences are, well, you know, if mints were intelligent and mobile, they could just, you wouldn't need automated warehouses. All the stuff would just sort itself out. But probably you couldn't do it for 3 cents. Makes you also think the other way. Why don't we do people more like we do mints? Instead of just loading everybody in one plane, maybe you load them into a smaller compartment and then load that compartment into the plane. You could pack them more densely. Pretty sure the airplane transportation companies have thought about that, and it's not going to work. Anyway, one of the ways that logistics gets this ride-sharing thing to work is that they use a progression of container sizes. Okay, you don't fill a truck with 1 billion mints. Okay, because if they weren't all going to the same place, it'd be a big mess, right, when you get to the first DC. So you put them in containers, but you put them in small containers, then you put those in bigger containers, and in bigger containers, you know, the mint goes in a roll, and in a box, and in a case, and in a pallet, and then in a truck. Truck's just a container with wheels, right? It's a big box. So that's one thing. And then, oh yeah, well, you know, the first time I drew this slide, I felt really proud of it, that I'd figured this out. And then I realized, oh wait, I'm the beginner. I went and looked at that textbook I mentioned earlier, and sure enough, I wasn't the first one to figure that out, that that's what was happening. Here's a similar chart that's in that book. And then down there, they cite a Navy, Department of the Navy document that has a similar chart, which is, instead of a mint, they're using a paperclip. So that turns out to be my intellectual contribution to this, is to have a mint instead of a paperclip. Anyway, so that's a central part of logistics, is this succession of containers. So let's follow the journey of the mint. Okay, you start out in the factory. In the factory, they put the mint in a roll, the roll in a box, the box in a case, et cetera, till it gets on a truck. Now the truck, let's say it goes to a distribution center, DC1. And what happens there is they take the pallet off of the truck. Maybe they take the case off of the pallet, and they're going to put the case on a different pallet. And so that's part of the sorting process, right? The cases on the original pallet get distributed to other pallets. That's sorting. And then those pallets get put in the or the cases get put on the pallet, pallets get put in the truck. Maybe the truck then goes to a second DC where a similar thing happens. But let's say now the next truck is going to go to the store. Sometimes the trucks are loaded with cases without the pallet there as the intermediate stage. So let's say that happens here. So the case is loaded onto the truck. Truck goes to the store, case is loaded off of the truck. You can see my cursor. So we're right here in this process. Oh, wait, here. Can you see my cursor? I guess so. Anyway, so we're here. Thanks. And so somebody at the store takes the case off of the truck at the loading dock, and they break it open, and they take a box, and well, several boxes, and they distribute those boxes to different, close to the register, right? So they're sorting it and putting it there at the register. And at that point, the consumer comes along and you pick the roll out of the box, and then later on you pick the mint out of the roll. So that's the whole journey, right? And everything here, it's all, you know, putting or picking. People don't always use the words this way, but basically it's the same thing happening over again, over and over. It's picking, putting, and sometimes sorting there in between. And this is actually oversimplified. There's lots more picking and putting going on. So as an exercise, for example, think about the process of getting it checked out, getting it bagged, getting it in the cart, getting it into your car, getting it, you know, all of that. Actually, you could add that to this chart if you wanted to. So it's all about picking and putting and sorting. Now, there are some iconic manipulation challenges associated with picking and putting, and they have names. So, you know, humans we're all experts at manipulation. And even though we kind of don't think that much consciously about it, or we don't talk that much about it, maybe, I don't know, but still we have iconic names for these problems. So if somebody is talking about the nested container problem, they'll say, you know, it's like Russian dolls. Or if you're having trouble getting something out of a tightly packed array, they'll say, you know, it's like, you know, getting the first cigar out of the cigar box. These are the iconic names that we have for these challenges. It's all about clutter, okay? And this is the worst kind of clutter that you can have. Something is so tightly packed, there's no room to fit your fingers. Or something that's even worse than that, packed, you know, in smaller and smaller containers. So there's actually no access at all to the item you want until after you've picked and disassembled several other items. So these are challenges that are familiar to us, but they're particularly prominent. They're prominent. You know, logistics has both of them sort of nested together. Well, so let's look at picking and putting in particular. And when I first made this slide, I thought, well, let's see, here's the easy case. But even this isn't easy. With this sort of iconic drawing of it, it looks easy, but this is essentially what you have if the hand was designed for the object. And that's what happens in some manufacturing applications. Every gripper will be designed for one specific object it's picking up. And in that case, the gripping process itself can be easy. But in general, it's hard. And you know, this has been a significant part of robotics research for the last 30, 40 years, is how to grasp even a single object in the absence of clutter, even a singulated object. So now when people were interested in clutter, like me, and you know, they started saying, well, you know, let's look at a high clutter situation. Let's look at random bin picking. So here's a, you know, a heterogeneous bunch of objects randomly assorted in a bin, a much harder grasping problem. I used to think of this as a high clutter situation. But, you know, this is one of the things I realized after getting into logistics, that's only intermediate in difficulty. Here's the real problem. And this is very common in logistics because you want everything to be densely packed for efficiency and storage, and so that you get the maximum amortization of cost in the ride sharing. You want dense packing of things. And so it's the cigar boxes, and I'm not showing it here, but it's also the Russian dolls. Right? Both of those things are very common in logistics. So that's the picking problem that we have to deal with. I'm going to show you a couple of examples of Berkshire Gray's picking. This one I'm particularly proud of. So we're using a lot of vacuum. But if you're familiar with vacuum, you'll be surprised at what we can do. So picking bags, for example, is generally difficult because bags wrinkle and the wrinkles let in air. But we're not having problems with that. This seam, you see that the seam between the baseball and the box? That seam lets in air. So we don't have to have a good seal. And obviously that bath sponge would be completely out of the question for most vacuum gripping systems. So there's some magic going on here that was developed at Berkshire Gray that I can't go to in any detail, but we're picking a huge assortment of items using that system. Let me talk about pudding then, the opposite. So of course, pudding's easier. It's just picking backwards in time, except gravity now is on your side. Okay, so pudding, in this case now, really, I think it is fair to call it easy, as long as we're not talking about an egg, as long as we're not talking about something that has to be placed carefully, either because maybe it can be damaged. So it can be easy if you're just like dropping a coin into a box or something, but it can be hard if we're talking about packing an egg. Bin picking, sometimes it's still pretty easy. A lot of the demos that you see in logistics are bin-to-bin transfers, and they can be very easy. But then, when density is an issue, as it often is in logistics, then you get this situation, and the difficulty there is just insane. Why can humans do this? How do humans do it? Well, think about how you would get like the first CD out of a CD case or the first cigar out of a cigar box, right? You'll stick your finger in there and you'll wiggle it, and you're actually spreading the objects apart, maybe even deforming them, and even deforming your finger. And the material in your finger and the structure of your finger matters. And you're using your vision, you're using your intelligence. Okay, there's an awful lot going on there. If you want to see how hard it is for a robot, you should get one of those toy grippers and try and do it with one of those, and you'll get a taste of how challenging it is. It's ridiculously hard. But naturally, I'm going to show you some videos of BG doing some good placing. Actually, this was similar. We saw a lady in an Ocado video doing some packing of groceries into bags. So this is similar. You'll see that it pauses in the middle and it takes a snapshot. And that's not to identify the object. It knows what the object is. That's so that it can get a better estimate of the object's pose in the hand. So pose in hand slows down the operation a little bit, but it gives us enough information that it can then get it into the bag and place it in a point in the bag where you'll be able to pack the bag more full. Yeah. And let's see. Yeah, here's another one. This might be the one that's, I think, actually done in our facility, although it has been installed in customers' facilities. But this is the one video that is taken at Berkshire Gray. What you saw there was it was packing things more densely, okay, and it placed it very carefully. So it did the pose in hand vision, and then it placed that object very carefully and without a lot of clearance. So there's an example of what a robot can do. Sorting, it's not that interesting, right? Just sorting, you pick and you put, but in between there's some discretionary transportation. But I'm going to show you a video. So this is, again, installed in a customer's facility. So you see those same linear sort wings, those same shuttles that we saw in the FedEx video. This is inventory coming in. Now, this is not FedEx, this is store replenishment. So if you have a retail store, when you run out of a certain item or when you've sold an item, you want to replenish it. So you call up your local distribution center and they fulfill the order for you. So it's like e-commerce, except it's within the store chain instead of for the consumer. So every one of those bins is a different store, and the robot's picking these things, putting it in the shuttle. The shuttle's carrying it to the correct store. And there's 4 of these systems running in parallel together in this facility. Now, Berkshire Grey did all of this. The bins, the conveyors, the caps on top of those bins, and the things they're riding on. An empty cardboard box doesn't travel on conveyors very well. And those flaps have to be controlled. And there are issues with getting the box full enough without overflowing, and that the caps can help with. So there's an awful lot going on here, right, that we have no time to talk about. So yeah, we're building the whole systems, and that was part of Wagner's initial vision. It was not to build a robot or to build a gripper or to build motion planning software. He had the idea we were going to build the whole thing. And as an analogy, let's suppose that robotics advanced to the point where we could automate a horse, which it pretty much has, right? Big dog, I don't know if it can pull a carriage or not, but we've pretty much gotten there. So somebody might say, hey, isn't that great? We could take a horse and carriage, and we can now replace the horse with a robot horse, and we'll have a horseless carriage. We could call it an automobile. But Henry Ford had the holistic view, right? He didn't ask, how can I replace that horse with a machine? He asked, how can I build a machine, the whole system? What's the best way? Because if you're just looking at one component, you can't get as much value, right? If you're looking at the whole system, now you can rearrange how stuff comes to the robot and how stuff leaves the robot. You can change the statistics of how all of the stuff flows through the factory or through the warehouse in order to get the maximum value out of the robot. And so it gives you a level of control. You can get much more value out of the system when you can do that. So that's why I'm showing you whole systems. That's why Berkshire Grey is working on whole systems. This is one more. I think this is the last one I'm going to show. Might be one more. Oh yeah, there's 2 videos about this system. So this is a case where instead of those shuttles, we're using mobile robots. One thing you're not seeing here is the mass storage, okay, the bulk storage. This is like cache storage. Off to the side, there is a big automated search and retrieval system that is storing things long term. When it's a store replenishment system, the store calls in their order. Just like the last system we looked at, the robots are picking from inventory bins into store bins, and then those bins are going to get loaded onto carts, and those carts get loaded onto the truck, and it goes to the store. Now, one advantage of this is that those carts are loaded in an aisle-ready order. So when the cart comes off the truck, it goes straight to the correct aisle. And then a worker in the store can move that cart up the aisle, and the objects will be on that cart in the correct order, matching the order on the aisle. So this system knows how your store is organized, and it's putting the stuff in the carts to optimize unloading the truck. And that means in this case, the trucks, forget the exact numbers, it used to take this company like 9 hours to unload a truck on their loading dock. Right, they're taking stuff off, it's going into the back of the store, it's all mixed up, they have to sort it out and everything. Now they just take it straight to the aisle, and they're unloading the truck in order of magnitude faster. So that's the FlexBot, Flex Field system. You can see the automated systems both for taking stuff off of the field and putting it on the field. And here's one last video. This one has music, which you're not going to hear, which is just fine, I guess. This is to show off some of the capabilities of the most recent generation of the FlexBots. That's what we're calling them. Before we were just carrying bins and cases, but now we're carrying single items. In the warehouse business, sometimes if there's an item that doesn't fit in a case, sometimes it's called a big ugly, something that's hard to handle. And here we're showing that these flex bots can handle a wide variety of things, whether they're in a case or not. So a very flexible system, highly modular, scalable, huge fleets of mobile robots being coordinated. And I think that was the last video. I had a few things to say, sort of implications for robotics research. So when I was just an academic, when I was just interested in the research side, I was still spending a lot of time in factories because there's an awful lot to learn about manipulation from the commercial applications of it in factory automation. The same should be true in logistics. And I think it is. Most of what I showed you, new ideas about clutter and new ways of looking at manipulation really grew out of my experience at Berkshire Gray. It raises the question of, how significant is logistics as an application area for robotics research, for advancing the ideas and the technology? And I think it's actually going to be as important or maybe more important than automated manufacturing. One thing the two fields have in common is the very short path from a research result to a commercial impact. And why is that? It's because the robots are already there. They're already doing the work. So in a factory, if you make some small improvement in an algorithm, in the software, or a slightly better finger shape, small changes sometimes can be deployed immediately. And that can happen in logistics too. That's not going to happen in the robot butler industry, right? A little improvement in robot butlering is not going to make it to market until somebody has made a really, really huge advance in robot butlering. So that's important. And I think I've already said this. You get a different perspective, new ideas. It's certainly been working that way for me. One last question that comes up is, will there be funding? There is some, and there is some prospect for military funding too. Less of an issue in Canada, but definitely an issue in the US because the military does care about logistics in a big way. And anything we can do that makes logistics more flexible there is they're going to like. There's also prospects for private and other types of public funding for the research. So I think the odds are good that it's going to have a big impact. If you want to learn more, the September issue of Material Handling had some information, and of course you can find stuff on our website, including, I can't remember, did I mention this? That very first video we saw at the FedEx facility, that same type of system is involved in a partnership with a collaboration with SIVA and installations in Vancouver. So we do have some operations in Canada as well. Anyway, and there's an article out there that you can find discussing that connection with SIVA Logistics. One last video to go out with a bang. I don't even remember what it is. Well, you can't hear the music. I could sing it for you. Okay, I'll stop. Sorry. I see there is no reaction icon for, oh my God, please stop singing. Too bad.
I think clearly this was very well done. All of us really loved it. And I think the effortlessness with which you say these things is just marvelous. I think broadly, Berkshire Gray has done so much nice stuff, it seems. But a lot of it, of course, you don't see every day. And then this really helps inform What sort of problems should we be working on? What sort of problems will emerge? So I think this definitely leads us very, very nicely into the next session, which hopefully you can be part of for the panel.
Oh, yeah.
We'll have all of our speakers, so all of our viewers, we'll move to the panel. We'll take a few minutes of break. Our administrators will move all of us to the panel. All of our speakers, you will be put on the panel. All of you will be visible to all of our speakers. And once we move there, I will explain how the process will work for Q&A and interaction. That would be much more interactive from an audience's perspective. I did.
We each have our microphones.
Yes, I think it was designed in a way so that it would work out that way.
If this were a real panel, I could try and whisper jokes to the guy next to me, trying to.
We need that functionality for sure.
I want to be next to Matt for the jokes. Also, that singing was fantastic. I would just like to say that I had sound in my talk. I didn't know that it didn't come up through, so I had this little like dance music thing, and I was going to start singing to myself in the background, thinking no one could hear me, but I should have. My mistake. My mistake. Now I know. Now it's too late. It's too late.
So for audience,
I'm sorry to let you know, I've had a bit of a diary mix-up. I thought this was broken into 2 sections of 30 minutes, and I was in the first 30. I have to do after 1:30, I'm afraid.
I think that'll be fine. Don't worry. Thank you very much, Alex, to be able to join us, and it's okay for however long you can be here.
Sorry.
We can get started sooner since Alex has to leave. But for our audience members here, there are 2 ways to ask questions. You can ask a question directly into the box with your name or anonymously, or you can queue up in the boxes below. Let me give you an example. And then, as a moderator, I will bring you on for questions. You can turn your video on if you so please. You can just turn your audio on. It's up to you. Definitely, we hope to make this as interactive as possible, and I'll try to keep track of who came first to keep track of a queue. Okay. Aiden, can you move me back? Yes. So before we take audience questions, there are questions we did provide our speakers, which we'll start with, and we'll very likely move to audience questions relatively soon, in about halfway past. So I think what Matt was mentioning, this idea that logistics is increasingly growing as a potential field of research within the space of robot manipulation. I think I would like to start with our academics on the panel to ask this question. What do you think are problem spaces where robotics can provide most value in manufacturing and retail over the next 5 to 10 years? Let's start with you, Angela.
Honestly, I think this is a question where I'm not sure if the academics are the best to answer this. I think it's an answer that needs to come in a close, from a close conversation with industry to understand where actually the value, where robotics can provide the best value for, for the least work. So what do we have right now that can already have an impact? And I think there's a lot there already. And so, yeah, I'd love to hear from industry about what the answers are.
Actually, we have planned for that. I think this is supposed to be a question to elicit understanding of what academics believe are the problems versus what Matt and Alex believe are problems. And I think we want to get that juxtaposition. maybe Jonathan has a comment.
Yeah, I mean, I maybe have a comment, I think, just off of Matt's really great talk, which is maybe, again, something that I hadn't thought about very carefully until now. But often in academia, we're concerned with niche, individual tasks in a niche. So I do motion planning as one paper, and then I do grasping as another. And then I very rarely couple all of those things together into a complete system that is able to do some end-to-end task. I don't mean an end-to-end in the learning sense. I mean end-to-end in the actual task space. And so and also Alex referred to this too, is that I think maybe one of the key challenges going forward is to actually clearly build systems that are able to not just do one niche thing, but do a whole series of tasks from end to end. And I think as academics, we're maybe not encouraged to do that so much. Like you write a systems paper, and sometimes the systems papers aren't that well received because there's no juicy mathematical component or something, but it's clearly just as important to industry. So that would be my take, I think. It's kind of a cop out also, because I'm saying like I think it's really hard and I'm not sure how to solve it yet. So I just want to do individual niche tasks, 8 pages.
I think if we flip the sides on the table, and we'll come back to you, Igor, as well. I have specific questions for you. Let's say Matt and Alex, what do you consider the biggest opportunities for applications of robotics in your domains? Things that are not yet solved, so definitely not a 1-year horizon, but actually interesting problems that you think are technological problems.
Matt, do you want to go, or do you want to go first? Sorry, how do you?
Okay,
you go. You've only got half an hour.
Well, I mean, Matt, fantastic talk as well. So I think when you were breaking the problem down into kind of handling and moving, that is exactly how I see the challenges in logistics. And there are so many different types of processes that all require different forms of handling. Depalletizing and removing the overwrap that is effectively trash, whilst preserving the important packaging of the items underneath that are basically both cellophane and both transparent, is something that humans are fantastically great at, but trying to teach this to a robot system is really hard. Everything that you were describing in your kind of last couple of slides about the kind of easy to the insane, I definitely see that ultimately for the goal that we want or all need in logistics, it is definitely up at the insane end of the spectrum. Everything, if you lose density, so pick and pack in the warehouse is the most labor intensive, as you highlighted. But actually, if you look at the end-to-end system of logistics, the logistics part tend to be a far bigger labor cost. So in Ocado's UK operations, it's 10% of sales. And so it's really big. If you therefore damage the density of the pack and the number of containers you can put on a logistics vehicle, then that throws all the economic benefit of robotic pick and pack out the window. And so having a really great understanding of the end-to-end optimization. And then when it comes to things like dexterous manipulation, we are really looking for a generalized dexterous manipulation platform. But we start simple, like with suction cup, but it's very clear that suction cup can't do in-hand manipulation, right? Two-handed operation is another thing that is really critical to being able to pack densely and being able to manipulate large items like multi-packs of loo roll or bottles of water. And so the kind of what's great about logistics is it allows for these kind of incremental solutions to be developed and delivered that provide economic payback and value, and provide this kind of great learning opportunity for the academics and roboticists to deliver the next iteration, the next leap forward in capability. But for us, the North Star really is being able to receive items in the warehouse, to do all the processing of the items. So that's decanting, putting into storage containers, as you say, kind of breaking down from the big parts, and then doing everything for packing as densely with the same level of quality and the same speed. Because again, if we pack much less quickly than a human, and a human can pick and pack at about 600 units an hour or more, then we again impact the overall economics of the operation. And so being able to deliver a system that can pick and pack as densely as a human with the same throughput, with all the myriad of items of 60,000 different items that you could imagine, is a phenomenally hard challenge. So coming back to the kind of the references of, pick your topic area for something that is incredibly hard and, you have a job for life. I see that, logistics provides a great domain for deploying this technology and for the collaborations that Ocado has made such great use of out of Horizon 2020 in the past.
So would you like to add anything, Matt? I think this was a pretty comprehensive answer from Alex.
Yeah, I'd forgotten. I thanks for reminding us that you were involved in the Horizon 2020 projects. I think that's really interesting. It makes me want to go back and look at what happened there and see if I can reverse engineer your thinking.
We were careful to redact information to what we published.
It's really interesting to look at similarities and differences between what you guys are doing and what we're doing. But let's see, to the point of the question. I mean, so first off, we saw some work earlier in the workshop that I think answers that question in a certain way. And this is kind of the more obvious thing, which is if you can do something fundamental that addresses, I mean, there are many fundamental problems that we rely on. And if somebody had said to me, should I work on inverse kinematics? I might have said, it's kind of a solved problem. Somebody comes along and says, you know what, you can use, distance geometry. It's like, holy shit, I got to look into that, right? I didn't know about that. That sounds really interesting. And if it works, the breadth of that is ridiculously huge. So that's one thing. Not specifically motivated by logistics, though. So, in my mind, at least for myself, where logistics has raised my level of consciousness is thinking about clutter, right? I used to think that random bin picking was the high clutter thing. And I'm now embarrassed to say I probably have papers out there describing it as a high clutter thing. And now I'm like, I had not looked inside of a truck. If I had, I would realize that is not a high clutter situation.
I think that helps. Maybe a different spin to the question, and this is for all of you. So I think this was an open-ended question, but if you were to make this question slightly more, let's say, fixed, how would you say the opportunities would exist on, let's say, a 3-year horizon versus, let's say, a 7 to 10-year horizon? Something that is, let's say, executable to a product, and something that is open-ended. 10-year, I'm of course picking up the random number. It could be 15, and specific examples here would help. Thinking about like things that, or at least the way you guys bin these problems. This is a problem that is solvable, while this is open-ended or blue sky. Let's start with Igor.
Yeah. So for navigation, it's actually a very interesting question. And since I started collaborating with you, Animesh, also on topics related to manipulation, I noticed for every problem we have in navigation, there is, under a slightly different spin, a counterpart in manipulation. And differentiating between the 3 and 7 year horizon, I would say, for navigation, to me, it feels the more structured the environments are, the easier we can modify the infrastructure, the more we can have products there. And there are already products going for such environments. The cost can be reduced. And for example, some of the ideas for Angela are great in that direction. And this is something that we can, I think, definitely develop in a shorter scale and then improve upon. And on a longer scale, we want to reduce assumptions. And again, for navigation, reducing assumptions is assumptions about infrastructure, assumptions about quality of the environment, and so on. And to me, it feels like for manipulation, it's similar. It's like reducing assumptions about clutter, reducing assumptions about how the objects are structured, how fragile they can be, and so on. And Matt, I was really excited to see about the abilities that we have already. So I'm curious about hearing what actually the great challenges are for in the logistics space that you think we cannot solve it ourselves. We would actually need some basic research where researchers come and help us solve this particular logistics challenge.
Angela?
Yeah, thanks, Igor. I think I agree with what you say about structured and unstructured environments. I think in my head, I put it differently in terms of how specialized are our solutions. I think the long horizon is if we could build systems that can quickly be deployed in non-specialized areas. And that would also help level the playing field a little bit, right? That not only huge logistics companies can use robotics. And I think that's the long game. I think in the short term, in those structured environments, we can see which tasks are not yet automated, and can we just get a little step further on those, right? I think we saw that at Ocado and Berkshire. Like, okay, can we now do the simple grasps, and now a little bit more difficult, I do think so that it's also systems challenge, right? We don't necessarily want to do it exactly as the humans do it, or just to replace the human where the human works right now. That may not work. Maybe we need different packaging solutions, different size standards, or I'm not sure. And I think, again, for this shorter horizon, I think a very good conversation between research and industry is really helpful, such that researchers can say what is possible, and industry can say where can we save money by doing it in an automated way.
So a follow-up question, and we'll come back to you, Jonathan, as well in a minute, is to both Matt and Alex. Both of you are at this point leading very large organizations, and even, let's say, projects and which projects to invest resources in. In the way Igor and Angela pointed out that maybe structure is a mechanism of evaluating these things. When you come across projects that people in your teams are pitching to you, it's like, hey, Alex, I want to do this. And you have to decide resources. Are there objective, let's say, KPIs or indicators, or even intuition from your experience beyond just like structure that you found in either of your domains that you use to assign what is sort of achievable, while what is, well, it's nice to do, but there is no guarantee any of this will pan out. Maybe we'll start with Matt this time.
Well, I'm not actually a technical manager there, and so I'm not evaluating projects and asking and figuring out where to steer the resources. But let me see if I can transpose your question to. Well, okay, I don't know if this fits or not, but one thing that you see that happens in e-commerce and warehousing is that I don't think there's actually a clean line between order fulfillment and manufacturing. So if somebody says, I want a gift card, okay, fine, the human or the robot throws in a gift card. They say, I want a gift wrap. That's too bad. They just throw in a gift back, right? They don't gift wrap it. It should be gift wrapping, right? You should be able to say, I want a gift wrap, and it comes and it's wrapped. And when you start thinking about it, there's a lot of things that are like that are close to order fulfillment, but involve some assembly, like supplying, let's say, those dinners that get loaded onto airplanes. So I don't know how those are made, but robots could be dishing out the trays and assembling those dinners for airplane catering. So there's lots of examples of those, flower arranging, all kinds of stuff that warehouses have already begun to intrude into those things, and could be, I think, a lot of potential there, and the problems are very interesting.
Okay, so 2 parts of the question, I guess. In terms of the ambition, so we already state to our retailers that we're expecting the next 3 years to be able to pick 50% of their volume by 50% of the range by volume in all of the international warehouses that we build. And so we are already progressing our deployment plans for that. Clearly, it gets asymptotically harder. So, the robots will do the easy stuff, and we will force the humans to do the more and more complicated stuff. And then as the robots will get more advanced with more sophisticated grippers and control, then the robots will do up to 100% is absolutely the North Star goal that we have. And, from receipt in the warehouse to picking and packing and delivery out through the warehouse. Now, when you combine kind of the complexity of the unstructured environments or the end goal The warehouse is a sort of a semi-unstructured environment, both in terms of moving and in terms of the pick and pack. But actually, the pick and pack is a great, if we're talking about gift wrapping, I don't have to gift wrap with robots at the moment, but I do have to provide over wrapping. So if you put bleach next to your chicken, you need to provide, hygiene rules specify you have to overwrap and seal, right? So there's already this level of complexity built into something like a grocery logistics operation, which is really provides a massively interesting place to work. I see industry as being, an area of applied research. And so what I'm looking for when it comes to working with academics is finding that right balance where they can work on very early TRL concepts that we can then take over. Because actually, if I'm honest, working in a commercial organization, it is all about the monetization of intellectual property. And just being an end user doesn't afford the opportunities for success, because, as kind of Angela saying, right, then anyone can come along and disrupt it. So the key, actually, if you're in industry, is to be great at doing applied research and then finding the best academic institutions and professors and groups to kind of do those very long-term horizon projects with, that we can then fold into our roadmap. The hope I have for the future, and recognizing where I am in terms of time, what's amazing at grocery, as opposed to, say, people moving, which is good for autonomous mobility and vehicles, or even kind of the Amazon non-food grocery logistics, is that the basket size is very small and they just kind of toss packages at your front door. So what we have as a proposition is taking the groceries from the back of a logistics vehicle to a person's front door. Now, if you live in a leafy suburb and you've got a driveway, then maybe you as a customer are willing to come out and go and get the groceries from the vehicle. However, my kind of totemic example is a little old frail lady living at the top of an apartment block that only has stairs. Asking her to come back and lift 75 kilos worth of shopping in, maybe 10 bags is kind of unreasonable, is not going to work as a proposition. And so for me, the kind of the long-term embodiment, and really where it gets exciting is a robot which can do that. So that can deal with all the unstructured nature of dealing with everybody's drives, children, pets, vehicles that are being parked, toys strewn around. Everybody's apartment block is going to be different, and that can carry all of those groceries and then hand them and do that doorstep interaction to the customer is kind of where, for me, the kind of the convergence of all the different projects, whether it be sensing, autonomy, autonomy in unstructured environments moving, or generalized dexterous manipulation, all kind of comes together. And then, for me, as a human and member of society and wanting societal good, the idea of assisted living robots, agriculture is really the goal, the end goal for these sorts of technologies, and why Ocado invests not only in grocery logistics, but vertical farming and any kind of other adjacent domain that we can to help accelerate the development of this capability. Each time looking for these great use cases which provide an additional stepping stone, like adding layers of strata, which you can combine and build upon through each cycle and each iteration.
I think that's wonderful. I know trying to keep a track of Alex's time, and we do have more questions, but I think I'll take one of the questions from the audience. Rahul Ranjan asks, for a student in robotics who is also interested in entrepreneurship in robotics, how can we find what kind of problems are actually solvable or solved via the state-of-the-art approaches in robotics? So basically, to sort of distill the question, I want to do a startup. How should I figure out what problem should I be solving? At what point in publication cycle would this be considered solved? Maybe Alex and Matt can go first, and then we can have Igor, Jonathan, and Angela pitch in.
That's probably I'm the least one to work on that one. I've worked in a startup, but not created my own startup, and so I'm afraid I'm always where I add value is in understanding the benefit of other people's amazing and inventive ideas and finding out how I can stitch them all in to the roadmap that we have. But I think you have to have insight in an idea and a use case, and probably some real world experience helps. And then obviously some deep understanding in some facet of the technology that can help solve whatever that domain is. So we're about to work with a company, or we have done some work with a company and looking at working with them more closely in sensing skin, right? So at the moment, most people, robotics classically has been position controlled, and then maybe some visual servoing. What really we think is it's all about force control. And I saw a great paper a few years ago from a lady called Professor Catherine Kuchenbaker from Penn, who injected a human hand with local anesthetic, told them to light a box of matches. They can't. It shows you that this is not at all to do with visual servoing. It's all about touch and sensing. And so that really fine-grained motion control at the point you're packing densely, it's not a visual servoing problem, it's a force control problem. And it's not just force in the hand or the fingers, it's force all the way up the body and the arm. And so, skin, right? The kind of sensing that we need is definitely an advancement we don't have at the moment. And so all the time I'm looking for the individual Lego blocks that can help build, contribute to the building of this amazing capability.
Maybe let me intervene and rephrase the question to Matt. This is very similar. So around 2017, 2016, there was a proliferation of research outcomes which were showing that picking without knowing the object was sort of doable, whether with a two-finger gripper, sometimes with a suction gripper. And since then, if you notice, there has been sort of a proliferation of number of, let's say, for-profit enterprise that is built around the core technology of picking. You started this, or your epiphany happened on May 6th, 2013 or 14, I believe. So this was a few years ahead of those results. What information did you have in 2015 that told you this is going to happen for sure?
Well, it wasn't. The success of the systems wasn't dependent on those. I've got a phone going here; it's driving me crazy. Was not dependent on that work, obviously. So we had a certain level of performance, which was good enough. We are using deep learning in our vision systems, I hear. Well, not just the vision systems, we're using learning in a lot of things.
No.
I think it's a scam. No. Let's vote. How many people think I should pick this up? I'm going to mute myself and figure out this problem.
No worries. In the meantime, I think I would love to hear from Jonathan. What do you think? How should a potential sort of new student pick up a problem? When do you think is that sort of ready for game time?
Well, that's a very difficult question, I think. Well, I think from a research standpoint, it's maybe easier to pick a problem that is unsolved based on the literature you've read to date. Now, the tricky question is whether solving that problem is actually relevant to industry, because there are a lot of cases where you pick something that you think looks good and hard, and then you realize, oh, actually, there's a different solution, even a heuristic solution, right, that just works 99 times out of 100, costs 1/5, and is just better in many respects. So I think it's hard. I think part of it is actually maybe just events like this, right, and us as professors going out and trying to actually visit warehouses and logistics centers and just understanding what the challenges are, right? And I think without doing that, maybe we don't do that enough, which is, we're sort of guilty of maybe walling ourselves off and knowing, as I said, that these niches can be tackled individually, and whether it's relevant or not is maybe up for debate. So maybe the key is as a student to get out and just either with yourself or other people, just try and visit centers where this type of technology is used and just ask, what can't you do today? Is the transparency really the key issue? If you could solve that, would you improve your output by 10%? That's a huge game changer, I imagine. So yeah, that would be my suggestion. Although that's hard to do, but worthwhile, I think.
We will continue this riveting discussion. I do want to say thank you very much, Alex, for sticking around, and thank you very much for your input.
Well, no, thank you very much. It's been an absolute pleasure speaking today. I will happily, if anyone wants to contact me, they are very welcome to do so. And thank you very much.
Ooh, fancy. So we can go from 5 to 4. Nice. So I think a follow-up question, a follow-up line of questions actually is this. So this is something that is potentially for all of you, because all of you at least started your careers as academics. There is this sort of cited example in academia that you want to work on something that we call 0 to 1, make something possible that was not possible before, while industry is chasing the 99.xx% metrics of performance, and the xx you can put however many nines you want depending on the domain and the use case kind of argument, right? Which is basically one way of saying that there is sort of a divide between the sort of problems you should be working on in academia versus in research. I do want to point out that in the last 5 to 7 years, research, particularly in certain domains, let's say machine learning, computer vision, natural language, has actually been taken up in industry almost at the same rate or even faster than in academia. And it's not to say that they're not creating products. Yeah, they are doing open-ended research, but they are equally fast sort of converting these ideas into technical products. So first of all, do you believe this sort of divide exists in robotics? And if so, are there mechanisms to bridge this divide? I find this thinking to be slightly, it creates a divide that is not very healthy. It paints industry with a negative brush. So maybe let's start with Igor. I'll sort of randomize the order myself.
Yeah, I mean, I actually absolutely agree. I think this divide that does not exist, or at least it should not exist. When you do robotics, the nice thing is you actually have to solve a big bunch of the technical problems that people also have to solve if they want to build an actual robotics product. So the problems that you're solving and the experiences that you're gaining, they are very, very interesting. And in robotics, you often see the situation that's similar actually to ML and computer vision, that a lot of what is developed within robotics research gets to be used in actual products. Sometimes the products are in different subfields as we expected, like the number of roboticists working on autonomous cars only recently became relatively big. Originally, it was more a niche within robotics research. So this we are not always necessarily good at predicting, but I think the skill sets that we are providing to our students, they can be useful independent whether they focus their PhD on exactly the application they end up doing once they graduate.
That's useful. Angela, do you want to weigh in?
I have one thought about this. I think we should move closer. On the one hand, from an academic perspective, there have been efforts in the community, and I think we should continue those, that we value people who build robots that, full robots that do tasks, so the systems part of it, and actually solve problems. I mean, maybe not at the industry standard, but I think we should, make it possible to publish this work and present this work and value the effort that goes in, which is huge. And then on the other hand, I think on the industry side, we can also come closer to academia by saying maybe we don't need 99.9%. Right? Because then, we have heard it from Ocado, but maybe the human can step in the other times, right? Or supervise and provide additional training data for those cases. And maybe there's already a lot of benefit, and some more traditional automation companies can think, may see value in that part. So I think we can move on both ends to come closer together.
That's nice. Matt?
Yeah, I think we've all spent time wondering why sometimes the transition is quick and easy, and sometimes it seems to be impossible. I think maybe robotics it kind of hampers itself because we are inspired by what people can do. And so a lot of times the research aims for problems that are, show that inspiration, and without worrying too much about whether that level of performance, that kind of performance, is available within even 100 or who knows 500 years. But that's also one of the great things about robotics, right? Is the connection to ourselves and to what humans do. So I would say, I mean, robotics needs to have both sides, and I think that is true. Maybe that's was said already. It's true even of individuals, right? I think it makes sense to be to take the inspiration, the biological inspiration and the human inspiration, and the inspiration from visiting factories or warehouses at the same time, and look for insights and sort of in that intersection.
That's useful. John, do you want to add something?
Oh, I think I would just echo what everyone said before, and also, I mean, that's easy, but also I would say, maybe there is a divide now that shouldn't exist, or we have to be cognizant of. I would say, I think our job in academia generally is to look beyond 3 years to maybe 5, 8 years, 10 years out, and hopefully come up with newer solutions that will eventually make their way down the pipeline and become cost effective, et cetera. But the danger with that division is that we then lose sight of what is going to be practical and valuable. Right? So I think we just need to do a better job, particularly in robotics specifically, of creating that dialogue between industry and academia. Otherwise, we run the risk of working on things that are novel in their own right, but will never make it into a product. And we ultimately, I think, all want to do things that make the world better, faster, easier for everyone. So yeah, I would say I'm clearly thinking myself today that talking more is key. Yeah.
Nice. There's one question that has been in the queue from our audience for some time, and I think you did touch on it, Matt, which was how much deep learning is actually used at Berkshire Grey? Particularly, could you comment on it? How much of it is used for computer vision versus deep RL for control, or is it useful at all? And
yeah, I've said about all I can say.
Okay, I think that's fine.
We use it. It's good stuff.
Yeah, I think it is good stuff. Maybe a more open-ended question. So Nicholas has been waiting for a question, so I'm going to unmute you so that you can go ahead and ask your question, Nicholas.
Excellent. Thank you very much. And I just want to say excellent presentations, and I really, really enjoyed them. I'm very curious as to what your take is on for collaborative robots for logistical purposes. So sort of similar, I guess, to Rethink Robotics, what they've done with like the Baxter robot. Do you think there are opportunities to apply that sort of technology to logistics going forward?
Anybody want to jump?
Whoever wants to take a first shot.
Sure. I mean, I'll comment briefly.
Okay.
I think that
Go ahead.
I mean, collaborative robots, I think, are potentially game changing, primarily because they're even in the. I mean, so for the logistics domain, absolutely. If there are things that need to be transported or moved, if you can cut down on the before you can do it end to end with an entirely robotic system, if you can cut down on ergonomic or repetitive strain type injuries of workers by having a robot there, then I think there are huge opportunities. And actually, Alex's video had a great example of a collaborative transport application where I think that's ideal and exactly where we want to go. But there's a challenge which I think Angela can speak to, so I'll probably hand it off to her. Safety. How do you make sure? Yes, you can do. I think Rethink had the right idea with Baxter, right? Make it compliant, spring-loaded, lightweight, but it's still challenging, I think, to make sure that you're trying to save the worker from a repetitive strain or some type of ergonomic injury in the interim. You don't want to bash them over the head with the robot, and that's hard. So I think guaranteeing safety is what makes it still a difficult challenge.
I can jump in. I agree, and we have looked at how we can guarantee safety in uncertain environments. Encourage you to look at that work. I would like to make collaborative robots much broader than what people usually think it is, because in all these systems, lots of automated systems or robots collaborate together, and there is always a human interface somewhere already, right? So I think I'd love to kind of go beyond the typical idea where, a robot carries something with a human to better reflect the fact that robots are never operating alone. There are always humans around, and there's always an interface, and there are always multiple systems interacting. And I think that makes it interesting. And I do think there's completely different roles for humans in these settings. For example, that human observes failure cases of the robot and provides additional training data or additional demonstrations. And so, or even purely teleoperation that eventually could lead to automation over time. So I think there's very interesting aspects that are not the typical thing that people envision when they talk about collaborative robots.
Yeah, I mean, I absolutely agree with that. And actually, the things that people typically envision when they talk about collaborative robots are often robots where the collaboration is the furthest out, like just having one armed robot work directly next to a human is something that is, in my opinion, very hard to motivate, because space is usually not that big of a limiting issue. So they can be placed far enough apart. But there are so many other types of collaboration, and I think teleoperation was one of the best examples where robots still do some tasks autonomously. It's much more closer to what will happen in products, but still super interesting research problems there.
So a follow-up question here is also sort of like something that Matt earlier mentioned is what is the relationship between what you guys call structure or clutter? Is clutter and density not just related? Is clutter just high density, or is something special about clutter? How do you define structure? I know this word came up multiple times in different contexts, but what is structure? Is neatly folded clothes structure? I don't suppose neatly folded clothes are any easier to handle, or just stuff thrown into a sink is clutter. Matt, maybe you said a very interesting thing, back of the truck.
I used to worry about the definition of structure quite a bit. And there's even a paper out there somewhere with reporting what I found out. I spent a lot of time searching through old papers trying to find out when did people first start worrying about it and who defined it. And it's almost never defined. And some of the definitions are completely contrary to what you might imagine. I mean, they're even contradictory. A NASA workshop, for example, saying that space is, or structure, I was saying clutter, but structure, I'm talking about structure. So, NASA is saying that space is perfectly structured or perfectly unstructured, depending on which publication you look at. I mean, the definition I know, and I think is most common, is it just has to do with whether an engineer has access to the environment as well as the agent, as well as the robot. Then you can engineer the environment to make the robot's job easier. But when things get weird is when people say, well, the kitchen's unstructured because the robot engineer doesn't get to engineer the environment. Well, no, but the people who design the environment for the human, right, for that agent, certainly did. And it's amazing, you know, how much similarity there is from one kitchen to another, right? The counter height's probably very, you know, very little, and the depths of the cabinets and the hardware, and, you know, on and on and on. So calling it an unstructured environment, I think, should always, you know, there should be an asterisk. I've wondered if there's a way to associate a metric, and it seems like it should have something to do with information theory, and outside of a few sort of fun conversations, never gotten anywhere with it. So structure, yeah, it's interesting. But what was the question again? Sorry, you just got me into that rut.
I think
What was the question?
essentially, the question was essentially this: what is clutter? What do you mean by clutter? What do you mean by structure? And
I see,
what you
yeah.
seem to appear to say is that it's not clear. It's something that people intuitively believe, but it's not not very mathematically defined, or it's not an objective that you can operate on.
I would say, I'll say one more thing and then I'll shut up. An awful lot of the time it comes up motivated by people who are trying to sell, who are making a pitch, trying to sell a project and trying to explain the limitations of robots relative to humans. And that kind of, I would say, dominates the discussion of it. I don't know if that's helpful or not. I'm shutting up now.
That makes sense. Anyone else care to weigh in? Angela? Oh, John, go ahead, please.
I might weigh in just quickly. I think Matt's exactly right. If I had to define structure, just thinking about, I'm not going to come up with a rigorous definition, but I think Matt's exactly right. It should be quantified in terms of some kind of information theoretic measure. And I think it's really predictability. So if I have structure, then I'm able to, if I know the bins are always filled with one item only, then there is no clutter by definition, because I'm guaranteed 100% in advance that they're always going to have just one item of a particular type. Then I would say the entropy is, you know, very low. Well, low, and I can predict, right? I can predict what action I should take, even blindly, because I don't need to worry about situations that are a myriad of possibilities, right? So that would be my guess, but that's far from rigorous. I'm
so tempted to weigh in, because I was like,
oh, you should. Sure.
A box of simple bottles versus a box of paper clips.
Yes, I would.
You can have a box of paper clips. All of them are paper clips, and yep. I don't know of a robot yet that would be very good at this yet. Maybe one of the good suction cup robots that Matt showed us might work. And of course, I'm making up this as an example that you could have object shapes which you are told in advance is just 1,000 of them, but still it's just not sure how to handle them.
Oh, but I think the paperclip example is the perfect one, because you have a bunch of paper clips and they're in a container, but they're random. They're randomly oriented, they're randomly placed, whereas a box of bottles has the bottles all upright, potentially, hopefully, in the same, right? So I think you could actually, I mean, I don't know how you would define a metric on that, but maybe. The only other thing I want to say, I'm sorry, then I will shut up, because I just wanted to go back to the last, go ahead, Animesh, yeah.
I think this has been wonderful. So one of the objectives of this this debate was to also come up with let's say potential concrete solutions. One of the questions that has been sitting, and I'm very anxious to ask this. All of you worked or have worked in ever so slightly different domains where increasingly in the last 5 years the solution was dependent on data. How much of that data came from real robots versus, or real robot first, versus, let's say, simulation? And what is the role of simulation in this pipeline? Just to give you context, autonomous driving is going down the route of simulation, in the sense that there are multiple teams of very smart people trying to just build simulators, because it's clear that the problem of 0 to k% is solvable. It's the long tail that's very hard, and you're not gonna encounter the long tail in the real world. You have to be able to generate it. Would you think that is also a problem in this domain? Maybe let's start with Matt or Igor, whoever wants to go first.
Yeah, I think, I mean, I am excited about simulation and autonomous driving, and we worked on this, but I think it is almost more exciting in manipulation. And the reason for this is, in autonomous driving, we traditionally, at least for the vehicles, know the dynamics somewhat well. And there are also by now somewhat decent pedestrian models. So a big challenge of the simulation in autonomous driving is, on the one hand, simulating perception, and on the other hand, simulating and predicting behavior. Now, if we go to the realm of manipulation, or particularly if manipulation involves also environments where humans interact, we get this third component of getting the physics right. And for one individual object, it may not be hard, but like for a big variety of objects that we want to be able to cope, some of which are deformable, I can imagine this to be a very like exciting space that adds like a new layer of complexity. And of course, I believe in it being commercially very relevant, because if you deploy robots, you need some sort of testing pipelines, and you need data generation pipelines, and both require simulation.
Angela?
First, we have to say that simulation has always been part of any engineering process. And I guess the reason being for first testing, or even proving performance, and then fine-tuning, and trying out different parameters that are much harder to do in a hardware setting. In terms of the role of simulation in the future, I started working with machine learning exactly at the point when our simulations failed. Like, okay, it would work all perfectly in our simulation, and our simulation was, pretty accurate for most tasks. But it failed in these challenging tasks because the simulation was not accurate. We didn't detect the issues of our controllers in the simulation, and we only saw it in the real world. And so I think there's a place for both, and there will be, I think, the real data will always be better than simulation data, but it's much harder to get. So the question is, how far can simulation data get you, such that you need as little real data as possible? That's one take, I guess.
Matt, do you want to add something?
I agree with Angela's points. Yeah, just in terms of ordinary engineering, simulation is very important in many ways. I guess the question is, can simulation supply all the data we need to learn everything we want to learn? It's been a mystery to me why it hasn't worked better. You see systems like, going back to M.O. Todorov and colleagues that built the walking machine in simulation that also did manipulation. And it was amazing to me what they were able to do with that machine. And I looked at the plans looked great. And, but getting that stuff to work in the real world turned out to be a huge challenge. And I still just want to look at those plans and think, I don't get it. They look great. What is the nature of that gap? I don't really understand.
That's reasonable. I think we can come back to that. We have 3 minutes to go. Jonathan?
Oh, I would just say that I think simulation will, it's up and coming, I think, in the manipulation domain. I think the main challenge right now is the physics of contact modeling, and that's what we're really good. I think Igor pointed out rightly that simulation of self-driving vehicles is good because we understand quite well the dynamics of a vehicle on a road, and also can model what pedestrians will do. But I think picking up a stuffed animal with a gripper, that's a very challenging task to simulate with any kind of fidelity or accuracy for now. But I think we'll fix it, yeah, in time, with as the GPUs get better, as they say.
So we have 2 minutes to go, and I want to ask a pointed, perhaps a short answer question. Hopefully it will be short answer. There were a number of problems discussed by Matt and Alex about potentially both on a 3 or 7 or even a 10-year horizon. And from, let's say I'm simulating being an industry person, often I would like to see in a research paper an experiment that I somehow can relate to, right? So somehow I can ground that experiment into my problem. If you can do that, then there is a good chance I might even reach out and everything. So then, and this is a question for all of you, do you think about designing your experiments such that that happens? In a sense that, do you think about designing experiments that will appeal to a practitioner rather than any other objective? And let's start sort of in my order of operation. We'll start with Igor, Angela, Jonathan, and then last Matt. So Igor.
I mean, I have to admit, I feel I don't think often enough about it, but I think this point is spot on. We should think often about it, because in my past experience, it was exactly as you said. Whenever the experiments that we had in the paper had a practical relevance, there were actually people calling and asking, can you do this for me? And what is interesting, when they call, they actually ask some very interesting questions. What they want is often slightly different. And this slight difference sometimes has the core for very interesting new research problems, because sometimes it's actually not possible, and then things get interesting.
Angela?
I think experimental demonstrations are extremely important to inspire people to think about how that technology can be used in their use case. But I'm not sure how close they have to be. Like in my PhD, I did dancing flying robots, and people looked at them and then they said, oh, can we use that for beer delivery? Can we use that for medical delivery? Can we use this? And they had lots of good ideas. I mean, and then, so I think I really think experimental demonstrations help in showing what the technology can do. If I choose my experimental demonstration for a paper, I choose them in a way that the demonstration satisfies the assumptions I made in my algorithms. And so I think then such that I can demonstrate what I want to demonstrate. And then if that does not yet appeal to industry, that means we made the wrong assumptions for their problem. And I think that happens quite a lot actually in robotics. And so I think then we have to work on more realistic assumptions.
John?
Oh, that's easy. I'll just agree with Angela, because I think that's exactly true. Yeah, and I think we often choose, we pick a niche where we make some assumptions in order to bound the problem such that we can carry out the experiments, and then we find out later that we made the wrong assumptions for industry, but maybe for our goal of getting the work published, maybe not. So
Matt, you get to have the last word.
Well, my first answer to the question was no. I don't think about applications when I'm putting demos together. I think about what's going to appeal to my fellow academics. I guess I'm talking now as an academic rather than as a and or funding sponsors, but those tend to be the same things if you're getting a lot of if you're working with NSF money. So but there are some cases when I've done work that's like we had a screw driving project. Definitely we were in that case wanting to demonstrate that it was of practical value to the to the people, not the sponsors, which was NSF again, but to potential business people. Not that any of them took it up, as far as I know, but sometimes.
I think that's wonderful. With this, I would like to thank all of you for this such an interesting discussion. All of the questions from all the members of the audience were very interesting. I'm sure I can go on for another hour easily, but I want to be respectful for all of your times. Thank you again, Matt. Thanks, Igor, Angela, and John, for doing this. For all of our members in the audience, we will now be moving to the next phase, which would be the student poster presentation.
Thanks for having us.
Hello, everyone. Welcome back, or welcome to a new room. Everyone's here, hopefully. We are going to be starting with poster presentations. Each of the poster presentations will be 2 minutes each. And this is the Ocado Best Poster. All of them will be competing for the Ocado Best Poster Presentation Award. We have 2 judges, James Berkshire. Can we have James in the speaker box? Hi, James. James is the director of AI at Ocado. James completed a PhD in deep learning at University of Montreal with Yoshua Bengio and was one of the first lead authors of Theano Deep Learning Library. He did his postdoctoral work at Harvard with David Cox, where he worked on hyperparameter optimizations, a project that later on became the HyperOpt project. He was also a postdoc at Center for Theoretical Neuroscience at University of Waterloo, where he helped re-architect the Nengo computational system for simulating a large functional spiking brain model. And before Ocado, he was at Kindred as a co-founder, chief science officer, and later as chief technology officer, where he drew all of his I would say, very different threads from his experience to build human-like intelligence in machines, a goal which he still continues to guide his work. Thank you, James, for being a judge here. We also have Morteza Azad as the second judge. Hi, Morteza. Morteza is the lead of adaptive robotics manipulation team under Advanced Technology Department in Ocado. He joined Ocado in 2019 as a robotics research engineer, and before that, he was a lecturer at Computer Science Department in University of Birmingham, UK. He has more than 10 years of experience working in the field of robotics and has published in several top venues. And his main research interests are dynamics and control of robotics, under-actuated robotics, and learning by demonstration in the context of robot manipulation. I'm hoping that both of you will enjoy this, and let's get started with the poster presentations. So instead of me doing one by one, in the interest of time, we will have all of the student speakers appear and share screen one by one, and we'll keep time for 2 minutes. So let's have the first speaker.
So good afternoon, everyone. My name is Xintong Du. Today I'm presenting our work on smooth and efficient task-prioritized model predictive control for sequential mobile manipulation tasks. So there have been increasing interest in using robots to assist humans in professional or in everyday scenarios because of their high economic and social values. However, we haven't seen many service robots deployed in everyday life because they are less efficient and robust than humans, particularly when given a sequence of tasks. They seem to make unnecessary stops during executions. They aren't very reactive to unexpected changes and failures. One underlying reason is that a sequence of high-level tasks are decomposed into a sequence of subtasks, which are planned and controlled separately. For example, for a sequence of pick-and-place tasks, they are decomposed into alternating base and end-effector tasks, which are executed individually by a corresponding planner and controller. So how can we better design the planning and control module so that a mobile manipulator can perform a sequence of tasks smoothly, efficiently, and robustly like humans. We propose the task-prioritized model predictive control method that improves efficiency by considering more than one task at a time. For conflicts among these tasks, we establish a strict hierarchy and use only the extra degree of freedoms of the current task for future tasks. We evaluate our approach in simulation. Here is a simplified pick-and-place example where we have 3 target objects. Baseline approach on the right enforces a full stop between the tasks. In contrast, our proposed approach allows the robot to move towards the next base target while finishing its end effector task. On 120 randomly generated scenarios, our approach achieves an average of 43.5 improvement in execution time. For more information, please check out my poster. Thank you.
That was right on time. Thank you. Next, we have Dylan. Your time starts now.
Okay. Hi, everyone. I'm Dylan Turpin. I work at the Pear Lab with Professor Animesh Garg, and today I'm presenting our RSS 2021 work GIFT, where we considered the problem of teaching robots adaptive tool use with a variety of hand tools. So human tool use is incredibly adaptive. If I tell you to picture a hammer, you probably picture a T-shaped object like this. But if you needed to drive in a nail and you didn't have one of these handy, you could improvise. You could use a rock, you could use a brick, you could use a sturdy ruler. And each of these objects would be better or worse for the task at hand, depending on their shape and material properties. So to learn adaptive tool use, labels aren't actually very useful. If we have a picture of a hammer and a text label that says hammer, there's a lot of missing information there. It doesn't tell you that you can also use this to pry something open or to hook and reach something that you can't quite get to. So instead, we want to learn from interaction experience. And prior work has done this. Prior work has learned self-supervised tool representations from a predict and check loop. The problem with this is that there are a lot of wrong ways to use a hammer. So if you're not bootstrapping from human data, you're going to have to run this loop many, many times to learn anything at all. Instead, we use a predict and adapt loop. So we predict a representation, and instead of executing exactly the corresponding action, we generate the closest successful action and learn from that. At the top right, we have a lot of detail about how we generate interaction experience to learn from, but that's not so important. If you look at our results down here, after training, when we show the system visual observations of new tools it hasn't seen before, it can predict reasonable places to grasp and interact with each tool, depending on the task that needs to be done. So with a slightly smarter training loop, we can learn adaptive tool use from simulated experience without any human labels. I think that's my time. Thank you.
Thanks a lot. We have Mohammed Qudair.
Thank you.
And your time
hello,
starts
everyone.
now.
Thank you. My name is Mohammed Qudair, and I'm presenting work on behalf of my collaborator, Ben Agro, and supervisor, Florian Shkorty. Our motivation for this work is to develop robots that can take a high-level goal and plan out a sequence of steps, along with the low-level motions and configurations that accomplish that goal. For example, here, the goal, the robot is asked to grab the purple block, which is the bottom of this sort of Jenga tower, and automatically has to plan to remove all of the blocks so that it can reach the desired one. So such task and motion planning systems are typically limited to small scenes with a handful of objects. So in this work, we're exploring the idea of allowing them to scale up to larger scenes by learning to predict subsets of objects that should be considered in planning. So in this example shown here, the goal is to stack the blue blocks, and the color of the floating grippers indicates how important our model predicts a grasp to be, with red being the least important and green being the most. So given access to these predictions, a planner can ignore half of the objects on the scene, and so be. So our overall and the resulting plans are analyzed so that objects can be labeled according to whether or not they were relevant to a plan. And our model is then able to read a kind of graph representation of the planning problem and the object it's in question, and score its relevance sort of like on a scale of 0 to 1. And at inference time, a planner can use a sort of priority queue to in order of relevance until a plan can be found. Motion planning problems against sort of a best-in-class domain-independent algorithm, which doesn't learn from experience. And we show that our approach is able to improve performance by over 50% on a benchmark of these challenging TAM problems. In almost all cases, we find that learning from experience can significantly improve planning times and enable planning in scenes with more objects. Thank you.
Next, we have Michael.
Hey everyone. So when most people like you and I go to the grocery store, typically we have our shopping list explore the store. Explore the store while we look for relevant signs, search for the product on the shelves, and we repeat. But not everyone has this luxury. Some may get anxiety in new environments. Some have cognitive issues, especially older adults. And for whatever reason, they aren't able to comfortably navigate through a store. It can be stressful for this population, and even more so when stores frequently change their layouts. To address this issue, we present a generic grocery store robot architecture that can assist shoppers to search for products in unknown retail environments. Specifically, we created a unique method which we've dubbed Context Slam that combines optical character recognition and 2D laser scan measurements using a RAL Blackwellized particle filter. Context Slam simultaneously generates an annotated map using text found in the environment and localizes the robot within it while building the map. Our architecture also leverages aisle detection and frontier detection to drive exploration and product search. We first evaluate the mapping and localization performance compared to a popular SLAM algorithm, and we saw significant improvements. So you can see a much higher map quality generated with our work compared to G mapping, and a 48% improvement for localization. And this may not seem like much, but this can mean the difference between accidentally finding canned beans instead of your favorite breakfast cereal. We then deployed our architecture on our Blueberry robot platform at a local grocery store with great results for simultaneous product search and mapping. So you can see the potential for this research. Right now, Blueberry is intended to perform as an assistant, but imagine adding a manipulator and this instantly becomes a personal shopper. Especially these days when shoppers are hesitant to go in person to do their groceries, we can see the possibility for automated grocery store runners. Thank you for listening. You can see Blueberry in action here at our YouTube channel, and thank you.
Thank you, Michael. Next, we have June.
So, hello everyone. My name is Jun, a PhD student and working with Professor Stephen Waslander. And today I'm going to present our recent work, the ROBI, the multi-view dataset for the reflective objects in robotic bin picking. So in the real world, these reflective objects are quite common in most of robotic applications, like the robotic bin picking and manipulation and guidance. And for all these tasks, the following information is generally required: the RGB images with a good contrast, and the high quality of the depth data. So generally for object with non-shiny surfaces, the depth camera can provide the dense, high quality depths. But for when object has highly reflective surfaces, there will be large missing of this depth measurement, making this perception difficult. And moreover, because of this specular reflection, this fake edges introduced in the RGB images make this task even more challenging. And because of this, in this work, we construct this ROBI dataset, the reflective object in bins dataset. So we captured this dataset with 2 active stereo cameras at different level of cost, and we mount these 2 sensors on a robot arm and capture it at different viewpoints. So compared to the other dataset, the biggest novelty of our ROBI dataset, it is a ground truth depth map for the reflective objects. So we know that for this, because of highly reflective surface, the active stereo camera generally have the problem of this inaccurate and the missing depth measurement, and therefore In our work, we apply a scanning spray on these objects to remove this glossiness, and using a high-end camera, the depth camera, to capture this ground truth step map for all these objects. And so our robot dataset can be used for evaluating different robot perception solutions for these highly reflective objects. For example, like this object detection and the pose estimation. And because we also have this ground truth steps maps, and we can evaluate this like multiview depth fusion or any other depth related tasks, for example, like a depth completion and stereo matching. And in our work, we evaluate several algorithms and provide a benchmark for this object pose estimation and the multiview depth fusion. And there's definitely a lot of room for this improvement. So our dataset is currently publicly available on our website, so feel free to play with it. Okay, that's my time. Thank you.
Next, we have Yunchun Chen.
Hi, I'm Yunchun. I'll be presenting our work, Neuroshape Mating. The human-built world is filled with objects that are shaped to fit. To achieve assembly, human reasons about the fit between shapes. Semantic understanding in this case, however, is not necessarily for shape assembly. Consider reassembling a broken vase where each fragment does not have a well-defined semantic meaning. Reassembling them requires reasoning about the fit. We introduced the task of pairwise 3D geometric shape assembly, given the pair of fracture shapes in the form of point clouds. We propose Neuroshape Mating that outputs an assembly configuration for them. The proposed task is challenging yet practical with various robotics applications. We formulate the task as a post-prediction problem. Given 2 point clouds, we first extract point features. We then use a transformer network to capture cross-shape information. We use a regressor to predict poses. To evaluate the plausibility of the generated assembly result, we adopt an adversarial learning scheme. We introduce an implicit shape reconstruction task to account for imperfect point cloud observation. To train our model, we collect a large-scale dataset. Each object in the dataset can be cut with many ways, and each part of an object can be randomized with an SE3 pose. We compare our method with point cloud registration and shape assembly approaches. Our method outperforms all of them both quantitatively and qualitatively. When presented with noisy point clouds, our method still achieves better qualitative and quantitative results. This concludes my presentation. Thank you.
Thank you, Yunchun. Trevor?
Oh. Hi. Hi, okay, thanks. So my name is Trevor Abbeel, and I'm a PhD candidate in the STARS lab. Today I'm going to be presenting Learning from Guided Play, a scheduled hierarchical approach for improving exploration in adversarial imitation learning. We were motivated by the following question. Can we improve the performance of AIL, or a popular form of inverse reinforcement learning, by enforcing exploration of expert-provided auxiliary tasks? Compared with the standard AIL loop, we use a hierarchical model that incorporates multiple policies and a scheduler for selecting them, as well as multiple discriminators. In our experiments, we used a simulated Francopanda to learn several simple-to-define auxiliary tasks, as well as 4 challenging main tasks, and collected expert demonstrations of each. Here we show an example of the learning progression of LFGP compared with the state-of-the-art method for AIL, discriminator, actor, critic. In these videos, we show 4 exploration episodes executed by the scheduler in the case of LFGP on the left and policies during training. And notice how even after 1 million steps, LFGP has learned to already lift and nearly stack the block, while DAC has trouble even lifting the block. We compared against both multitask and single task baselines. To try and make a fair comparison, we trained our single task methods with the same amount of total data as the multitask methods. Our benchmarks are shown here. Although single task BC performs better than our method in 3 out of 4 of our main tasks, remember that it uses non-reusable expert data and doesn't gain the benefits of a multitask model, such as the ability to transfer. More importantly, our method outperforms single task DAC and multitask BC in all cases. A simple approach to transfer learning, in which we added new model heads to an existing trained model, improved learning speed in 3 out of 4 tasks with particularly dramatic improvement in brain. In this work, we identified and addressed an exploration problem in AIL and showed that a scheduled hierarchical approach can allow us to learn policies with better sample efficiency, both in terms of expert data and environment interaction than standard AIL. Furthermore, this method gives us the extra benefit of allowing reusability between both expert data and learned models. Thank you.
Thank you. Adam Hines.
All right. Okay, hi everyone. My name is Adam Hines, and I'm going to be presenting some recent work called Keep It Upright, Agile Non-Prehensile Object Balancing with a Position-Controlled Mobile Manipulator. Our main inspiration for this work was a waiter in a restaurant who has to balance food and drink on a tray while navigating a cluttered and dynamic environment. And we were wondering, could we do something similar but with a mobile manipulator robot? In particular, our goal is to balance objects at the end effector, avoid static and dynamic obstacles, and move as fast as possible to a given target location. This is not only applicable to service robots, but generally to transportation and delivery of goods where we might not have a rigid grasp on every object. We do this by using a model predictive controller that enforces motion constraints to balance multiple objects and avoid obstacles, minimizes the end effector distance to a given goal position, and is in fact fast enough for real-time computation. We validate our approach with a simulated robot shown here, which is balancing 4 objects, 1 tray, and then 3 cylinders. So to show you what this looks like, on the left here, I have the robot navigating a cluttered restaurant-like environment where it has to move through the environment without dropping anything or colliding with any obstacles. A little bit more challenging, on the right side, we have this dynamic avoidance experiment where it has to dodge the red balls, again, without dropping anything. In our experiments, we're seeing end effector speeds of up to over 2 meters per second and accelerations over 7.5 meters per second squared, while balancing our 4 objects. Also, we're seeing average controller computation time less than 30 milliseconds in all of our static and dynamic obstacle avoidance tasks. So it seems like we can in fact move fast and not break things. Thank you very much.
Thank you. Helen. I think you're muted, Helen.
Hi everyone. Today I will present our work, Seeing Glass, Joint Point Cloud and Depth Completion for Transparent Objects. Transparent objects are an essential part of our everyday lives. We use glasswares in our houses, factories, and laboratories. However, a problem that exists is that commodity RGBD sensors are only able to capture the distorted depth of transparent objects. This hinders manipulation tasks, which often require depth as an input modality. Our work has 3 key contributions: a novel dataset named Toronto Transparent Objects Depth Dataset, an approach to scalable and automatic dataset collection annotation for RGBD data, as well as TransparentNet, a novel method for joint point cloud and depth completion of transparent objects. Here we present TOD, which compared to other transparent object datasets has a larger scale, contains 3D annotations, and presents objects in a real setting with multicolored liquids and clutter. Even better, the dataset collection and annotation process is fully automated. The automated dataset collection and annotation method starts with the eye-in-hand RGBD camera, which scans the scene and collects the raw depth and RGB images. Next, post-processing with April tags identifies the poses of the objects. With the known translation and pose, we can fit CAD models of objects to the image. This enables automatic annotation of ground truth depth, poses, and segmentation. We then train TransparentNet for depth completion. Using input depth and mask, we first deproject the object depth into a point cloud and use point cloud completion to recover the basic shape. Next, we conduct refinement through applying the depth completion module to the point cloud to fill the blank depth and correct the shifted depth. We show the effectiveness of our approach in 3 scenarios, which presents the benefit of a fused point cloud and depth completion method, as marked in the red bounding boxes. Thank you for your time.
Thank you. Thank you for keeping us on time as well. Cody reading.
Hi, everyone. My name is Cody, and I'm here to talk about categorical depth distribution network for monocular 3D object detection. CADEN is a deep neural network designed for the task of 3D monocular object detection, which is estimating 3D bounding boxes of objects using only a single camera. The key feature of our approach is a prediction of a categorical depth distribution for each image pixel in the image, in order to accurately locate image information into 3D space. We transform our 3D representation into the bird's eye view perspective in order to perform 3D object detection. So the core issue with monocular detection is that monocular cameras do not capture depth information. So somehow we need to recover this lost depth information for 3D estimations. We learn that this depth information for each image pixel with a neural network. Rather than learning a single depth value, we learn probabilities that each pixel belongs to discrete depth bits. And we use these probabilities as a weighted projection into 3D space. This encodes our depth estimation uncertainty into our 3D representations, and we use our 3D representations for 3D detection. CADEN achieves state-of-the-art results on both the KD and the Waymo datasets. We visualize our depth estimation results from our image, where we can see that brighter colors indicate closer depths. We can also visualize our bird's eye view perspective features, in which objects can be distinctly located. And finally, we can overlay the detections on the LiDAR point cloud in order to show the accuracy of our method. We can see here that objects on both sides of the lane can then be accurately detected, even if partially occluded. If you're interested in our work, more details can be found on our project page, and we also provide a code release for our work CADEN as well. Thank you.
Thank you, Cody. That's great. Next, we have Alan Tan.
Okay. Hello. So in retail and manufacturing applications, multi-robot teams can help with merchandising, equipment, and supply transportation to reduce human labor and increase productivity. However, communication between robots can be costly, unreliable, and limited with increasing robot team size. And without the ability to exchange information between robots, task allocation and completion can be significantly degraded and compromised. Now, this is also a common challenge in human-to-human cooperation, but as humans, we are good at recognizing others' intentions to anticipate and adapt our plans to be complementary and beneficial for the team. Motivated by this insight, our research looks into how mobile robots can cooperatively explore an unknown environment by inferring their teammates' intentions in order to reduce redundant and overlapping tasks. To do this, we present MateNet, which utilizes a centralized training for decentralized execution paradigm where robots learn with global information such as the behavior and intentions of all their teammates during training, but only require local perception during execution. To test this theory, we deployed a team of 3 robots to cooperatively explore previously unseen environments and benchmark them against industry-standard methods as well as a state-of-the-art deep learning approach. The results showed that our MateNet was able to complete the task in less time, less distance traveled, less local interactions while achieving the highest objective function value. More importantly, we showed that our approach was impacted the least with decreasing communication availability, whereas the industry-standard methods degraded significantly. So what does this mean? Well, 2 things. 1, it is possible to train a team of robots to learn to predict their teammates' intentions and utilize that to anticipate and adapt their plans in an end-to-end manner to achieve successful cooperation. And 2, from the benchmark study that we've shown, we show that our method can save both time and cost while increasing productivity when deployed to complete tasks in partially observable and cluttered environments that can be found in retail and manufacturing settings. Thank you.
Next, we have Hao Yuxiang.
I'm going to share my slides. Okay. Hi, my name is Hao Yuxiang. Today I'm going to talk about our project, Learning by Watching. This work was done during my undergraduate internship under the supervision of Professor Animesh, and learning from visual data opens the potential to occur a large range of manipulation behaviors by leveraging human video demonstrations. However, the key challenge is how to bridge the domain gap of the robot morphology and the humans. And to achieve this, we built a framework learning by watching. The main contribution of our project is that we present an unsupervised domain transfer framework for robotic imitation learning from a single human video. And results show that our method achieves the state-of-the-art on 5 manipulation tasks. The key component of our method is the perception module, which composes a translation network and a key point detection model. In our framework, we learn a reward function, and then we use this reward function to learn a reinforcement learning policy. And the details of this method can be found in our paper. On the right side of our poster, we're gonna show some visualization and the results of our experiments. We first present the task scenes and the human video frame visualization examples for the pushing, sliding, drawer closing, and coffee making tasks. And we also present the visual results and comparisons of our method. And you can see that given a human video as the input in the first row, and we present the translated images of a cycle gang in the second row. And in the third row, we visualize the translated images and the detected key points produced by our perception module. And our perception module accurately detects the robot arm pose and the location of the interaction objects. And finally, we show the comparisons of the success rate for the testing evaluations of our learning by watching framework and the baselines. And for more information, please visit our website. Thanks.
Thank you. We have Abhishek Gadar and Bendaza.
Good afternoon, everyone. Today I'm going to present our recent works on ultra-wideband aided indoor localization with a focus on system design and calibration. To start with the motivation, accurate positioning is important for many indoor applications such as autonomous navigation and asset and tool tracking. Such a positioning system must fulfill certain requirements. That is, it must be accurate and robust to changing infrastructure and lighting conditions. Also, it should be computationally efficient and scalable. Finally, it must be lightweight, inexpensive, and easy to use. While GPS is unavailable in indoor environments, positioning systems based on cameras and LiDARs only don't fulfill all of these requirements simultaneously. We propose that the combination of ultra-wideband radios and lightweight odometry is a better fit for indoor positioning. However, in cluttered environments, the performance of such ultra-wideband-based system degrades if the influence of objects in the environment is not accounted for. We present a twofold approach to improve the performance of such systems. To set up an ultra-wideband aided localization system in cluttered environments, the first question is where to place the radios as shown by blue circles. To answer this question, we propose a mean square error-based algorithm to compute radio positions, which reduce the effects of the radio geometry, as well as the obstacle-induced measurement biases. We show that only by optimizing radio positions, we can achieve an improvement of 76% in localization accuracy. In our second work, which can be seen as a fine-tuning step, using a variational-based approach, we estimate the position of the anchors that were placed using the previous algorithm in an unsupervised manner. We also estimate the biases induced by the obstacles on measurements, and also the measurement variances to further improve the positioning accuracy. With the proposed approach, we see an average error reduction of 55% in position root mean square error. So what does this mean? With just off-the-shelf components using the two proposed algorithms, we can achieve centimeter-level accuracy in highly cluttered indoor environments. More information can be found in our poster session. Thank you.
I believe this was the last of the poster presentations. This was a very good job, and I think definitely everybody kept to time. So kudos to everyone. Hopefully judges had a time to evaluate. Additional material is also with the judges. I think in the interest of time, what we would do now is, can we move everyone to the lobby, Aiden? And Aiden would also have an announcement for all of us.
Okay. Welcome back, everyone. Hope everyone had a reasonable lunch, short break. And we are ready to get started with the second half. And I now get to take over the moderator and managerial position from Animesh, who managed the earlier session. Thanks very much to Animesh. Also wanted to say thanks very much to the folks that you don't see behind the scenes that have made this entire workshop possible. Animesh, Joan, Hallie, Jun, and Philippe. And of course, Aiden, who has put together our OYE-based pseudo-physical virtual system. So thanks to them. Okay, so if our next two presenters are ready, I am happy to pop over to read their bio information. And I'm delighted now to present to you at the workshop Dr. Goldie Nejat and Dr. Hani Naguib, who are going to talk to you next. And so I'll read their bios briefly. So Professor Nejat is a Canada Research Chair in Robotics for Society, or Robots for Society, I should say, and a professor in the Department of Mechanical and Industrial Engineering at U of T. She's also the founder and director of the Autonomous Systems and Biomechatronics Lab, which you can find online. If you haven't seen the website, it's great. Professor Nejat is an adjunct scientist at both the Toronto Rehab Institute and also at the Rotman Research Institute at Baycrest, and a fellow of the Canadian Institute for Advanced Research. Her research actually focuses on developing intelligent service robots and multi-robot cooperative teams for applications that are in the domains of retail and manufacturing, which we're talking about today, health, elderly care, emergency response, search and rescue, and security and surveillance. And you may have seen Professor Nejat. She's been invited to speak about her research in many different places, including in industrial forums, to scientists, to healthcare professionals, to policymakers, and to governments, as well as the general public, and just generally around the world. So look forward to hearing what Professor Nejat has to say. Joining her is, as I said, Professor Hani Naguib, who is the founding director of the Toronto Institute for Advanced Manufacturing. So we're glad to have Hani here. And Smart Materials, I should say, and Structures, and the Smart Materials and Structures group, pardon me. He's also a research scientist at the Toronto Rehab Institute, and his core expertise is in the manufacturing of programmable materials and systems, including stimuli responsive materials, metamaterials, and biomaterials. The research in Dr. Naguib's group is focused on the development of self-assembling systems, micro and nano fabrication, and additive manufacturing techniques for developing smart material systems. And Professor Naguib has received many honors and awards. He is, he has a Canada Research Chair. He received the Early Research Award from the Government of Ontario, a Faculty Early Teaching Award. He's also a professional engineer in Canada, a chartered engineer in the UK, a fellow of the Institute of Materials, Minerals and Mining, a fellow of the American Society for Mechanical Engineering, a fellow of the International Society for Optics and Photonics, a fellow of the Society of Plastics Engineers, and a fellow of the Canadian Society of Mechanical Engineers. So that's great. It's fantastic. So a lot. So you're going to hear an interesting talk from the two of them together. So with that, I hand it over to Goldie and Hani to take it away. Thanks very much.
Thanks, Jonathan, for that great introduction. So I'm going to give it to Hani first, and he'll start the first part of our talk, and I'll take over at the end.
Excellent. Thank you, Goldie, and thank you, Jonathan, for the kind introduction. So it's my pleasure to give today a presentation on the rise of robots and digital manufacturing, and show some of the work we have done with some of the industrial partner, as well as with what we do in our labs as well. Next slide. So just to give a general just summary about the Toronto Institute of Advanced Manufacturing, which we're very closely with the Robotics Institute. So the idea was really to start from that curve on the top left here, which is the idea of technology readiness level. And as you can see on that curve, you see the industry is looking at really high technology readiness level. So these were defined actually by the aerospace industry, from basic technology approach all the way to feasibility of the research, and all the way to a system a final product and or system development, and finally system test at the end. So the industry normally look at really high TRL, as we call it, technology readiness level, and then academia, what we're working on in research, is normally at very low, and the question becomes how to actually shorten or reduce that innovation gap, which you see here on the screen. And hence the idea came of the Institute for Advanced Manufacturing at the University of Toronto, is to look really at core research areas. Among them are advanced materials, manufacturing technologies, knowledge-based manufacturing, and business manufacturing. And from there, start to see how we can apply this and we, like with our industrial partner, and reduce that innovation gap. So one of the right away, the technology transfer we did, Goldie and I, which was apply this model actually under what we call the factory of the future, which I'm going to explain more in details in following slides, in some of our industrial partners. And the three pillars for these were in robotic and sensing, and also in Internet of Things, and I will mention this in the next few slides. So what is Industry 4.0? And I think the idea of smart manufacturing comes really from our factory of the future, or smart factory came from the model, the different industrial revolutions as known. So the first revolution is, as we all know, is the mechanization, water power and steam power. And then the second one, we looked at the mass production and assembly line. The third one started to look at computer and automation, which is a huge part of manufacturing currently. But now we're moving to the fourth like generation, which is the cyber physical system, which is a concept of utilizing, as we call it, large data exchange through the manufacturing and distribution processes, as you will see. So let me show you a small video, or part of a video, to show you this. So you can see a number of elements here, from additive manufacturing, big data, and major components that we can actually expand on it and see how we can apply this. And that's actually Industry 4.0 is apply this through our manufacturing facility. So next slide. So for the factory of the future and the idea of the strategies and focus areas, so we're looking, as I mentioned in my first slide, to robotics and automation, and the second is smart sensing, and finally human-machine collaboration. And that's kind of the framework we put together, and we started to apply to some of our industrial partners, looking closely and to what's involved. So looking at autonomous here and intelligent reconfigurable robotic system, collaborative robots and mobile robots, and having soft robotic system as well. On the smart sensing, looking at wearable sensors and how to monitor all the processes during manufacturing from operator and machines, and start to communicate and get all this information. And finally, the human-machine collaboration is getting robots, sensors, and workers, and getting them in a framework of a data, as we call it, system, by which we get all these information, and we can have a feedback signal to the robots or to the smart sensing system as required. Next slide, please. So just to give you an idea, so that's an example from some of our own research as part of the smart materials and structure, and looking today at renewable energy, looking at creating energy from triboelectric, supercapacitor, membrane batteries, CO2 capture and conversion, and we get this definitely through now implementation through a different industrial setting. looking at soft robotics, in actuator system, and artificial muscles. Examples are like these. Looking at the idea of human-machine interface, and looking at can we have a wearable system that can measure and communicate not only on the biomedical level, but also on the machine level or in manufacturing facility. In looking at mechanical system, looking at renewables, materials, and new development of new materials, as you can see, and how we can implement them, or structures system. And finally, looking at electronic system, starting from thermal management, piezo system, electronic skin. And we look at this and the integration of this through, as I mentioned, part of the factory of the future. We can see now it's one element only, and we can apply it through this. And with this, I would like to turn it to Goldie.
Okay. Thank you, Hani. So I'll just do a quick overview about the robotics and automation stream that we've been focusing on. And really, we encompass a lot of different techniques and technologies into how to make robots autonomous and how to make them interact with other robots in different types of environments, and of course with humans. So our research focuses on anything from autonomous exploration, navigation in both indoor and outdoor environments, how to manipulate different objects, either they could be complex objects or small parts to large parts, as well as then I was mentioning how robots will collaborate together to get tasks done and reach a certain goal or series of goals. And of course, it's important to have robots working alongside people. So we look into how to effectively integrate human-robot collaboration taxonomies. And of course, we do this with a lot of perception, sensing capabilities, and machine learning and deep learning strategies to allow our robots to be able to adapt to changing environments, changing people as they move around. For example, dynamics are involved in this. So just to give you some examples of what we do, for example, on the perception side, we look at really looking at complex parts and being able to sense them with the details needed. Because you're thinking about parts, for example, that because they're so complex, there's shadows created from the different features of each of the part on top of each other. So we'd like to do this all in real time, be able to gain 3D data from these parts. We use structured light, so we've developed unique sensors that use structured light techniques, and they do this all in real time to be able to sense 3D complex parts. And this can be from the macro scale all the way to the micro scale, where we're looking at micro scale features. For example, if you look at here, a Canadian dime, where you're looking at just the date, for example, the 1-2 at the end of the year 2012, and being able to sense and get the profile of those small features within a few micron accuracy. So this is really important for our manufacturing partners to be able to have this level of accuracy. In terms of robotics, we look at really varying different environments. So for example, having robots learn how to plan collision-free paths in an environment which has a lot of obstacles or objects in their way. So we want them to be able to learn how to get to certain goals or certain locations in doing this. Also, for example, in cases where we can't provide continuous testing in an environment, we can simulate the environment, and this is where transfer learning comes into play, where we can have the robots learn in the simulation, and then we've developed a pipeline that transfers that into the real world. And of course, when you consider that, it's not just about the transfer itself, but thinking about the reality gap and developing strategies that you have to consider when you're looking at the real technology in the real world, limitations in perception as well as mobility of the robots, and how to model those in the simulation. So you have this effective way of being able to deploy the robots in the real world. And so here it learns from simulation, and then you can deploy it in the real world. And of course, we're not looking at just flat terrain, because some environments can have, varying profiles, surface profiles, and be 3D. So we're looking at all different types of terrain when we do this. And then if we're looking at teams of robots, well, they may not all be the same robot. So heterogeneous teams. And how do we provide information to our users or the operators from a supervisory control perspective? The robots may be autonomous. They may need some user control depending on what the environment is like or what the task is like. And we like to do this in a way that's very effective for the operators so that they have improved situational awareness and we don't overload them with too much information all at once. Moving on just quickly to then our next topic is the cooperation between robots. So now looking at multi-robot teams and how for them to cooperate together to get certain tasks done. So for example, I said that we're looking at human-centered environments. So these robots have to be able to do their tasks with environments that may have people. And those people in that environment also have their own tasks that they need to complete. So robots have to be able to be aware of where the humans are, predict their motion and behavior, and be able to then move on to actually get their tasks done. So these robots are trying to go from one end of the lab to the other end of the lab to deliver packages, for example. In this video, we're looking at deploying robots in unexplored environments and having them work together to pretty much solve the coverage problem in these environments. These environments may be cluttered, you may have different obstacles, and the idea is to be able to efficiently do this with as much coverage as possible. And of course, robots need to share space with each other. So if you're looking at delivery tasks, how do they share the space and schedule each other and plan so that there's no collisions, of course. And lastly, we can look at our environments with people. So we want robots and humans to work together efficiently. So in this case, we're looking at collaboration between a person and a robot. This is the handover task. For example, the person hands over the object to the robot scans it to identify what it is, and then has to naturally hand it back to the person. So we want to do this as naturally as possible for the user so that they don't have to learn how to interact with the robot in an unnatural way. And then, of course, you have robots that need to go find certain users. So if you're looking at collaboration within a dynamic environment when the person that the robot's interacting with may not be always situated in the same location, you need robots to be able to find where the users are to interact with them. So we've developed AI planning techniques and scheduling techniques that allow the robots to plan how to find certain users within obviously a time frame so that they're not continuously always looking for the person. And then we deploy them to be able to execute those search plans. So here in this case, our Blueberry robot is looking for a certain person in an environment where there's multiple people and is trying to find where they are. And lastly, what about an environment that's crowded
I will
with
help
people,
you find cereal, crackers,
but you don't
granola, and
necessarily
honey.
are looking for the people, but you're looking for products. So a perfect example of this is our grocery store robot, which you can send it a grocery list and the robot will go down the aisles and find where the products are in that aisle. But of course, there's other people in those aisles that have their own tasks because they're going and shopping for their own products. So the robot has to be able to navigate around them and reach its goals. If the people are blocking it, it has to learn how to avoid collisions with them, go around them so that it can share the same space with them. All this has really led us to create what we call our new Center for Robots in Manufacturing. And we're happy to say that we have now a new physical lab. And the main themes of this lab are on robotic material handling and transportation, robotic manufacturing and industrial part metrology, as well as 3D printing of soft robotics and sensors. So that really brings in all the research that we've been doing across the multiple decades into one center and hub here within the Robotics Institute 5th floor as well. And I'll stop there. Thank you very much.
Okay, wonderful. Thank you. That's great. So just in the interest of time, we might ask folks to, everyone loves the clapping, ask folks to maybe hold their questions to the panel discussion that's coming up at the end of this section of the proceedings. And we'll move on to bring Dr. Sandra Skaff to the podium from NVIDIA. She's available. Thanks to Hani and Goldie very much for the great talk. Okay. Hi, Sandra. Great. So welcome. Hi. Virtually.
Thank you. Do you hear me? Yeah.
Yeah, we can hear you. Great. And so I'll just introduce you quickly. So it's my great pleasure today to introduce Dr. Sandra Skaff, who leads robotics ecosystem development at NVIDIA with a focus on startups in particular. And prior to this role at NVIDIA, she was the global lead of academic research engagements, including what was called the NVAIL program, where she was responsible for setting the strategy and managing the portfolio of engagements with many of the top research labs around the world in the areas of AI, robotics, and data science. She has 10 years of experience in computer vision and machine learning R&D at both large-scale corporations and at startups. She received her PhD and MEng degrees in computer vision from McGill in Montreal, and she has also actually authored more than 20 peer-reviewed conference and journal publications and has 13 patents. And I would just like to add also that NVIDIA has been a great help with Sandra in getting equipment for us for a new course we're developing, our capstone course for robotics as part of the Robotics Institute. And also, I think many of us are grateful for other support we've received from NVIDIA as well. So with that, I will turn it over to Sandra to give us her talk. Thank you.
Thank you, Jonathan. So I'm excited to be here today to talk to you about industry challenges and opportunities in robotics AI, and potentially how some of NVIDIA's tools can help. So as we all know and we see around us, the number of robots is growing, and we could bucket these into two types of robots per the International Federation of Robotics. There is industrial robots and then service robots. And within service robots, we have professional service robots that have grown tremendously over the last year. And within these robots, essentially what counts are the AMRs for logistics and transportation. So naturally, these essentially have grown because of the demand in the retail industry. And specifically, if we look at commercial robots in warehouses, it is projected to reach 1.5 million robots shipped to warehouses by 2030. And so definitely there's huge demand for robot in warehouses, and it's continuing to grow. And looking at some of the key trends in e-commerce, right? As we all know, in 2020, there has the demand for e-commerce skyrocketed. And to put that in perspective, in the last 10 years, the growth has been about 15% year over year. But just in 2020, we've more than doubled that growth in e-commerce. And majority of brands say that they are already deploying or have deployed AI and virtual reality to better serve their customers. And essentially, it comes down to software playing a key role and being the differentiator in solutions across the warehouse robotics sector. And specifically, of course, AI capabilities have a big role to play in that. So let's look at the state of warehouse automation. Traditionally, warehouse automation has been conveyor-based, and but recently, with the advances in robotics, mechanics, computer vision, navigation, and AI, we're seeing more and more automation in warehouses. And if we were to look at the main tasks of warehouses, in here we list them as material handling, sorting, order picking, packing, loading, unloading. We can essentially categorize a warehouse by its level of automation on a scale of 1 to 5, similar to the way you would think of self-driving cars, for example. By essentially, we can categorize them by the number of tasks they have automated. So the warehouses that are still in early exploration are around level 2 or 3. And then the most advanced warehouses are at level 4 today. So there is a fraction of those. And really level 5 is where the innovation lies, and being able to automate the entire chain of tasks is something that has not been done and is essentially, I would say, a green field. And so how does robotics AI help, and where does it manifest itself? So as many of you are familiar, we have seen autonomous guided vehicles turning more into autonomous mobile robots. So originally these were essentially remote controlled, and now we're seeing more and more AI. And these are being used to move goods around and material handling in the warehouse. And then we also have the stationary robots for picking, palletizing, loading, unloading, and so forth. And these are also seeing increasingly a reliance on deep learning and AI, specifically when it comes to recognizing the objects that are in front of them, right? And essentially the computer vision piece of these. And then we also have, for the fulfillment, essentially, and last mile delivery, we have these sidewalk delivery bots that are everywhere, and adding AI to these is a constant endeavor right now in industry. And we've seen this in many of our partners featured here. These are all using AI in their products and trying to advance their products as much as possible with AI. And Postmates, as many of you know, has been now is now served. So this image needs updating. So I don't need to convince this crowd here that robotics applications are very complex, right? Complex in many ways. It's a very highly interdisciplinary field, so you need experts from a lot of different fields to bring a robotics applications to life. There are many different types of robots out there, so the developing robotics applications is expensive and time consuming. In addition, there is a lot of different complexity when it comes to the different components and precision components as well, especially when it comes to, for example, manufacturing applications. And then adding AI, which needs to operate both at the cloud and at the edge, in the cloud and at the edge, is not making it any easier, right? So this is a very highly complex problem. So where does NVIDIA come into play? NVIDIA essentially is a full stack computing platform that innovates all the way from the hardware level, systems and chips, all the way up to the application frameworks, essentially, and everything in between. So for robotics specifically, we have the Isaac platform, for example. For autonomous driving, we have the Drive platform. And then we have a large ecosystem of partners, developers, startups, all building on this platform. And of course, the ecosystem feeds into each other. So before getting a little bit into the NVIDIA tools, let's look at what are the top 3 challenges in robotics application development. So I believe, and based on what we're seeing a lot from our partners out there and customers, we mainly talk about 3 problems, really. It's data. How do we get enough data to train? How do we label the data? Do we have enough? Do we not have enough, right? So that's one challenge at the training phase. Second, getting low latency, high throughput processing is very important, especially when it comes to, trying to select your hardware, trying to minimize cost and all that. So this is very important. You don't want to have more hardware and spend more than you need to. And then third, essentially, once you've developed your application, now how do you maintain it and manage it without having to have staff on site all the time? So let's double click on each of these, starting with data collection, right? So why is it complex? We have diverse environments, as you know, warehouse, fulfillment center, and so forth. Different types of objects, right? There is a myriad of objects out there that a robot might need to deal with. And then there is a lot of different attributes of these objects. So essentially, having all this variety and modeling all that is very complex. And so collecting the data for all this, each neural network needs millions of training examples, right? So that is very complex. And then you need to multiply it by all this variation that's needed. And so I argue, of course, that simulation would help a lot, or synthetic data generation, essentially, for collecting data for training models is very important, as it allows you really to speed up your development process, and then you can fine tune with some examples. And then when it comes to low latency, high throughput processing, essentially, there are three factors that come into play, right? So you need to be able to maximize the throughput in the warehouse, right? So it needs to be a really fast system. And then not only that it needs to be fast, let's say a robot doing a certain task, it needs to be highly accurate, right? So you cannot be a best effort solution. And specifically for, the packages are being shipped to customers. They don't want to be receiving the wrong products, for instance. And then, of course, the robot needs to be operating safely, in the sense, for example, if you have a robot navigating in the warehouse, they need to avoid obstacles. So that means they need to sense, essentially, and act on that very quickly. So sending data to cloud for processing and back is not a viable solution. And so, that also essentially feeds into the need of low latency processing. And then if we were to think of a solution in here that would essentially target all, essentially and address all these, we also need to think about the hardware, right? So the hardware plays a key role. And then the cost of the hardware, because we see a lot of our customers, of course, they need to justify, or partners need to justify cost to their end customers. And so, you know, you cannot just have a beefy GPU or processor to do your entire compute all the time. And, you know, that could be good to get started, but at some point you need to build a commercially viable solution that needs to be, you know, as cheap as possible. And of course, with the same capabilities that you would have otherwise. So when it comes to deploying an application, there are many challenges as well. So we have a large number of robots and types of robots, specifically we see with warehouses, you know, there's different types of robots that might need to be deployed to really automate a warehouse. Even we've seen, you know, customers look at drones, AMRs, autonomous mobile robots, and then maybe you have you know, other types of robots as well. You have cameras, so which are not necessarily robots, but edge devices. And then, of course, once you deploy your model, you need to keep monitoring it, because there is this model drift phenomenon that occurs, right? So the model that you trained initially might start degrading in performance because of some, for example, sensor degradation or changes in environment that maybe you might not have anticipated, but that could happen, right? And so you need to constantly monitor your deployment. And then finally, your deployment needs to be scalable in the sense that if you were to add one robot or remove one robot, you want to do that in a seamless fashion without taking down the entire deployment. And ideally, you know, you want to do that, for example, if you want to spin up a deployment or a robot, you want to do that without sending your whole you know, development team on site. You want to do as much of it as possible remotely. So you know, there's definitely a need here for finding viable ways to operationalize and manage deployments. So with the NVIDIA robotics platform, we look at accelerating the whole process of robotic simulation, development, and deployment. And it starts with data collection, as I mentioned. So, you know, collecting data for training your AI, synthetic data, as well as maybe training your robot in a simulated environment. And then we have tools for training. We have tools for developing. For example, we have recently started working with the ROS community to accelerate some of the deployments and provide, algorithms, and provide packages that ease the deployment of these accelerated algorithms onto robots. And then finally, at the deployment stage, we also have different tools to both deploy and manage deployments. And we have a large ecosystem of partners, essentially across sensors, frameworks, robot computers, reference platforms, and so forth, and CSPs that could essentially leverage each other to make robotics applications, bring them to life, essentially. So on the simulation side, some of you may have heard that NVIDIA is building Omniverse, which is a platform for 3D content creation and collaboration. And on top of Omniverse, we are building different applications for different use cases. So for the robotics use case, we are building the Isaac simulator. And the Isaac simulator has two main components, or two main uses. First, it's the synthetic data generation. And then second, it's simulating robots inside the training robots inside the simulated environment. So you can train a robot for navigation and manipulation. And we have capabilities to import robot models in the form of URDF or STEP, for example, format. And then different sensors could be loaded, sensor models could be loaded, RGB, stereo depth, and so on. And for synthetic data generation, we also have essentially support for the applications of segmentation as well as object detection. And then we do provide different samples, whether ROS or Python or so forth, to essentially get started with this Isaac simulator. And when it comes to synthetic data generation, I just want to highlight that we also have a tool for domain randomization. So you could randomize, you know, perturb your color, materials, and so forth of your objects, and then you can export all this data and use Isaac Sim essentially as a tool to generate the data. You can export it and then use your own framework for training using this synthetic data. And this could essentially ease the data collection process. And then in your robotics application, you would fine tune on a small set of real data. And then when it comes to low latency, high throughput processing, we have the Jetson family specifically for AI at the edge and autonomous systems. And we have the whole, product line from entry to advanced autonomous machines. So if you size your compute needed, you can select the appropriate Jetson. And naturally, the more floating point operations you need, the higher the cost. But we do have this whole range. And then this week, actually at GTC, we will be announcing a new Jetson called Orin. And actually we'll be announcing its specs. So we're excited about the potential for more advanced Jetsons, essentially. And then using the Jetson platform, what you could do is leverage the software that we provide. And a lot of folks don't know actually that we have a VPI, which is a vision programming interface. It's actually a collection of computer vision and image processing algorithms accelerated and optimized for the specific hardware processors on the Jetson. So on the Jetson, there is not only the GPU, there is CPU cores, of course, and then there is a PVA, programmable vision accelerator, as well as a video and image compositor. So you could use some of our VPI algorithms that are optimized for these specific processors, and that way you could essentially free up the GPU for more of the heavy compute. We also have TensorRT that helps you optimize your models for inference. It essentially includes pruning and quantization capabilities as well, and it supports different variety of NVIDIA hardware. And actually, a lot of folks today are using TensorRT, so it's highly popular. We also have Triton for managing, which is an inference server for managing your different deployments or inference models in your deployment. And the back end of all of these is CUDA, as you probably are familiar with. And then specifically for ROS developers, we have been working on providing accelerated algorithms in ROS. So we're taking our GPU accelerated algorithms and wrapping them in ROS nodes and making them available on GitHub. So that way, any ROS developer can natively call some of our GPU accelerated algorithms. So we have started with a few April tags detection, visual odometry, stereo depth. We also have a neural network inference package that supports segmentation and 6D pose estimation. But you can also add in your own models. We provide 2 models in there, and you can replace those with your own models. So you can use these packages, and they are optimized to run on Jetson as well as other GPUs such as RTX. And then for managing inference jobs in your deployment, we have the Triton Inference Server, which is great because actually it's open source, so you can use it and extend it, and it supports different frameworks. It helps you schedule all the jobs, and so you don't have to do that manually. It helps you upgrade, so you can upgrade a model without having any downtime in your system, and it's also standardized across cloud, data center, and edge. So this could help essentially support managing application management. And then finally, I just want to highlight some programs that NVIDIA supports. So on the education side, we have educator programs, Deep Learning Institute and Ambassador programs. We have also teaching kits that professors could take and download and integrate in their course material. We have 2 grant programs, the Hardware Grant Program for teaching and research. We have an Applied Research Accelerator program that supports research that is being deployed in a product or service. And then we have a startups program called Inception, which supports startups and has more than 9,000 startups today. So thank you, and happy to take any questions.
Okay, thank you so much, Sandra. I think just in the interest of time, we might ask for folks to just hold their questions for the panel that's coming up. We will definitely have a chance, so you'll have an opportunity. Don't worry. Don't forget your questions. Save it for Sandra, and we'll get to it definitely during the panel segments. And thanks Sandra again, and then we'll jump on to our next presenter, who can come to the podium virtually. Thanks, Sandra. Okay, so now it is my pleasure to reciprocate and introduce Professor Animesh Garg, who should be popping in there. There he is. Okay, so you may recognize Professor Garg from such presentations as this morning, or the panel discussion. I get to read his bio, which is great. So it's my pleasure, again, as I said, to introduce Animesh. He's a CFAR chair, assistant professor in computer science with a courtesy appointment in mechanical engineering at U of T. He's also a faculty member at the Vector Institute and at the U of T Robotics Institute, of course, where he leads the People, AI, and Robotics, or PAIR research group. Additionally, speaking of NVIDIA, Animesh is a senior researcher, at NVIDIA Research. He earned his PhD from UC Berkeley, which is a school I think I've heard of somewhere. It's down there, yeah, I think it's down in California somewhere. He was also a postdoc at the Stanford AI Lab, and his research, he's done a number of really interesting things. His research focuses on machine learning algorithms, particularly for perception and control in robotics. And the goal of his work is really to build generalizable autonomy systems, generalized robotic autonomy, which involves a confluence of representations and algorithms for reinforcement learning, control, and perception. The work that he has produced and his group has produced has received multiple best paper recognitions, including at ICRA, IROS, RSS, the Hamlin Symposium, and at workshops at NeurIPS and ICML. And it's also been widely covered in the press by the New York Times, Nature, BBC, and Wired. So great stuff. I'm really jealous of the video I can already see playing on his slides because I didn't have a cool video like that. So without further ado, Animesh, please take it away.
Thank you very much, John. And I agree. I think I'll try to preserve and conserve time as much as possible. So what we are here today to talk about? We are here today to talk about how to automate manufacturing and retail. Let's think about perhaps one potential store. This is a store around the corner, grocery store in this particular case. Now, it's not that people haven't tried automating this, right? Amazon Go is something that you may have heard of, but really what I would call this is Wizard of Oz, right? What if you pick up almond milk and then decide, oh, I don't want it, and keep it somewhere else? Someone has to go behind the scenes to sort of make it look nice. That is the kind of thing that we're trying to automate. What if this was completely self-sustainable, autonomous store? From back room to front room, what would that mean? Oh, that would mean a lot of interesting things. That would mean, as Matt was mentioning this morning, receiving, sorting, inventory tracking, customer tracking, social interaction, restoration and restocking, retrieval and packaging. So essentially, a store or automating a store is stand-in for running a warehouse and actually more. And again, we keep using grocery as the running example. Nothing here that we talk about is limiting us to grocery, right? This is equally applicable to the Mall of America, Lowe's, Target, Macy's, and so on and so forth. It's just that running a Macy's must be much, much harder. Fair enough. But nonetheless, the principles are still the same. Now, the kind of things that we need to do in a store is actually very varied, right? You might need to do cleaning, cooking, or preparation, or whatnot, right? And this idea of like jumping from kitchen to manufacturing and then let's say retail is not really that big of a jump in the sense that the variety of tasks is very big. That's the thing that you need to understand, right? Now, if you think about like a robotic framework, what does it need? Sense, plan, act. So you need perception, planning, control. Along the way, you'll probably need some data as well. It is not really working somehow. So we need to do something about it. Why? Clearly, there are not a lot of workers. The problems are too varied to be able to sort of automate it one by one. Now, if you look at our friends in vision and language, they seem to keep just growing and growing every month or so. The models keep growing, the performance keeps growing, da-da-da. And what is happening? One thing to attribute their performance could be compute, and the other one could be data sets. Turns out, robotics doesn't really have the concept of large data sets, right? There are too many problems to create data sets for each. How are you going to go about that? So this is where I would argue simulation comes in. The idea really is that we want general purpose robot learning algorithms. But to get to the algorithms, or to even make the algorithms, you need frameworks where you can enable, test, design these algorithms. Then you need to do some sort of learning or control with that algorithm. And finally, you'll need to think about deployment. And all of these result in independent technical problems. And what I'm going to do today is to give you a brief preview of the things that we have been up to in the last sort of few years. Of course, this would not be all of the work that we have been doing, and definitely we'll not be able to get into any sort of detail, but it'll still get you a sense of like what sort of problems we are interested in, and how I believe and how we believe we can make meaningful progress towards the bigger picture. So let's get started with simulation. So the first problem that I want to talk to you about is dexterous manipulation. This is something that essentially is needed for any sort of dexterity in whether it's food service work or retail or packing that cannot be done, let's say, with a simple suction cup. So this itself has been tried, but the last time it was tried, it required 200 centuries of compute. So that is a bit, well, not accessible. So what we tried looking at is we looked at a robotics by robotics as a service model that was provided to us by our friends in Germany, and high performance, high throughput simulation. The outcome of all of this is you can now train this system with reinforcement learning style model and go from there to train something that was supposedly very, very complicated with a simple algorithm on a single GPU in a single day. The important thing to note here is on the top is actual time, and on the bottom is number of time steps, and that is billion with a B. So we are operating at 4 billion time steps in 1 hour on a single GPU. This really democratizes the kind of things you can do as a researcher. And now we actually went one more step ahead. We actually said, okay, let's see what happens if we put it on robots that we have never actually touched. So we did this, and it turns out that the performance wasn't all that bad. We were succeeding 5 or 6 times. We were not optimizing for this thing. We are completely training in a simulation at large scale. So this is where, when simulation is scaled to a point where we are thinking beyond millions, suddenly a lot of things that was considered hard starts working. Similarly, as we saw in the previous talk, one of the other problems is, well, scalable simulation. So easy things can be simulated at scale, but what about complex things like kitchen? There are so many things, so many objects, dexterity, articulation. So what we need is ease of use. We need frameworks where we can model a very large variety of things very easily, so that any algorithm will be exposed to a diversity of problems. So in this case, we tried learning a mobile manipulation system that can do articulated or interact with articulated systems that it has never seen. So it has never seen this particular fridge or this particular oven. And what you're seeing here is procedurally generated kitchen models where the robot goes in and opens these objects without explicit knowledge of any geometry, any shape. The only input is actual vision. And then again, you can use classical algorithms, not just RL. In this particular case, you're using optimal control to build a whole body controller that will open a drawer even in the presence of simulated walking human. And again, you can combine the power of GPU-based simulation and put the policy in, let's say, a 3D scanned environment and try to play it back and see what happens. So you don't have to train in slow simulation. You can train in fast simulation and then go to slow simulation, if you will. So we talked about a couple of ideas of what we can do with fast simulation. But simulation itself sometimes might need learning. Why? Because every phenomenon is not easy to simulate, or at least not fast to simulate. What about clothing? You could argue that we can, in principle, simulate clothing, but it's usually very slow. And now we want to be able to have a general purpose simulator, not one-offs. I don't want to just fold t-shirts, but what about pants and pantsuits? And if you're good with that, then what about my wife's tops? All of that is very hard to fold. So what we did was we created a learning-based simulator this time around, which is operating in a much reduced order. So it is only using 8 key points rather than a full FEM model. And a single model based on causality can learn how the dynamics of a towel works, a shirt works. The shirt can have half sleeves or a different fabric or maybe a pant. Importantly, it's a single system. I'm not training it per topic. So yet again, this is better simulator, but this time the simulator itself is learned. Similarly, you can argue that there are other phenomena like cutting. Cutting is something that is ridiculously hard to simulate, is very slow, but is very, very common in both surgery, food processing, kitchen, and whatnot. So we built this differentiable cutting simulator, which allows you to not only understand the process of cutting, but actually differentiate through the process of cutting so that you can compute, for example, the right amount of knife forces and trajectories. This allows you, basically, it builds the system with a spring mass system, and cutting is essentially weakening the springs. Interestingly, this idea can now be put to use on real robots. And of course, in this particular case, we are able to do open loop cutting, but this idea can be used actually to do curvilinear cuts as well. Finally, whatever we do, we're never going to be able to solve the problem just with simulation. There'll always be something where human dexterity is needed. And that is precisely where I would argue that we need to be able to have mechanisms to collect large-scale data. And a lot of times we talk about data collection and we argue that, oh, perhaps dexterity can be achieved by maybe VR. But VR doesn't give you the scale. What you want is diversity of solutions, because the same problem can be solved multiple ways. Dexterity of the solution, because that is the part that is really hard to learn. And scale. If there's one thing that deep learning has taught us, it's the fact that if you have scalable data, then a lot of problems will become easier. But generally, doing this through VR will never scale. At least you'll not be able to scale it to a point of tens of thousands of demonstrations. So what we need is crowdsourcing. So what we've created is a framework where you do not need any special equipment, no special compute. Everything runs completely on cloud, and all you need to download is just an app. This allows you to completely control a 6-to-off robot, either in simulation or in real world, to collect these kind of dexterous and interesting data. And we have tested it. We have tested it across environments, across tasks. People have done this from kitchen, coffee shop, and homes, where the robot was not even co-located. And in some cases, the robot was actually across Pacific. And finally, the question usually is deployment. We are real roboticists after all, so we do want robots to work. Now, usually what happens is you do what you do to train your system. Then you bring your system to game time. And then when there is game night, you say, I will cross my fingers and hope the robot works. Sometimes it works, sometimes it doesn't. This is an example where a Boston Dynamics robot failed on live demo in front of Jeff Bezos. That was kind of failure. But then what do? You just go back and try again. Right? Of course, this was a tongue-in-cheek argument, but the sort of safety is mission critical in many use cases. It's not just legged robotics or dexterous manipulation. It is across the board. And of course, you might argue that, oh, in manipulation, what if I dropped one vial of glass, or it's just cheap? It's not about that. I think it's about performance. When speed is being measured through throughput, you cannot have a system that is working 98% of the time, and the other time you're just cleaning up the glass shards. So what we created is an algorithm where safety is easy to specify. I don't know how it will fail. All I know is it's easy to say this is failure. I can verify yes or no, this is failure. Everything else is super hard. I don't know, for example, for a high dimensional system, this is safe state or not safe. That is very hard for like an intuitive system to design. And in doing so, we create an algorithm which can learn to do the task. Let's say it already knows how to stand, but it can go to running without failing. But in the process, incur much or far few failures. And this is very important, right? If you can reduce the number of failures by 2x or 5x in practical systems, it matters. So this is indeed the last slide. So what we talked about is, I believe that the solution to building general purpose autonomy or AI robotics will require all of these components: better simulators, better learning algorithms, mechanisms to use and collect large-scale data. And finally, we have to take a systems approach to robotics when we deploy them, very much like what we do with machine learning. I think this is where I would like to end. Thank you very much, and thank you for the privilege of your time.
Excellent. Wonderful. Thank you, Animesh. That was great. Okay, so we will, in the interest of time, save questions to the panel. Please don't forget your questions, and we will move on to our next speaker, who is Professor Stephen Waslander. And if Steve can come to the podium, I will introduce him. Professor Waslander is a leading authority on autonomous drones and also autonomous driving vehicles, with an emphasis on 3D perception, SLAM, and multi-vehicle systems. Steve received his bachelor's degree from Queen's and his master's and PhD from Stanford, with a PhD in 2007 in the Aeronautics and Astronautics departments, where he created the Stanford testbed of autonomous rotorcraft for multi-agent control, or STARMAC. Many of you have probably seen this. The world's most capable outdoor, way back, the world's most capable outdoor multi-vehicle quadrotor platform at that time. And then from 2008 until 2018, he was a faculty member at the University of Waterloo, where he founded and directed the Waterloo Autonomous Vehicle Lab, or WAVE Lab. And luckily in 2018, he joined here at U of T at the Institute of Aerospace Studies and founded the Toronto Robotics and Artificial Intelligence Lab, or TRAIL Lab. And Steve's work focuses on pushing the state of the art in localization and mapping, object detection and tracking, and integrated planning and control, as well as multi-robot coordination. So with that brief intro, take it away, Steve. Thank you.
Thanks so much, John. And really fun to be here today. I appreciate getting a slot. I feel like a little bit of a contrarian or outsider here, in that I'm sandwiched between a beautiful talk from NVIDIA and soon to come Pieter Abbeel. And I'm going to go back to the classical methods and completely ignore everything Animesh just told you and start talking about ways to do challenges within this space without learning. So we're going to look specifically at a small topic here. So not a broad speech, but we're going to talk about one of my PhD students, Jun Yang, and his amazing work in collaboration with Epson on dealing with highly reflective objects for bin picking. So I thought that was quite suited to this session. So we've been looking at specifically the challenge of trying to reconstruct and then identify the pose of objects in bins to enable rapid bin picking for any variety of applications. And specifically, we're looking at objects made out of metal with highly reflective surfaces, which tend to be a big challenge, particularly for the prevailing approach for bin picking these days. So what we're looking at here, we can see sort of the default bin picking task. A robot arm needs to pick up a screw or a valve of some sort. It starts with a static active stereo camera perspective, then identifies those subcomponents that are the individual objects, finds a pose with which it can identify a grasp, and then plans a path to execute that grasp, right? And so the primary sensing technology here is these active stereo cameras. And the reason for this is that we need extreme precision on the features, the fine-grained features on these objects in order to determine their pose reliably. We're often talking about fairly small features, and we have full control over the environment, so we can do what we need there. And so we have a nice little example pair over here on the right of a matte object versus a reflective object, and how the active projector pattern gets affected by the reflectivity of the surface that it's being shown upon. And as a result, you can see the degradation of the depth map over here in terms of how that object appears. And this is to some extent, hopefully, an avoidable problem, right? In that if we know something about the shape and we know something about the loss of information when we overexpose the image, we should be able to move to a better viewpoint. And so if we can do this, we can then fuse multiple viewpoints together and construct more complete representations of the bin, and therefore identify the components within with more precision. And the challenge here really is, how do we then determine which components or which subpixel or pixels and depth values we should be keeping, and which ones should we be trusting, and which ones are garbage or missing? How do we fuse these things reliably in a way that is going to lead to accurate accurate pose estimation. And of course, anyone who's taken a course from me or seen any of my previous work would of course know the easy answer is Bayesian inference. So let's see if we can do that properly here. So we're going to look at essentially improving on a volumetric representation, because this actually leads to a reliable 6D pose for the objects. And you can start obviously from the TSDF representation for these depth maps, but they don't tend to have a strong probabilistic formulation integrated into them. And so you end up with a lot of artifacts, a lot of challenges from the collection of those multiple views, where data of different reliability is being fused together into a single view or a single representation of the objects. And so what this work does essentially is it tries to decompose the uncertainties on each depth measurement and apply those essentially throughout the truncated sign distance function representation. So we're going to look at both photometric uncertainty and geometric uncertainty, try to identify how those are affecting the individual depth values we've observed, and then properly update the sign distance function representation of the environment using that probabilistic information. So for photometric uncertainty, we can actually directly compute that from the source images we have in the stereo. So you can see on the left here, we have visible patterns of the light from the projectors onto the surface. And what happens, of course, is you get this nice ideal cost curve in your stereo matching, where there's a single minimum and everything else is quite noisy. And therefore, it's clear where your disparity is and what your corresponding depth is as a result. However, when we get to these regions with oblique angles and large reflectivity, that same kind of nice minimum disappears, of course. And so we can use this actually to give us a sense for the uncertainty associated from the photometric perspective of how much we should trust a particular depth measurement reported by the sensor. And so we literally look back at this subsegment of the stereo matching process, and we can construct an uncertainty based on the shape of the disparity hypothesis curves. For the geometric uncertainty, we can look at local neighborhoods. And here the idea is essentially that the parts are still, 3D and embody a physical space, and therefore are unlikely to have fully noisy and erratic surfaces. And so we can construct local surface normals and identify whether or not an individual point matches with its local neighborhood in some sense. And this, again, gives us a probability or an uncertainty associated with that depth based on how far it deviates from its own local neighborhood. So combining these two together, we end up with measurements that are inliers and measurements that are outliers. And we relied on a really nice formulation in this paper by Dong et al. Called the PSDF, a probabilistic sign distance function for fusion of sensor views. And what we're doing essentially is treating the distribution as Gaussian for inliers and uniform for outliers. And we can approximate this combination, this addition of Gaussian and uniform, as a beta times a normal distribution. This is a pretty cool approximation. It works quite well. And so now all we need to do is estimate these 4 parameters and have a representation for each individual measurement, essentially. So we can construct a measurement model directly from this inlier-outlier representation. We then have a nice way to form Bayesian updates using this conjugate prior form, right? And that allows us to now come up with a precise probabilistic representation of each of the sign distance function values within the volume. And so we now have a probabilistic update for our volumetric representation. As mentioned by June in his poster talk, he spent an immense amount of time building, I think, one of the most detailed and interesting data sets for bin picking with metallic or shiny objects. We call it ROBI. And it's got a huge amount of data associated with it. So go take a look if you're interested in this problem at all. And what's really neat about it is for every single bin, it's got 88 views and 125, sorry, in some, this is the updated version. 88 was the original. So we now have 125 viewpoints and 94 on low bin. And you can basically look at any different variety of fusion methods and do a lot of interesting comparisons. And in order to get ground truth, we used the cool trick of a scanning spray, which covers all of the reflectivity and recovers basically an almost complete depth map from a single viewpoint. And in fact, we can once again fuse over all of the views with the scanning spray included. Okay, so just to quickly show some results and to wrap things up, we're very excited to see both the standard deviation as a function of views decrease and the inlier probability increase. So you can see that we have reliable depths being accumulated over time with our model, and we can show performance improvements over TSDF and other existing methods. So all the details are in the paper, and what you get essentially is less noise and more precise representation of the objects, which ultimately leads to significant improvements in the pose estimation for the individual objects. So where are we going from here? We can do more specific photometric modeling of the reflectance by making estimates or predictions of the surface normals. So we're looking into some interesting things there. We're looking at learning some of the uncertainty models and slowly, jumping ship from the classical approaches. And finally, we really like to exploit low-cost sensors and make this move at a much higher frame rate. So that's where we're headed in the future. So with that, I'll wrap it up and pass it back to our moderator.
Wonderful. Thank you, Steve. Great talk. Wonderful. Okay. So again, folks, we're just about back on track, and we thanks to Steve for pushing the envelope in terms of delivery. We appreciate it. And so we will save questions again to the end for the panel discussion. And now we'll move on to the next talk of the session, which is Professor Pieter Abbeel. Thank you, Steve. All right, we'll bring Pieter to the virtual podium. And it will be my pleasure to introduce him. Hi, Pieter. Great. Okay, hi. So I will read your bio quickly, but it's a short one, but it could be pages, but it's not. That's okay. We'll go through Pieter's bio. So Pieter Abbeel, if you don't know him, which you should, is a professor at UC Berkeley and also the co-founder and chief scientist at Covariant. As well as the host of the Robot Brains podcast, relatively new podcast. If you haven't listened, check it out for sure. At Berkeley, Pieter directs the Berkeley Robot Learning Lab and is also the co-director of the Berkeley Artificial Intelligence, or BEAR Lab. And Pieter's research strives really to build ever more intelligent systems with an emphasis on deep reinforcement learning and also deep unsupervised learning. At Covariant, Pieter is helping to bring AI and robotics into the real world, beginning with the challenging task which we're talking about today of warehouse automation. In terms of awards, as I said, if you haven't seen Pieter's work, you should definitely check it out. He's received many awards and honors, including the Presidential Early Career Award in Science and Engineering, the NSF Career Award, the ONR Young Investigator Program Award, the DARPA Young Faculty Award, and a TR35 Award from Technology Review. And he's also an IEEE Fellow. And his work also is very frequently featured in the press, including the New York Times, the Wall Street Journal. It's been in the BBC, Rolling Stone, Wired, and on Tech Review as well. So without further ado, Pieter, whenever you're ready, please take it away. Thank you.
Hey, thanks for the nice intro, and thanks everyone for being here. I'm going to actually broaden the scope a little bit. Thank you. Beyond just retail, and think about the really great opportunities ahead of all of us in AI-powered robotic manipulation. So look at this here. What are you seeing? This is recycling being done, but it turns out that most of the things that could be recycled are actually not recycled because there's not enough labor available to do all this sortation. Another good example is produce. A lot of the produce actually goes unharvested on the fields just because it's very, very labor intense to harvest produce. And so it just is left there to rot. Then the big example that's most central to today's topic is, of course, e-commerce fulfillment. A lot of shopping is done online. More and more every day, accelerated with COVID. Turns out a lot of labor has to happen behind the scenes, and it's not the most interesting or pleasant labor, it turns out. So, for example, warehouses tend to have about 100% turnover on a year-to-year basis for people doing the pick and place operations. And then looking at a completely different end of the spectrum, where something like surgery, you might someday need to undergo some surgery. You'd love to be at the hands of the best surgeon in the world, naturally, But those are rare and not available everywhere in the world. And again, another scenario where, in some sense, a different kind of labor is not sufficiently available compared to what we would want. So where are the robots, which in principle could be helping out at all the things I just described, but actually aren't so much? Well, the robots today are mostly in car factories and electronics factories. And what are they doing there? Well, they're doing the kind of things that you're seeing here. So on the left, you see robots actually hard at work assembling cars. On the right, assembling circuit boards. And so this works. It's very effective for these kinds of problems. But these kinds of problems are actually narrow once you look at the details. What's done with traditional robotic automation requires highly structured environments such that pre-programmed deterministic motions are enough to succeed at the task. And so cars are built with pre-programmed robots, not robots that react to what they're seeing. And that, of course, is the next generation that we're knocking at the door of, AI robotic automation that can handle less structured environments and exhibits intelligent reactive behaviors. If we can do this, there's actually a massive space of things out there that could be done by robots. We just need to make them smart enough to do these things. So what is the current status? If we look at the space of semi-structured environments, as the examples I just showed you, there's actually high, rapidly growing demand, and many AI robotics pilots are being run across all these domains. I mean, less so in surgery, that's that's a bit different, but in farming, in warehousing, in recycling, a lot of AI robotics pilots are being run. But going large scale is currently bottlenecked on autonomy. And if you hear bottlenecked by autonomy, you're probably the first thing you think of is self-driving cars. For now 10-something years, there's been efforts to get self-driving cars on our roads, and they're bottlenecked on their ability to achieve a sufficiently high level of autonomy to actually be viable without having a safety driver. And of course, once you have a safety driver, it kind of defeats the purpose of having the self-driving car. But the same is true in robotic manipulation. Sufficient levels of autonomy are key to becoming commercially viable. And so let's take a look at an example. Let's say you have some station, maybe a pick and place station in a warehouse, and your robot has 90% reliability, and this is a station that needs to fulfill at 500 picks per hour, and every 1 minute there is a failure. And so that's a lot. That means somebody needs to be with that robot at all times to fix up the robot's mistake. And actually, it becomes more expensive than just having a person, because the person could just do it, but now the person is there and the robot is there, and they're not more effective than just having a person. Once you have 99% reliability for a station that's 500 per hour, you might have a failure around every 12 minutes. And now, actually, a person could maybe oversee a handful of robots. And things start knocking at the door of being commercially viable. Once you hit 3 nines of reliability, you would have a failure once every 1,000 picks, let's say. That is once every 2 hours for a 500 picks per hour station. And now all of a sudden, a human can oversee a fleet of robots, and things become absolutely viable. And so 3 nines of reliability is a kind of a good reference point for robotic manipulation solutions, at least in something like warehouse operations. Now, it's not that they're all 500 picks per hour. Some stations will be 200 picks per hour, because just the flow around it doesn't come in as fast. Others will be 2,000 picks per hour. And so it can vary from station to station in a warehouse how fast things have to go. But the 3 nines of reliability is probably still the right ballpark to keep in mind of what you need to strive for. And so the question becomes, of course, can we try to achieve this? And in fact, many companies are working on this. If you look in the recycling space, there's multiple companies pursuing robotic pick and place to reduce the unnecessary waste that goes into landfills. In farming, there are many companies pursuing this, often for harvesting produce. And then in warehousing, actually, there's even more companies. It's probably the most crowded, most active, and maybe commercial, so most highest dollar turnaround, at least right now, space, where a lot of companies are striving exactly for that, achieving sufficient autonomy that robots can be truly helpful. And so many, and I'm not sure, I mean, some of you might work at some of these companies listed on the slide here, but if you're not, actually what's very interesting, what's happening behind the scenes is that many Fortune 500 companies are running numerous bake-offs to compare autonomy levels. So these Fortune 500 companies have started to realize that autonomy levels matter. And so they'll just do things like running a private competition to compare the performance of different systems. Or they might do things like shipping you a box with goods and tell you to, roll the camera, no cuts while you open the box, put things in front of your robot and see how the pick and place goes. And they won't even tell you what's going to be in the box, because they start to understand now that the ability to generalize, the ability to deal with a wide range of items, even unannounced items, is really what matters in warehousing, because that's how you're going to achieve good performance. And so they understand now to not give you too much information ahead of time to truly test the AI capabilities of the robots they're evaluating. And so you could ask the question, will autonomy be achievable anytime soon? Let's say 3 nines of reliability to be economically viable, or, are all these robotic manipulation efforts in for many billions of dollars of expenditures and counting, like the self-driving companies have had so far in costs? Well, my strong belief is with the right team and effort, this is actually achievable. And I mean, a big part of it is, of course, that 3 nines is not enough in self-driving. Self-driving needs many more nines of reliability before it's viable. And so 3 nines can be achieved more quickly than many more nines. And so that's a big reason why I think we're going to be getting there in robotic manipulation much sooner than self-driving, reaching the autonomy that's required for economic productivity. And in fact, one example you might have seen if you follow Covariant at all is this video from now almost 2 years ago already. This is recorded in a warehouse in Berlin. And this robot is doing autonomous pick and place. This is fully autonomous. And in fact, what you're seeing here, it's a 10x sped up video, but if you, were to watch it in real time, you would have a 1 hour long video uncut showing the actual capabilities of the robot. And anybody who works in robotics knows that it's much harder to have a 1 hour long video that shows good performance than a 30-second highlight that shows good performance. But also the 1 hour video is actually what you need. It's what you need to understand, is the system reliable? What can it do? And so that's what we started doing at Covariant, is to release longer running videos than you would typically post as a highlight on, when somebody lands on your website, you want to see the 10-second highlight. It turns out not to be that informative compared to long running videos. And so this is an example of what's becoming possible now. This is doing order fulfillment for electrical supply in Berlin, where electricians will put in their orders the night before, and then in the morning, they'll get a delivery and they'll take their supplies to their job site and start installing whatever they're installing that day. So what it has to do this is close the perception action loop, and that's where all the challenges are. And this is where things are so different now from what used to be, the traditional approach, or still is a traditional approach, and now, old approach to robotic automation based on pre-programmed motions. And what you need to deal with then as a robot is things like this. So what you see here is different totes from a warehouse. Sometimes they're single SKU bins, sometimes they're multi-SKU bins. Sometimes these bins are compartmentalized. And ultimately, the task of the robot tends to be pick out one item at a time reliably. And if you take a step back and think about what needs to happen behind the scenes to make this possible compared to what was done in the past with pre-programmed motions, turns out learning is at the core of what's happening at Covariant, and I imagine it's at the core of what's happening at pretty much any other company that's making significant progress on this. And more specifically, deep learning, which we all know at this point, exceeds the performance of older learning approaches, because the more data you pour into these large neural networks, the more they learn, and they keep learning as you feed them more data. The question then becomes, well, how are you going to feed the data? There's actually quite a few different approaches that all matter to get the best possible performance. So I'm going to give a quick highlight of how deep supervised learning is playing a role in this, how simulation is playing a role in this, deep unsupervised learning, and deep reinforcement learning. I might remind you a little bit of Animesh's talk, where he said a lot of things need to come in place for all this to take off. Well, all 4 of these matter to build reliable robotic pick and place systems. So deep supervised learning, how could that play a role? Well, I mean, what is supervised learning? Your neural network takes in an input, for example, an image, and then outputs a decision. For example, cat versus dog versus train versus car and so forth, if it's a kind of classical computer vision benchmark. But now in a robotic manipulation setting, you probably wanted to somehow output something related to robotic manipulation based on what it's seeing. And so what might be providing as labels, and then the neural network should learn to predict on its own? It could be segmentation, right? If the robot can segment the scene into its component pieces, that's great, because now it can understand where to maybe put a gripper or a suction cup and make sure it picks one item, not two items. Or if it's a larger item, it can put multiple suction cups because it understands it's one item and that whole surface area is belonging to one item. You might care about the 3D. So you might, and Steve, of course, talked about 3D understanding of scenes. That's critical for robotics. Otherwise, the robot doesn't know where to go. Now, you might wonder, how do you annotate 3D? Well, one way to annotate it, which we can get to later, is through simulation. If you have simulated scenes, you know the 3D. In the real world, you can also annotate with 3D cameras, but of course, then you might ask the question, if we can use a 3D camera to annotate, why learn if we already have the 3D camera? But it could still be often good if you know that your system is going to be learning and wants to exceed the performance of existing 3D cameras. You could supplement it with data from existing 3D cameras, in addition to getting other data that maybe you generate in simulation to get a more capable system than any existing 3D camera can provide, because the existing cameras often rely on projecting light onto the scene. You project light onto the scene, you can get weird reflections, complicated to process, and then these existing 3D cameras often fail. Another thing you might care about is grasp points. And so a third example of how you might want to supervise this robot or the neural network that's powering the robot to make decisions. And you might say, maybe grasp point is the thing you ultimately care about. Why bother about segmentation and 3D prediction if all you need is grasp points? Well, you could use the others as auxiliary losses. And actually for grasp points, if you're annotating in 2D, you'd still need the 3D recovery to actually execute on it. In practice, what it comes down to is mining the real world long tail of hard cases. It's actually fairly straightforward. Anybody who has a bit of AI experience, let's say, even a first-year AI PhD student, can probably set up a robotic grasping system that will allow them to record a 30-second video that looks good. But getting something that actually works reliably is very, very hard. And a lot has to do with collecting enough data, the right kind of data, and then making sure you architect your neural network correctly, that it can absorb all the information from that data. So you might wonder, what about labeling the data? How are you going to get this done? Turns out there's a lot of companies doing this. You can also do it in-house, of course. These companies make a lot of money. I mean, many of these companies are billion-dollar companies. So you can imagine that this is a big business. It's a great business to be into. You can also imagine, as a company that collects it and needs to get it labeled, that it could be a cost factor that you might want to reduce a little bit and not just rely on supervised learning to train your neural networks. So the other 3 bullet points here are how we can get away from just supervised learning and have other signal we can bring to bear to teach neural networks how to do robotic manipulation. Simulation is an important one. There are ever more realistic simulators being built, and the more realistic, the better. But also, surprisingly, sometimes somewhat unrealistic simulation can already lead to meaningful training data. And so a good example from now a couple of years ago was this work on domain randomization, which was done by a group at OpenAI that I was part of at the time. And what it showed is that even though the training data on the left is not that realistic looking compared to the real world scenario on the right, just training on this somewhat unrealistic training data is good enough to learn to localize objects in real world images and then actually also do pick and place. So what we did then was we had this robot trained purely in simulation to, in this case, it was trained to identify grasp points in simulation and then was deployed in the real world without any real world training, was capable of doing, of course, in relatively simple scenes in this case, just one object at a time presented to it, and it doesn't work 100% of the time, but it works surprisingly well, showcasing that there is a lot of interesting signal, even in, let's say, medium realistic simulated environments. So deep supervised learning, simulation. Of course, the beauty of simulation is that you have automatic labels. If you want to extract a segmentation of a scene in simulation, you have it because you generated the scene. You want to extract 3D, you have it because you generated the scene. You want to extract grasp points that you wouldn't have directly, but you could simulate and see what happens when you grasp. Now, deep unsupervised learning is another component that's proven critical to us to get the best possible AI systems to work. And the idea there is that actually you're going to do something very much like supervised learning. I guess it's only spelled with two letters different. The U and the N are the only difference. You train your neural network, and you will still have a real task on your neural network that you care about. Maybe 3D prediction, segmentation, grasp point prediction. But in addition, you have another head to the neural network that is a unsupervised task. And unsupervised really means, in this case, the same as supervised in pretty much every possible way, except that the output you're trying to predict does not require human effort to provide. So there'll still be an output to be predicted here. For example, the next frame in a video, or if it's text, the next word in a sentence, which is exactly the same thing as they do in supervised learning. So the same neural network machinery can be brought to bear. It's just that the supervision is automatic, and that's why it's called unsupervised learning, because there's no human supervision required to generate data for the top branch of the neural network. And the hope is, of course, that by training with a lot of data along the top branch, that the shared part of the neural network will learn something very interesting that then allows you to in turn train that second branch at the bottom from a very small amount of data, yet do really, really well. And that's where unsupervised learning would shine, is you might have 10, 100x, 1,000x, 10,000x more unsupervised data to train most of the network, and a little bit of fine tuning on the real task, which requires human annotation and hence is more expensive to get data for. So for something like robotic manipulation, what might you do? You could say, well, this is a scene of a bin. We could blank out the middle part here. And now when you look at this, well, if you think about this, you say, well, this Band-Aid box will probably continue here, even though it's blanked out. This pill bottle will probably continue. You can even imagine what that would look like. This orange cap would continue. This toothpaste here would continue. This pen pack would continue here. You see some plastic covered cardboard here, right? Then another pen pack in the back that would continue. And so when you think about this, as a human, you can complete this. And that's interesting because what that means is that you understand enough about this bin to mentally fill in the picture. So if we can now train neural networks to do the same thing, that is effectively instilling onto these neural networks an understanding of what bins with a bunch of items tend to look like. And by doing so, we would be training the top branch in this network. And after we train long enough, we could then train on a small amount of data on things like segmentation, 3D, grasp points, and so forth. The things that require human annotation and hence are more costly to collect data for. Now, you might wonder, well, asking a neural network to predict a patch isn't that hard to do. Well, one patch, let's say 16 by 16, has 10 to the almost 2,000 possibilities of how it could be filled in. It's a lot less atoms in the universe, and there's a lot less words in the English language. So even though for language, it's not too hard to fill in a word, a neural network easily can output, a softmax with 1 million possibilities. It's a little harder to have 10 to the almost 2,000 outputs on your neural network. In fact, it's just impractical. So, in fact, success in computer vision with unsupervised learning has come later than in natural language processing. Nevertheless, as of 2 years ago, it's become quite successful. The sequence of papers, Contrastive Predictive Coding V2 from 2019, late 2019 was the first paper to have a real success here. SimClear from 2020, actually out of Jeff Hinton's group at Google in Toronto, and then MoCo out of Kaiming Hayes' group at FAIR. And these are all very related. I'm going to explain the SimClear version, but think of them as sufficiently related to not worry too much about the distinctions. So what you'll do is you'll say, I'm going to, instead of trying to fill in an image, I'm going to train a neural network to learn what makes an image similar or different and learn to embed image information. And so here's an original, a picture of a bin. Here's another original, original 2. 2 different originals, both get duplicated. And then all the duplicates get processed by the neural network that is to be trained. It's to be trained such that if the duplicates came from the same original, they should attract. So the resulting embeddings should be close together. Top 2 should be close together. The bottom 2 should be close together. But if they come from different originals, they should repel. So the embedding should be far apart. There are some subtleties here on how to set this up. If you do this just in Euclidean space, it might not work so well, but it was set up as essentially an info-NC softmax type loss with actually a lot of negatives and a small number of positives is typically how this is trained for each loss term. But this is the main idea. You somehow transform originals into duplicates, let those attract to each other, and have duplicates come from other originals repel from that. This is the loss that's used. The details do matter to get this to work, but probably these days you just use an existing implementation, but this had to be figured out to make it work. And so we want a classifier loss effectively to say that duplicates from the same original have a high inner product with their embedding vectors, and it's normalized by inner products, exponentiated inner products coming from negatives, duplicates coming from different originals. The key result there was that if you looked at performance on ImageNet, supervised performance was at a little below 80% at the time. This is training a neural network, fully end-to-end supervised loss. Then SimClear was trained in this unsupervised way, learning to embed, and then it was given one layer, one linear layer to train on top of that. And if the network was large enough, horizontal axis is size of network, if the network is large enough that you train unsupervised with this contrastive loss, just a linear classifier on top of that can do as well as training a full network end-to-end supervised. What this suggests is that somehow in this unsupervised way, you're extracting the right kind of features to then easily learn image classification in this case. In fact, Jeff Hidden at the time tweeted about this. Unsupervised learning of representations is beginning to work quite well, in this case, without requiring reconstruction. What can NLP trends tell us about vision? In vision, this is still the earlier days. In NLP, what we've seen as the main trend is that the larger the network, the more data, the more performance improves. So likely the same thing will happen in vision, and it's starting to happen. If you collect more data, train larger networks, and performance will improve. In fact, it's been done on some private data sets. Facebook trained, I believe, on 1 billion Instagram images in an unsupervised way to then complement with fine-tuning on ImageNet, which does better than only doing unsupervised learning on the million ImageNet images, followed by fine-tuning a linear classifier on top of that. So we got deep supervised learning, simulation, and deep unsupervised learning. The last component I want to hit upon is reinforcement learning. Reinforcement learning is about trial and error learning. It's where a robot is going to perceive the world, act, and learn from those consequences, and hopefully improve performance over time. We've actually seen a lot of fast progress in deep reinforcement learning in the last almost 10 years now. I would say the big result that made everybody think about deep reinforcement learning was in 2013 when DeepMind showed that a deep neural network can train itself to learn to play a wide range of Atari games. This was a very surprising result at the time. Reinforcement learning results tended to be on very toyish problems. They would not use visual inputs. They would use very compact state representations as inputs and typically be on grid worlds. But they show they can be made to work on a wide range of Atari games. And under the hood, it was a convolutional neural network, much like the neural network used for the ImageNet breakthrough AlexNet, but in this case, outputting joystick actions rather than outputting classification labels. In addition, it was trained differently. In the ImageNet result, it was trained with supervised data to match the classification labels that were provided. Here, it was trained through trial and error learning. So initially, the agent is playing the games quite poorly, but over time, it learns from seeing when its score goes up, when it doesn't go up, to reinforce the scenarios where the score went up and become better and better and better at playing these games. The most famous result is probably the AlphaGo result, which was a combination of supervised learning at first, where there was training on human games for a given situation, what's the move a human player would make. And after a good amount of supervised learning, there was reinforcement learning, fine-tuning. Through self-play, the neural network improved its performance and then ultimately actually became good enough to beat the human world champion. While DeepMind was focused on reinforcement learning for games, a lot of the work we did at Berkeley at the same time was focused on reinforcement learning for robotics. And what we're watching here is actually reinforcement learning in action. So initially, this robot is falling over, but over time, it becomes better and better and better at making forward progress, which is what it is rewarded for. And after 2,000 updates to the neural network, it's capable of running. And you can then run the same algorithm on a 4-legged robot, it'll learn to run, or on this 2-legged robot, where now the reward is for how high the head is, the higher up the head, the better, and it learns to get up. You can also do this on real robots. So this is Brett, the Berkeley robot for the elimination of tedious tasks. And here it's learning to put the block into the matching opening. It's learning both a vision system and a control system together in one large neural network to complete this task. And in about an hour of training time, it learns to do that quite reliably. And then maybe on the robotics end, the kind of recent most famous result is the Rubik's Cube manipulation that was done by OpenAI. And so what you see here is not the training. The training has already happened. But after the training is completed, the learned policy is run, and you see it's actually capable of solving this Rubik's Cube. It takes a couple of minutes, so I'm going to scoot forward a little bit. But we're watching this in real time, and it only takes something 5 minutes to solve this Rubik's Cube. The training here, interestingly, was done all in simulation, which is very surprising, right? That you can fully train in simulation, yet solve such an intricate manipulation task with a lot of contact forces involved, which tends to make it very hard to simulate this correctly. But actually, the trick was to not worry about simulating it correctly, but instead building a wide range of simulators and training a policy that could solve the Rubik's Cube across all of those simulators, and hence was robust enough to then also function in the real world. So one of the things that you might wonder about is the sample complexity of reinforcement learning. Even though the final results are often very strong, it can take a long time to learn. And I would say that's not a problem. I mean, if you want to do 100% reinforcement learning, you might say, okay, that's a problem because I want to do everything 100% with RL. But if you're willing to bring in some other methods, like supervised learning, simulation, and unsupervised learning, you can think of RL as providing that extra training that kind of happens for free. You just let the robot run and let it improve itself. It doesn't need to invent things from scratch, because you can provide supervised learning to bootstrap from and get a reasonable performance already to start out from. You can run things in simulation where it might not be as expensive to collect experiences. And you can augment your RL agent with unsupervised learning, which actually has seen some pretty interesting breakthroughs in the past year. So if a little over a year ago, you would go check on state-of-the-art learning curves for reinforcement learning on these DeepMind control suite environments, you would see in blue a learning curve that is an agent that gets access to the underlying state. In green, a learning curve when the agent has access to pixel inputs only, but doesn't get to observe the underlying state. And your first reaction might be, well, that makes sense. When you learn from direct access to state, you've been told what is essential, what are the variables that matter, and you should be able to learn more quickly. Yet at the same time, when you look at the pixels, even though it's high dimensional and it's not giving you the exact information in the smallest number of variables possible, it still has the information. So you could also question this. You could say, well, if in parallel to do reinforcement learning, I can somehow very efficiently learn a great vision system, shouldn't I be able to bring these two learning curves, green and blue, closer together? That's actually the research problem we set out to resolve. And what we did, we actually brought in ideas that I presented earlier, the SimClear ideas, into reinforcement learning. Remember that there would be two originals. You make duplicates of each one of them. You have an attraction and a repelling force to train the neural network to generate the right embeddings that capture the essence of what you're effectively looking at. Well, you can do the same thing in reinforcement learning. You typically generate a replay buffer from your experiences, you pull observations, and then you generate augmented observations. And if they come from the same original, they should attract. If they come from a different original, they should repel. The neural network encoder is trained this way, largely, in addition to then, of course, going into the actor and critic loss of your reinforcement learning agent. Actor loss is the policy, the critic loss is the value function. If you set this up right, you can actually bridge the gap pretty much. So what you see in gray here for 16 different DeepMind control suite robotics environments, in gray, the learning curves with direct access to state, in red, the learning curves with only access to pixels. And we see the red curves almost always match the gray curves, showing that by combining unsupervised learning with reinforcement learning, we can actually learn as efficiently with pixel inputs as we could with direct access to state. You might say, why do we care? In simulation, don't we always have direct access to state? Well, in research, a lot of experiments are done in simulation because it allows us to learn the lessons we want to learn. But of course, the real value is in the real world. In the real world, state is often not accessible, not available to us. And so what this shows is when we now go to real world, we can learn as efficiently if we only have pixels as inputs and not have access to state, making it a lot more practical. Similar results in the Atari games, where by combining, the approach is called curl, in this case curl rainbow, because the RL approach is called rainbow, that is building up on combining with the curl unsupervised learning approach, achieves state error across a wide range of Atari games that are kind of the standard small suite of tests, outperforming prior approaches because it's so efficient at absorbing, really learning from pixel inputs compared to prior work that more directly learns from reward signal, which tends to be sparser. Okay, so to summarize, I started from this picture on the right here, saying that, okay, the next generation of robots will be powered by more intelligent software, AI software rather than pre-programmed motions. The robots will have to see, understand what's around them, react to that. And what will power that under the hood is going to be deep learning. And the key kind of trend for deep learning is the more data you feed into your neural networks, the better the performance. And that's kind of the magic and the beauty. At the same time, of course, you need to have that data available. And so there's a range of opportunities really to collect such data. Deep supervised learning is where we're willing to label the data. It gets tedious as a human to label data, so you might not want to do it for too much data, but it's very effective when you have the time to label. And so key there becomes mining hard cases. And that's actually where things get interesting as you build a company, because the hard cases, you tend to find them by deploying in the real world. That's how you get access to the interesting hard cases, and you need an interleaved approach between learning and deployment. Make sure your deployments are great, so they're popular, so your robots can collect a lot of data in the real world, which allows you to mine the hard cases and keep improving their performance. Simulation can play a big role, and I think the most surprising thing of the last few years is that simulators don't need to be super realistic. If you randomize what you do in your simulator and you have enough versions of your simulator, a lot can be learned already from that. Deep unsupervised learning has been the driving force behind all the natural language processing breakthroughs in the last 4 or 5 years. It's also becoming a driving force behind computer vision, state of the art. And so especially contrastive learning is becoming key to learn the best possible perception systems. Deep reinforcement learning is key to ultimately have the end-to-end training. You want to optimize end-to-end performance. You want your robot to maximize symmetric, and reinforcement learning will directly optimize for that. Nothing intermediate like human annotation or unsupervised losses, directly what you care about. But to make it effective, you want to combine it with this contrastive learning, which effectively recovers state for you without you having to instrument anything or somehow learn a mapping directly onto annotated states. So what does that mean for us at Covariant? Here are the kind of 3 families of major opportunities we are deploying robots into. The first one here on the left is order picking. So that's what we're seeing in action here. These green totes come out of a automatic storage retrieval system, get brought to the robot based on whatever was ordered, and the robot picks and places into a shipping box, which then can be shipped off to the customer. Decanting is the opposite. So decanting is where you receive new goods that you want to store in your warehouse, and you would then effectively open the cardboard box and take things out of that box that you received and put them into your storage totes to be stored away in your dense ASRS system. The second one here is parcel induction, and a variant of that that's not shown here is apparel induction. But what you see here is essentially parcels come down a chute, which is a pretty common situation. But you don't want this massive parcels on your conveyor system. You want these parcels to go through your conveyor system one at a time. And so that's, again, a hard problem because you're faced with this mess of stuff, and somehow your robot needs to make sense of it, pick one item at a time, never put 2 in a slot, and also not leave any items behind. Turns out in the apparel space, something very similar has to be done, where individual apparel items need to be singulated and put into a similar kind of conveyance systems as you see here. It's often a little different because the conveyance system for apparel often also has a bagger system as part of it that will bag up the apparel and put a shipping label on it. And then there is put wall and kitting, which are very related use cases. What you see here is put wall, but it's essentially the same thing for most practical purposes. So what you see here is a robot that, again, through a conveyor system is presented with items. In this case, in the put wall use case, what's typically happening is it's actually a warehouse with very little automation. And so what will happen is a person will run around the warehouse and will collect items into a bin. And those items will constitute maybe 100 orders. And then we'll put that bin on the conveyor that goes to the robot. And then the robot will pick one item at a time out of that bin. But these items are from 100 orders. So now each cubbyhole in the shelf behind the robot will correspond to an order. The robot will pick out one item at a time, barcode scan it. That's the red flash is what a barcode scanner tends to do. Then it'll light up the correct cubbyhole. The robot will put it there, then go to the next one. And so over time, each of these cubbyholes will become a complete order. Maybe somebody ordered 5 things, and once that cubbyhole has all the 5 items, it'll know it's complete. And on the other side, things get taken out and put into a box for shipping off. Kitting tends to be when this is done in a kind of more, typically it's not on a per customer basis, but there's a notion that you always want one of this, one of that, one of that, one of that, and that together forms a kit of 5 items that is a type of kit that you want to ship off. A put wall is the kind of higher variance version of this is one way to think of it. So these are the use cases we're deploying our robots into today, or the main use cases we deploy into. We're always expanding the use cases. And these are actually super helpful to fulfill all the orders that we're all making online when we just click on something and all of a sudden next day it shows up at our door. A big part of the process is the pick and place in the warehouses. Now, I showed this video earlier. This is the real life version of order fulfillment. The thing I'd encourage you to pay attention to is the blue bin. The range of items, and you saw there plastic baggies, those are going to have weird reflectances. It's very hard to fully see the 3D of those for those kind of scenarios. But again, neural networks that we have been trained to understand that and even understand with objects never seen before. So these objects have not been trained on, but the neural network has been trained on enough objects that when it's faced with new ones, it still understands this very general concept of what does it mean to pick one item at a time. And that's really what it's learning, how to pick one item at a time out of a bin across any range of SKUs it might be encountering. This was done in a partnership with Knapp. We also worked together with a company called ABB, one of the world's leading robotics manufacturers. And here's an example of actually what they did. I mentioned earlier on, a lot of these companies will run bake-offs. So ABB ran a bake-off where they said, we're going to present items to your robot and it needs to pick them one at a time, leave nothing behind, never pick 2 at a time. do this at a high pace, and we'll compare you with 10 plus other companies, and then we'll partner with the one who has the best robotic system, which in this case was us. And so that's how we ended up partnering with ABB. And that's pretty common these days, is that these companies will do explicit comparisons, understand who can actually deliver on this beyond, let's say, a marketing brochure that's easy to put together. So with ABB, we're working on parcel sortation, which is shown here. We're also, here is actually a video that ABB made showcasing this in action. And so what we do is we provide the brain behind this, and ABB provides the mechatronics. And so for us, things come in through the cameras. We then send commands to the robot, and then from there, ABB takes care of everything around it to together provide a fully working system that the customer actually can rely upon. Here's another example. Here, it's this is a typical scenario for apparel induction. You can see there's a bunch of apparel arriving there in this tote. Robot needs to take out one at a time, place it onto that. Essentially, it's a pocket induction system. So it's bagging it up. It's being pushed into a bagging system into that slot where you can't see it anymore. And then things can get shipped off from there. And again, the big challenge here is to reliably pick one item at a time at high speed. And of course, if you pick two items, you induce a cost. If you don't detect it, somebody will get to it. They might be happy, but it also means that you lose money as a seller. So you want to do this at extremely high reliability as well as at high speed. And the SKUs will always change. The t-shirts that are sold today, the shirts sold today will be different than the ones sold tomorrow. They'll look different. You cannot train on any one of these specific items. Your system would be too specialized if you zone in on specific items. You need to train a much more general pick and place system. Oh, so in fact, I think that's it. Yeah, that was the last slide. So thank you, everyone, and open to questions.
Wonderful. Thank you so much, Pieter. That was great. Fantastic. I think what we can do after the applause goes away, just I'll check with Aiden, our all tech. Yes, it's quite the feature. Should we move to the panel discussion now? Okay, welcome everyone to our second panel discussion of the day, which I think I said was at 5. It's 4 p.m. Eastern. I'm just confused. At the hour, as Pieter said, is really the way to think of it. Not in terms of time zones. I'm lost. Okay, so I have a set of some discussion questions to seed our conversation. And as well, I will attempt, if I can, to take a couple of questions from the question box, the chat box as well. So if you have a question, please feel free to ask. And you can also upvote questions in the box as well. So you can click on the question to upvote, and the upvoted questions will come to the top, which makes it easier for me to see. So kicking off, all right. We'll maybe ask the panel in sequence, starting with the industry folks, or folks who have been involved in industry. If we're going to draw parallels with autonomous driving, there's a lot of innovative problem solving happening in the manufacturing and logistics industry right now. And part of this could be because just to even figure out what the problems are, you need to have access to large scale infrastructure to generate and log everything, and then to even discover what the long tail issues end up being. Actually, do you think the manufacturing and logistics industry is going to follow autonomous driving in this respect, or well, maybe let's just start with that. Do you think that industrial robotics and manufacturing and retail is going to follow the trend of autonomous driving of these massive deployments? And maybe we'll start with Pieter, just because I put him on the spot since he just talked about it.
Sure, yeah. I think, can you hear me okay, by the way?
Sounds great.
Great. So I think there's There's a lot of analogies for sure between the two. I think the only way to get to the reliability we want is by collecting a lot of data, collecting data in the real world, and having that data is a bit of a competitive advantage. So it's it's natural to keep that data to yourself. That said, I mean, in some sense, if you think about it from an academic point of view, and okay, now we're not able to participate, I wouldn't necessarily see it that way. I think really you could work on any problem where you try to achieve very high reliabilities, and you'll run into similar challenges, is my sense. And you could, yeah, maybe you wouldn't be able to do it inside a factory or inside a warehouse with the data coming there. Maybe you can't do it on a self-driving car because it's expensive to collect data there, but you can find other places where maybe you can more easily collect data and try to go through that same process of what does it take to get to more and more nines of reliability. And yeah, you'll run into the same challenges, I think. And it changes how you do things, right? Because you start looking kind of overall picture, what's the weakest link or what's the best lever to pull to improve things, as opposed to what's the most interesting algorithmic improvement I can make today.
Yep. Okay, very interesting. So based on that, I'm just gonna put Pieter on the spot to follow up with just one more question, which will then lead to the whole panel discussing, and then I'm gonna ping Sandra for a bunch of stuff on simulation, because that's coming up shortly as well. So Pieter, if I can ask, let's say you're trying as an academic then maybe to pick a problem where you can compete without having a huge set of robots doing tasks all day long. Do you have a strategy for picking those tasks? So I would ask you, as maybe putting on your industry hat for a moment, and then as an academic, do you have suggestions on what tasks maybe you would like to work on? And I'll ask the rest of the panel the same thing. How can academics keep industry interested by doing things that actually appear or hopefully are relevant to that 99.999% long tail?
Well, I mean, I haven't given this a lot of thought ahead of time, because I tend to do the work at Berkeley and Coherent pretty separated. But I do think, for example, for pick and place, you could probably get pretty far in an academic setting, just because it's about picking every possible item you could ever encounter. At some point, it'll start adding up. I mean, you'll probably want to buy only cheap items and maybe items you can return and so forth. But you can probably get reasonably far and already encounter a lot of the challenges that you would encounter in industry. I think similarly, if you have, let's say, a navigation robotic system, maybe with cars, it's hard, full cars, but if you have smaller robots that would go around, let's say, campus and buildings, I think you can encounter a lot of the challenges related to, okay, running across people, how to navigate that. It'd be hard to maybe get to the same scale of data collection, but maybe a bunch of academics could get together and you could have 20 universities contribute mobile robot data from their 20 campuses or 20 buildings or whatever is the setup. And I think you can get to reasonable scale. Probably not industry scale, but I think reasonable scale to run into many of the main challenges.
Okay, thank you. That's actually a great suggestion of a collaboration. I guess just a question of who gets first author on the paper, maybe. But nonetheless, but yeah, very, very good. And I think Animesh might have a thought about also how you, what you can solve. I'll move to Animesh just to follow up with the same question, maybe coming at it from both the NVIDIA perspective and also from the academic, wearing your academic hat.
I think one thing that I definitely agree with Pieter on is when you are going to build any practical system, the long tail will, at least by design, only be discovered through data. If you could discover it a priori, then you would already build it in. It's this sort of chicken and egg kind of problem. So one takeaway is deployment in real application or real system, like the full system is necessary. Now, of course, in a resource constrained setting, whether you are a small or medium enterprise or an academic setting, you probably are facing similar challenges. You just cannot buy an Amazon warehouse full of goods. you need to be ingenious. Let's put it that way. I think Peter suggested this idea, right? You can buy a lot of things and return them, or collaborate with people. But nonetheless, I think this engineering effort of building the system is needed, which is something that I believe often sort of people turn away from because of the upfront cost it requires before, like this collaboration is a very good example, the mobile robot collaboration, right? And it will go on for 18 months before the first paper appears. Whoever is the first student on this side is risking a lot before anything appears for them. And I think this is the kind of research as in academia we need to at least encourage to ensure that students can take up such projects, so that we are at least ensuring that students are solving relevant problems rather than making up problems just because.
Okay, very well said. Very well said. Yeah. So I'll actually maybe transfer to Hani and then to Goldie to also address how you think it's easiest for an academic to stay relevant to industry by presenting unique opportunities or unique problems where you can make progress for that long tail. I'll start with Hani, but just before that, I'll just mention that also for folks working in robotics, I think many of us are very familiar with Dollar Store or Dollarama. Speaking of mass purchasing, you can get a lot of objects for a very cheap price. I'm in no way affiliated with any of those stores, but anyway, just as a note. Go ahead, Hani, take it away.
Thank you, Jonathan. So I agree with Pieter and Animesh as well about the we need to find the problems that are currently in the industry and how we can solve them using the technologies we have at the research level or the R level, and definitely it's always a question of whether or not we can apply it, and as I mentioned this morning, how is the technology readiness level, right? Because companies normally want a final product very quickly. When we start on the R&D level, we start really at low TRL, as we call it. And I think it's always this gap, which is not easy. I mean, I showed the curve, and we can always say, oh, we'll reduce the gap, but it's not easy because it's actually, we need to start from a fundamental and up. And then for industry, it's they want to have the results. So one particular thing we found it very useful is really looking at the problem statements and how to find from the industry and how to find solutions for our robotics and automation and autonomous systems. So it's more of industry pull in a way rather than our ideas, or we find solution and try to see what is the problem there. So that's kind of the way we found out is the most direct way to reduce that gap between industry and academia.
Yeah, very good. And I think we actually talked about this a bit in the earlier session as well, in the earlier panel about the idea of industry pull and how to actually, you actually talking to industry to figure out what is really needed. So maybe I'll hand it over to Goldie just to also chime in on the 3 nines after the decimal point in terms of how do we get there as academics with a limited budget, perhaps.
Yeah, I think maybe just not to repeat what everyone said already, but I think what we aim to do is bring the real world into our labs as much as possible. So that was the Dollarama example that you were giving. So as much as real world we can bring in, that would be the first starting point. And then to take our robots into the real world as well. So we need to have a balance between the two, I think. And right now, I think is a great time to do that because we do have, industry that's focused on the development of the technology, deployment of the technology, but then there's user industry as well. So for example, when we're thinking about, the retail market, there's grocery stores all around us that would love to test out the automation and see what it's like. So we don't have to have, every set of the technology developed already and it's not ready to deploy yet, but we can do testing in these in these sites, and they'd love to have us there, right? So I think we could do that being aware that we're a research lab with limited funds because everything is kind of just starting out right now, and we're doing proof of concept at this stage before we bring in our partners for collaboration of development and deployment of the technology at a larger scale. So it's a balance between, I think, the real world, bringing it to our lab, and taking our robots out into the real world.
Yeah, that's a great point. In fact, actually, I think that we do have stores all around that probably would be, yes. And I confess, I've never gone locally and said, hey, could we just try something out? So very good point. Yeah, very, very good. So I'm going to go to Steve to ask the same question, and then I'm going to come back to Sandra at the end, and then I'm going to hit Sandra with the second question. So go ahead, Steve. How do you get to 99.999%?
Well, and maybe I'm going to be the contrarian again. I think this is the wrong question. I think we're not the ones in academia who should be driving to 99.99. That's certainly for the startups and the large scale industry players that need that to make the products, right, and to make a market for themselves. I think what academics should be looking at are the capability enhancement or expansion that's going to change what we can do in 10 years or 15 years or 30 years, right? So, I saw some beautiful examples today of massive automation, but the robots themselves were picking up large packages, right? And everything was relatively flat, the surfaces they had to deal with. There wasn't a lot of interaction. There certainly weren't any videos with two hands going simultaneously, pulling apart a piece of Lego, for example, right? There's a long way to go. There's big choices that we have to make in the future about how we can solve these massive manipulation tasks that we can do as humans, but that would have huge value. Like, let's assemble a jet engine, right, without any human intervention. Let's do these low frequency tasks that change every time you do them, that humans can manage. Like, there's massive open space beyond this application, and you see by the number of entrants, you see by the amount of competition coming into these spaces. These, from an academic perspective, are almost solved problems. Let's prove we can solve them reliably. Let's argue about safety and how you quantify it. But then let's force our students to think about problems that we haven't even started on yet.
Okay, excellent. So Steve, you're advocating for not chasing the long tail and instead just switching to a more open domain, because that's an engineering task, you would say, I guess.
Yeah, when in doubt, look for the blue sky, right? Yeah, as opposed to the long tail.
Right. Yeah, that's okay. Yeah, no, very, very good point. Very good point. So maybe the juicy research topics are not in that long tail. Hard to say for sure. Which is perfect, because then I will turn it over to Sandra, who's actually had experience looking at the academic side, but knowing what motivates companies who are ultimately the recipients, I can't talk, of these products. Sandra, what would you say? Do you think the long tail falls within the bounds of what academia can provide, or should we be chasing blue sky ideas more?
I think it's a tricky question with Steve.
Just having a little trouble with your audio. So, sorry to. Oh, wait. It was just breaking up a little bit. We couldn't.
Better now?
No, it's still. You sound like a bit of a robot, actually. It might come. We'll let her. We'll let Sandra just check the audio quickly, and I can. Well, she can try it one more time if she wants to, or we can just move on to the next.
Can you hear me?
Oh, now it's great. Yeah, perfect. You're back.
Okay. All right.
And you sound human again.
With the AirPods, I mean, I keep resetting them. I'll switch to the other speakers if this keeps doing.
No, it's fine. You're great.
Anyway, yeah, I was saying, I think I agree with Steve that academia can look at blue sky problems, and if we look at and I think there is a place for both. In academia, right? So I think like academia can work on the blue sky problems. If we look at what happened with deep learning, for example, for the longest time, it wasn't working. It was a purely academic problem, right? And basically studying what works and what doesn't work ended up feeding into another domain, which is potentially, building CUDA and parallel computing algorithms and cuDNN, right? That essentially ended up accelerating deep learning. So knowing that is very useful, and the best place to do that is in academia. Now, that being said, I think it would be great, and it depends really on maybe the lab and the expertise, if also academia can look at long tail, in maybe collaboration with industry, I would say. Maybe that's not a pure academic problem, but maybe something that could be like collaboration. So that way, when academia is looking at long tail, they could find like the really harder problems that maybe are beyond the industry expertise to help solve those. So I would say, it's a bit of a balance. I don't think that this is a black and white. That would be my 2 cents.
Okay, yeah, very, very good points. Very good points, definitely. So try and maybe do both, and pick the quote unquote low-hanging fruit, if there is any, in both spaces, right? Okay, which leads into my next similar question, actually, a related question for Sandra to start with. I'll go back through the panel. Since we've talked about the idea of getting data, right, and Pieter's talk was a great example of simulation as a viable choice for data collection. For the panel, the question is, maybe starting with Sandra, with the experience at NVIDIA, with the portfolio of simulation products that NVIDIA now has, what is the role of simulation? Does NVIDIA perhaps, and for the panelists later, do you see simulation as being something where ultimately everything will be tested all the time, and we will actually, very rarely need real robots? I think Pieter has already alluded to some of these things. Or does simulation have a limited role that we'll always need lots of physical demonstrations in order to get things to work reliably at that 99.9999% level? Sorry, long question.
So I would say the former. So I think the idea with simulation is essentially getting as much as you can without having to go to the real world, right? And so simulation allows you to collect data for training models. It also allows you to train in simulation, right, with hardware in the loop potentially as well. And so what we're trying to achieve with simulation is making it essentially making the data problem in AI more manageable, and then making algorithm development more scalable. So essentially researchers or developers can rely, again, as much as possible on simulation, and then fine tune with a small set of data. On the other hand, what simulation also allows you to do is benchmark your capabilities, right? So what Pieter was saying, that potentially these Fortune 500 companies bring you a box of objects, can you pick those? And so maybe you want to be prepared to know what your deployments or robots are capable of doing, so you can try them out in simulation. And maybe a customer asks you, or maybe not, you just want to benchmark your capabilities internally. And so having that handy without going to the real world is very important. So I'm not, and the closer, like the more true to reality simulation you have, the better you can do, in the sense that you could deploy with as little or maybe no real data, depending on the situation. So that would be my 2 cents there.
Okay, excellent. So that, I'm going to ask Steve. Based on Sandra's response, I'm going to change the question just slightly. I'm going to go back to Steve, then Pieter, then Hani, Goldie, Animesh. Steve, if I change the question slightly, what's wrong with simulation, if anything, and will it ever be fixed? Obviously, there's nothing wrong. It doesn't need to be fixed, but yeah, what do you think?
Now you're asking the wrong guy here, in that I don't use
I've seen you
a lot, but it's all good. I'll take a stab at it anyways, and I do love being controversial on panels. That's one of my favorite hobbies. So I think simulation, what Pieter was saying is bang on, right? So what we've learned over the last few years is that really the issue is generalization and overfitting to a simulation that led to a lot of the early limitations in their use for RL tasks, and even similarly for perception tasks, where I'm more familiar in terms of autonomous driving, and that simply by making the system robust to the specific setting of one particular simulation, by making it deal with multiple simulations, by slightly tweaking the physics, by adding a bunch of uncertainty, by overwriting some of the images, this goes a long way to resolving those issues. I think the issue with simulation is that it still doesn't solve the problem of the long tail, right? You still, you can generalize to a lot of objects, but you still have to have imagined them first, all the scenarios that you're expecting to have observed. And you're still sort of in this learning paradigm where you're only able to deal with situations that you can either predefine or pre-compute or somehow pre-imagine, right? And so I think perhaps that combined with the unsupervised approach and the large-scale data approach, right, that may end up getting us to a point where our robots are general enough to actually deal with all of these tasks as they arise. And I think some of the biggest indicators there, the ones that are most interesting, are the ones where we see these new tasks arriving that, the robot clearly has not seen either in simulation or in old data, right, that it now is able to handle. So I think that's really pointing a direction that's quite exciting.
Interesting. Okay, I'm just going to jump Pieter in the middle because I know he's definitely seen both sides. Anything broken with simulation, and if so, will it be fixed such that eventually we never need, well, not never, okay, that's too strong, rarely need a physical system? Can we get to that stage with simulation only? Arguing against Steve or for
rarely
Steve.
needing a physical system. I mean, that's going to be a tall order for the simulator builders, but I mean, it'd be nice because obviously in simulation, if you make a mistake as a robot, it doesn't cost anything, just some compute cycles. But I think as Steve alluded to, you want to discover the corner cases, and they're very hard to discover in simulation because that means you built them into the simulation, and then you don't need to discover them really. So I think ultimately the ideal model would be, well, the ideal model is all simulation. That makes it easiest. But the more realistic ideal model would be you detect the new scenarios in real world, the simulator automatically takes in that real world data, generates simulated scenarios that are many, many variations of the thing you just ran across. And then you can train in simulation against those many variants of what you run across in the real world. And so closing that loop back from real world to simulator, but the simulator would expand it. It wouldn't just like take that one thing, but it would somehow understand that that's one instance of what it could generate, maybe even 1 million instances of the same type with slight variations. I think that would be pretty ideal and would be a big step forward. And I think that's often what we do in practice, right? Something doesn't work in the real world, you then start fiddling with the simulator, set it up in a different way to also capture that part. But if that could be automated, that'd be great.
Interesting. Okay, so automated discovery of corner cases or something in the real world, ported into sim immediately for fixing. Very interesting. Okay, excellent.
Yeah, and then testing,
yeah,
right? As Sandra alluded to, then once you have enough cases in your simulator, you can run a lot of your just regression tests against the simulator. At least if it doesn't pass there, that's already a problem. If it passes there, you might need more, but it's a fast first test.
Right. So yeah, sure. Litmus test for the beginning. Absolutely. Okay. So Goldie, then perhaps, since you mentioned going out into the real world, actually getting robots out there and also bringing objects and real world items in, do you see simulation as still lacking? Do you think there's things that we're going to miss if we don't get out in the real world?
I think in terms, maybe echoing what Pieter said, but maybe thinking in the long run in terms of the environments we're looking at, because the challenges get bigger as we look at no longer flat surfaces moving in kind of indoor environments, structured environments to now unstructured environments. And that's where our real challenges between simulation and the real world need to be better modeled right now, right? So our simulators are great. We can pretty much model, a fixed, let's say, set of environments that we want. But if that terrain changes a little bit in one direction or another, or the surface profile changes in any way, then we've lost our control really of a robot right in the real world. So I think there's a lot of factors, especially if we're thinking of outdoor versus indoor, that we have to consider, like weather, like I was saying, terrain and so on. So we haven't gotten quite to that point that we could model all that, right? So I think it's not only just the data that's coming in, but how well are we modeling the robot as it's moving through its environment? And the complexity just gets worse and worse as we go into these complex environments. So I think we can't handle those yet, but we can, of course, handle the test cases pretty well. So we do have to consider an abundance of information from the robot design and the interference between or interaction between its environment before we get to those, that we can just put everything in simulation and hope that it can learn, right, for the real world.
Yeah, very good points. I'm going to ask Animesh, and Hani, I promise I'm going to get back to you as well, but I'll ask Animesh next, but I'll also mention that Goldie brings up a good point that, of course, we're not building robots for this at the moment, but if you ever watched the TV show like Deadliest Catch, for example, humans are pretty good at picking live crabs while they're moving on a ship deck that's pitching and rolling in the rain at night. So it's pretty, we have a long way to go. Maybe Sim's not quite there yet, but maybe one day soon. Okay, Animesh, any thoughts on simulation? Recent with the cutting sim, for example, you've shown that, right, you can simulate some of these very difficult things. So
I think the main thing to realize is this: what roboticists or computer scientists think of simulation versus what graphics people think of simulation has a 10-year gap. That's one, right? So graphics people are thinking of simulating phenomenon, while roboticists are thinking of usable system that is easy to plug into, let's say, a robot utility framework that they are using, right? And the phenomenon that we are able to simulate reliably, that are available in any simulator, whether it's NVIDIA or DeepMind or someone else's, is actually very, very limited. Like if you went to a graphics person and said, "Is this graphics research?" and they say, like, "This is 1992 kind of thing." Right? We are not doing this, and the kind of things that is considered research in simulating physical phenomena is actually still very hard, still not very fast, and all of the properties that we need, like general purpose, in the sense that I want to be able to have rigid body collision, but I don't want just this scene. Arbitrary objects should work, that kind of stuff. That kind of generalization, even in simulation, currently doesn't exist. So what we have seen so far, at least this is my observation, that if you can build a system that can do a task in the simulation, there is a very good chance that the real robot will work in near time. Usually that has been the case. I'm not saying that is the requirement. There are one-off cases elsewhere, but I can give you a few examples that started out like this, which were before that supposedly very, very hard, but somehow it is not, right? It's like legged robotics is one example. It's a combination of the robot itself getting cheap. I remember when I was in grad school not too long ago, very handful of people worked on legged robotics. Why? Because it required so much of what you would say domain expertise. We never tried it. It was just too hard. Now we are fairly certain that you can train with enough domain randomization, and you don't need anything fancy on the system. You just put it and it will work. So that's one. Simulation is definitely valuable, even if it is not realistic, as Pieter said, in warm starting things. I think there are algorithmic ideas of what people are working on to make simulation useful enough to generate long tail without actually seeing the observation, right? Folks working on causality are looking into this. Basically, it's a combination of generative models or unsupervised learning with simulation, where you are trying to say that there's a good chance that the unicorn never actually exists and it will never be observed. But can I actually build a system that will not collide into a unicorn if it ever were to see it, kind of argument, right? So you could do that. So that in principle, you could guard the system against such black swan events. And and the one final thing I think that is a more of a practitioner's tale is, at least the simulation as it exists, it has been shown that it is neither necessary nor sufficient. there are many cases where we have shown domain randomization to work, and it is sort of something that many of us do, including myself. But at the same time, I have also done works where we have explicitly shown do however much randomization you want and will still fail, kind of thing, provably. So that space right now is an open question from a research perspective itself. Because simulation itself is just a functional model that we use in, let's say, any sort of optimal control. Think of it just that the simulator is a black box model that is not differentiable in general. And in any case, we don't necessarily always know what is the quality and the fidelity of the model that you need to get certain levels or bounds of controllability and stability. So it works when it works, and sometimes it doesn't.
Okay, we don't know exactly yet. Although unicorn proofing, that's a hard. If you've never seen a unicorn, it may be challenging. But I guess if you have a generative model of unicorn, potentially it's doable. Yeah, at some point, if it's simulated enough. Okay, this actually. So I'm going to segue here, and I'm going to go back. I'm going to stay with Animesh just because he's speaking now, and I think he'd be a good question or a good topic for the next question. Pardon me. That is a question from the chat. I should also mention, if you would like to come up, you can actually come up to the front of the room to speak at the mic virtually by joining one of our 4 or 5 little panel boxes at the bottom with the people with their little hands up, the little graphics. You can step into those. I may not be able to get to all of you, but I'll try and get to at least 1 or 2 questions from if you step into one of those panels. There's one person there now, but I'll ask a question from the text question box first for Animesh to start with, and that is related to what we just said. Models. So simulations are effectively just models, right? Of course, maybe more than one in a box. Should we try to, I'm going to generalize, it's a question from Trevor. I'm going to generalize the question a little bit to beyond just Pieter, but to ask how much of the work you do in each of your groups or labs or companies is classical planning control. I say classical, like maybe with a reasoning or learning component, but planning control, symbolics, and how much is end-to-end? And should we just all be aiming for ultimately end-to-end learning without worrying about the intermediate, perhaps classical techniques? Animesh, go ahead.
I think I come from a school of thought where the sort of answer is end-to-end. But there is a nuanced answer. The nuanced answer is this. If you look at the last 30 or 40 years of algorithm and AI development, and you try to distill certain ideas that are key to AI, one of them could be probabilistic programming. Other one could be, let's say, symbolic or logic systems, rule-based systems. Another one is clearly gradient-based learning, essentially. And then the fourth one, I would argue, and this has always been true, it's just that sometimes we forget, inductive biases. So at this point, what I would argue is that when people usually use the word end-to-end, it's not as if I'm going to use a 3-layer neural network and the whole thing will be just a simple MLP and I expect it to do GPT-3, right? It's not true. What we find instead is domain-specific problems are being solved by particular kind of inductive biases. Language uses attention. Turned out attention is now useful for vision. Recently, Pieter students also showed that it is also useful for decision-making. So there are these components of what you would call structured inductive biases. Before this, there was this idea of resonance, basically long hops in information. I think what we need is structured inductive biases. What we have discovered in vision and language are good inductive biases. I don't argue, at least as far as I can tell, we don't have very good structured inductive biases for RL models. So far, if you look at like a lot of decision-making research in deep decision-making, I'm not going to limit it to RL because you could always argue like it can be deep planning or deep search. A lot of it is basically figuring out what is the update rule, not necessarily what should be the better architecture. On the contrary, if you look at vision and ML, vision and language people, a lot of the research actually goes into like how the information flows. I'm not singling anybody out or I'm not saying that there are no examples. I'm painting with a broad brush here. So I think the answer will be, I believe, and at least I would bet my career on it for now, that the answer will be end-to-end. It'll just not be MLPs. So a lot of research needs to be done on what sort of structured inductive biases you need for decision making. I think I'll rest there.
Okay. Thank you. That's a very, we have this on a recording as well, actually. So now we have you recorded saying that you bet your career on end-to-end effectively. That's what we're going to edit this clip to say later on.
But we do adaptive control. You do realize that.
That's true. That's true. That's very true. Very true. Very true. Yes. Okay. So I'll ask Hani maybe also. What do you think, Hani, about end-to-end learning, the effectiveness of end-to-end learning, or do you think we need to bake in more than just an inductive bias in the learning process, but maybe some more well understood and auditable perhaps techniques like classical planning, for example?
Yes. So like as mentioned as well by Animesh, it seems now we need to look at a new methodology actually for how to get these systems. So either, as you mentioned, learning to learning or other system. And I'm going also to comment on the previous component about how is introducing either simulation and modeling and so on will be of interest on this. And we're looking maybe, if we're looking closely to the robotics or more on the manufacturing side, we always need validation at some point of what we have and what we built. And so building physical models or building a system is of not only of interest to validate, but also we were talking also previously about how to get to really industrial partner and high TRL and so on. And that's really important. But given the new technologies, I'm going back to Steve's points, which is that we're working maybe 10, 15 years ahead, it's sometimes difficult to have that link. And I think the simulation and looking at new techniques. So one of the things we need to learn always is what is really out there and how we can implement in especially, so I'm talking in general in manufacturing, so not in robotics in particular. But again, I want to reiterate the idea that we're still dealing at the end with, we need somehow an end product, right? And we need to, and sometimes we need to visualize it, not only for ourselves, but also for our collaborator and so on. So it's, I think there is a balance, and it depends really on which like kind of technology we're looking at and so on. It's like if we're looking at, for example, so similar, if I give an analogy in manufacturing, so we have a lab scale where we do some of the research, including the modeling and so on. But then there is an intermediate scale, we call it pilot scale, by which, again, we can somehow scale up, right? So even cannot be, so we currently can working with some UAMs and so on, we're trying to build it, but cannot build it. It's the whole thing, so maybe to scale, and then finally it goes and we can scale it all the way up. So there is a balance, and it depends really on where is the application is. So, and the requirement, as I mentioned, the problem statement by which we're looking at.
Okay, interesting. Yeah, absolutely. Okay, so speaking of end products, I'm going to talk to Sandra now. So one of the things I think NVIDIA, and please don't let me put words in your mouth, but NVIDIA is pushing towards is really the market for learning-based systems, as opposed to, so the most important thing now is fast GPU cycles for learning algorithms, as opposed to really pushing like being able to do classical planning on a CPU, for example. Do you think that's the approach NVIDIA will continue with, or it's just for maybe the whole portfolio of products expands to try and cover all the bases?
So I think that's a question for Jensen. our CEO.
Right.
But
Fair.
but in general, if we look at what we have today, I mean, we do have, as I showed in the talk, there is a full stack acceleration from the hardware all the way up to the application layer, and everything in between is accelerated to run on GPU. But we do have the CPU cores as well on the GPU boards themselves, and we do have some capabilities, algorithmic capabilities that are optimized to also leverage that. And then with the acquisition of Mellanox, we recently added a third processor, which is the DPU, which is for data processing. And so potentially we're looking at right now getting workloads running efficiently on GPU, CPU, and GPU. And you can, yes, you can say that maybe a majority of this is AI workloads, but we do have some HPC, high performance computing SDK actually as well, and some other high performance computing applications that are not necessarily learning based, that we that can leverage essentially the parallel compute that CUDA provides. So anything that, if you can boil down, I guess, your problem fundamentally to fast matrix multiplication, like your problem, if it requires that, then you can definitely leverage a GPU and CUDA libraries for that, and it doesn't need to be AI. So that would be my 2 cents there.
Okay, excellent. So good. So I mean, it sounds like there's a wide, obviously, and we have some experience with many of the NVIDIA products, but didn't realize that the portfolio was still growing. And so it sounds like it's not all eggs in the GPU basket end to end.
No, I think so. I think AI kind of boomed in the last 10 years for NVIDIA, right, since ImageNet. But before that, I mean, we operated also in gaming, right? And then there was, again, these traditional HPC workloads that we accelerated back in the days. I mean, I can't really name them. I'm not an expert in that domain, but you know, AI has only been maybe the focus over the last 10 years. And then before that, CUDA was accelerating a lot of different areas.
Right. Very true. Okay. Very good point, actually. Absolutely. Of course. So maybe I'll ask Goldie next, and then I'll go to Pieter, and then Steve. I'm going to give Steve the last word on this as a contrary opinion, if he has one. So go ahead, Goldie. What do you think? End to end, or end to end with maybe some inductive bias, or do you bake in some of the classical stuff for interpretability, even maybe?
I was thinking when you asked that question, what happens when there's people actually in the loop as well? And what does end-to-end actually mean in those scenarios? And
yeah, it's also a good question.
Yeah, so that changes, like, I think, our whole perspective when I say that. So it doesn't mean the same end-to-end that we're used to, right? When we're dealing with a robotic system, interacting with the environment. So then I thought to myself, like, yeah, I don't even know what end-to-end in that application would mean. So that would be really interesting to see, like, answering your question with the perspective of, you know, the environment itself, and then with people embedded. I mean, we know there's human in the loop reinforcement learning. I mean, there are already strategies developed around that, but what happens when the people are very dynamic or very unpredictable? Can we actually have an end-to-end model in that scenario? And I mean, I don't have an answer right now because I literally just thought of it as you're asking, but I think we need to explore all those scenarios and situations that would come up to actually say if we could go one way or another, right? So I'll leave it at,
yeah, okay. No, very interesting.
Yeah.
And what's the reward signal for the human in the end-to-end? Like, cookies is what I would just feed me.
I think
cookies.
money. It's always money.
Point. Or money. Yeah, money. Give me money or cookies. Either or. Yeah. So very good point. Very good point. I mean, in the context of human-robot interaction and having a human in the loop, it's not quite the same as end-to-end learning in the traditional hardware-only robotic context. So I'll ask Pieter now, because I'm sure he would. This may be, of course, a great topic for him to address. And we'll maybe just limit it for now to the robot-only system. But if you have thoughts on keeping humans in the loop as well, that'd be great too.
Yeah, maybe I'll take it back to the more narrow version of the question, and because we had a lot of coverage on the broader version, and I think the question, like, okay, on a covariant robot, you know, whether or not to use some traditional robotic control algorithms and planning and so forth, I think it often comes down to understanding what are the assumptions that you're making when using those algorithms. And so let's say a robot just has to move in free space, open space from point A to point B, then probably a traditional algorithm will do quite well in finding an optimal path from A to B, and that's nice. And then there's no reason to abandon it. I mean, it's possible it's slow and that maybe a learning approach can generate the same path faster because there might be patterns to what are the most common paths you need to generate, and then a learning system could, essentially speed up that process, and that could be one reason. But actually more, and that can be quite important because you want to move very fast in these industrial environments. The number of operations per hour or per minute, whatever you want to count it, it's very important. But I think often the more subtle thing is that some assumptions are made that are hard to undo. So now let's say the robot is doing pick and place of some polybags for mail sortation. And you have one of these floppy bags and the robot just puts suction cups on it and it picked it up and now has to move with the fastest path from where it is now to putting it wherever it needs to be placed. Well, a traditional approach for just robot motion planning can find the fastest path for the robot, but actually it might lose the object because there might be too much force generated by the object swinging around. And so now the question becomes, well, what do you do? How do you find the fastest path while you're holding objects that will swing around? And now we could say, well, we could use traditional methods and you could try to perfectly model how does the suction cup work? What's the friction involved? Well, what is exactly the mass of the thing you're holding? Because otherwise you can't perfectly model. And you'll quickly run into a lot of modeling questions. First of all, modeling the physics precise, and second of all, what you're faced with in the world, you don't have perfect access to all the underlying variables. And so at that point, it becomes less clear. Is this like great existing path planner really going to give you the right path? Or if you follow a learning approach, you might be able to essentially learn that, oh, when you see this kind of situation, you do a pickup, maybe learn something simple, like maybe my max speed should be capped because this is a more difficult object to maintain suction seal on. Or it could be more advanced. It could be this would be the optimal path generated for this kind of object. And so I think you quickly start seeing that things are more complex than the kind of nicely canned algorithms typically provide for. And then the natural thing for us typically is to say, well, if we just collect enough data, we can get it done. And then you might say, well, are you throwing out all these existing approaches that do so well in these simpler cases? You don't have to throw it out, right? You can still, when you recognize you're in a simple case, you can just call upon it. Or you could say, hey, the simple cases are just one of many cases, and you can use the well-understood cases as a training data generator. You could say, okay, I know for an empty arm moving, this is the optimal path, and there's your training data, and you can generate it very fast, a lot of data. And so that, to us, has always felt less limiting in terms of if once you start hard coding something, often you hit limits and you need to find a way to work around it. Once you commit to being data-driven, but use anything hard-coded and perfectly understood as a data generator, you're not as easily hitting against limits of performance in our experience. And so generally our philosophy is to go that path, though, I mean, there could definitely be scenarios where, an existing approach, non-data driven, could cover it all because, it's just that specific scenario, but it's quickly more rare than you expect that you are in a clean-cut scenario.
Yeah, very interesting. Okay, so that's very interesting. I mean, also, I think as you mentioned, once you commit to becoming data-driven, since you have the data, you're storing all the data. Presumably, why not get the maximum return out of that data as opposed to hard coding solutions for individual cases, right? Yeah, absolutely. Okay, so I'm coming to Steve then, in hopes of a controversial opinion.
I'll see what I can do. I think people have become extremely reasonable and said a lot of really interesting and valuable things so far. So it might get harder. I was going to say, I think what's interesting about the end-to-end versus sort of sequence of modules is that at some point you do still want to understand how to decompose the complex system that you're developing, because you may want to fix a problem in some subset of it. And so it's certainly fascinating to think that we could cover with data every possible packet that you would ever want to pick up, or in my domain, every possible driving scenario that you would want to be able to navigate, or that you can somehow decompose all of those into reasonably well represented things within large scale data sets. But somehow I think that problem, that assumption kind of breaks down too. So I think the advantage of a truly end-to-end system would be that you'd only have to train once on an infinite amount of data and you would just be fine, right? But you lose the ability to interpret what's going on, and you lose the ability to improve things incrementally when you uncover problems that are truly problematic for your 99.99%, right? Instead of your 99.98% improvement. And so I think there's real value to both. And I think, to quote somebody else, it's Raquel Urtasun always comes with this opinion that you can use end-to-end, but do it with intermediate tasks and learn for multiple objectives, so that there's still an interpretable representation at many different stages throughout your robotics system. I think that's a really neat approach, and I sort of like that one, that there's a lot of value to fully differentiable models that you can train right all the way through control and planning and perception and prediction, right? But that you, if you bypass any kind of intermediate representations that are human interpretable, you really run into a complex system that's hard to advance. That would be my take.
Okay, that's excellent. Yes, I think that I'm taking notes on this as well for later, and I would agree. I'm just waiting for the networks to get smart enough to tell me what they're thinking. So once we have enough layers, the network will simply tell me what's involved inside it. Okay, so for the last 8, we have about 7 minutes left. So I'm going to try actually to take just a couple of more questions from the audience. And so I see that, please forgive me if I mispronounce your name, Hrishikesh. I don't know if you can turn on your video if you're still there. Maybe, I don't know if he's still there. You've popped in the chat box at the bottom. There he is. Yeah. Go ahead if you have a question.
Good. Can you hear me?
We can. Yep. Sounds great.
Okay, great. Thanks. So my question is, what is the role of custom AI chips, if any, for the actual robotics hardware, so that the algorithms can be executed faster, or do you still see that they should be built with generic components?
Ooh, great question. Great question. So maybe Sandra would like to field that one first, and then we can see what the panel would actually like in terms of chips. If Sandra wants to take it, no pressure.
Well, I can comment on what we see in the industry today, right? So essentially talking about what's on the mobile robots, we see a combination of robots using, one category using a mix of Intel or Qualcomm processors along with the NVIDIA GPU to do the AI. And then a few are actually trying to put the entire software stack on the NVIDIA GPU or Jetson. And as far as the role for custom chips, I think I would prefer to defer that to somebody else, maybe in academia, to answer.
Sure. Animesh, do you want to pick up? I mean, also being involved on the NVIDIA side, what do you think? Custom?
I don't have active experience on this, but I believe the answer would be yes, for simple reason that the way to think about this can be what is particular custom chip. Basically, if an operation just needs to be done so many times and you're absolutely certain will happen, then why do you need to do slow thinking on it kind of argument? So an example could be, let's say you have built a robot that is essentially a simple navigation robot, and you're feeding in RGB, and then RGB, that model is predicting some sort of depth map, and then that predicted depth map is being used to do some sort of directional control. Would it not just be better to take all of the front end of the model and just bake it into the camera itself? So the camera is essentially outputting a tensor that you need to make decisions, because as long as you don't need to render it for a human sort of consumption, why bother? So then you can do it at speed, perhaps even faster. The other things we have seen, for example, I've worked somewhat in model compression, and one way to also think about custom chips is very simple. Would you rather run Python code or assembly code if speed was the concern. You compile code. Model compression is equal to program compilation. It's the same output input, but you are doing this much faster and dropping all of the sort of fat that you had because you were using, let's say, easy to program libraries and abstractions. You will drop FP32 and you'll go to FP16 whenever possible without dropping accuracy. You will save power, you will save memory. So a lot of this will be done. So it's like, think model compilation. So you want compilation in general. So it's the same argument.
Okay, so maybe there's a market for, not quite bespoke per task chips, but maybe within categories. Absolutely interesting. Hani, speaking, since chips, are difficult to manufacture, you have an experience with manufacturing. Do you think there's a market for? Is custom chips the way to go? Do we care? We do care about carbon footprint, absolutely.
Yeah. So the issue always from a manufacturing point of view is we're moving more now to high mix, low volume. So before it was really high volume, no mix. So there is no change in when we talk about chips and so on. So then it was really, so it was easy, like really to manufacture on the same manufacturing line and so on. So more and more now, and especially with a number of manufacturers, it's more nowadays on really high mix and low volume, which really complicate the issue, which comes back to the idea of custom-based system, but it requires also custom-based manufacturing, or what we call flexible manufacturing. So I can change my manufacturing line always in order to accommodate for any new design and so on. It's not a very easy thing to do, but that's the future now. Like it's really more and more towards that area. There is nothing currently we can do in really high volume. It's very targeted, and hence it comes back to on the manufacturing line. We need to have it like as a flexible, or what we call a clean manufacturing system.
Okay, very interesting. Okay, so maybe we'll finish with this one, maybe, since we have just 1 minute left. We can run just a couple minutes after 5. So maybe I'll just in random order maybe ask Pieter, and then Goldie, and we'll do Pieter, Steve, and then Goldie, because I put Steve on the spot at the end last time, so put Goldie on the spot. So Pieter, do you have if you could get your hands on some custom silicon, that would how specific would it need to be, and would it be worthwhile, or does it really matter that much?
Well, I mean, it's clear that the custom chips could speed things up, but I think the real question is knowing what you want to speed up, as Animesh alluded to, and I think that's where it gets complicated, right? It's the beauty of the current chips is that you can run a wide range of experiments, and as something converges, something custom for whatever you converge onto makes a lot of sense. And I think we'll see that happen. I mean, there will be more conversions, and there will be more customized chips that really do specific things faster. But I don't have a specific, like if I could only ask for one specific custom chip, and not sure what to ask for. On the other hand, if for every experiment anybody at Covariant runs or any one of my students runs, if on the fly a custom chip could be generated that runs that experiment 1,000 times faster, sure. That would be great. And I imagine a custom chip might exist that could run each single specific experiment a lot faster, maybe not 1,000 times faster, but 10 to 100 times faster. But I don't think, generating those chips on the fly might be a lot to ask for. It might take longer than the experiment itself.
Yeah, that's right. It might be more cycles used to actually build the chip to do the thing than actually just to do the thing with the existing hardware. For sure. Yeah. Okay. Very interesting. Okay. For sure. Good points. Steve.
I couldn't agree more. Yeah, the idea of custom chips is wonderful, but on the 1 to 2 off in the research side, I don't think it's hugely important. It's really interesting to see where the first custom chips start becoming important for robotics applications. I think that's kind of cool, right? So what are the game changers where this is a task that we actually need reliably on many robots, and therefore it's worth doing this kind of investment. I saw, Serta Cameron came by once and showed off his monocular VIO custom chip that he had built, right? And this was pretty impressive. And you could imagine sticking that on every drone and every little ground robot and just having a reliable inertial odometry solution, right? Or visual inertial odometry solution. That kind of thing makes a lot of sense to me. And so what's the next one? I'm not sure. Maybe it's a people detector or a face detector, or, right? Like all these things for robotics specifically.
Yeah, indeed, absolutely, and that's a very good point. I think I'll mention also real-time robotics, which I don't know if they're using custom silicon as well. I assume they are, but that's for, or some type of, it's for motion planning. So and maybe it's not. Maybe I'm not sure if I haven't actually looked into their hardware. It's just I know it's boards for motion planning, but I don't know if the silicon on the boards is actually custom at all. Okay, and we'll finish up maybe this with Goldie, and then we'll just check the time. We'll probably wrap up there. But Goldie, if you have any thoughts on. Would you like custom silicon for your lab? Probably the answer is yes.
Yeah, the answer is yes, but I guess
say no to it, yeah.
What cost, I guess, is the ultimate, right? How much is it going to cost me, and how much is it going to save me that I'm willing to invest in it? Especially if you're doing exploratory research, as Pieter and Steve were saying. I mean, you don't necessarily know what you're trying to optimize or speed up initially at the beginning, so you don't necessarily want customized chips then. But if you are developing a product and you have, specifications that you're looking towards achieving, then it's a different story, right? But I think in general for research, we do look at more general chips that we can use because we don't know exactly what we're doing at the beginning, right? So until we get to that point, until we know what we need, then the question comes back down to, okay, what performance metrics will it improve? And then of course, how much is this all going to cost me? And if I'm trying to sell the product and I have a startup, how much is it going to cost the consumer, right? So it's all those, I think, different aspects that we have to consider in the end. But of course, I mean, ideally, yeah, I would love them. And if I could have them for everything from perception to control to interaction, whatever I could use the chips for, it would be great. But again, at this point, I don't know exactly what I want to optimize, right?
Okay, so okay. I think that is a great way to end it because Goldie just, the central rule of engineering that we always, or one of them one of the main ones you always tell students, right, is don't optimize until you know, and then probably even then don't optimize, but definitely don't optimize before you know. So in this case, in general, right, we don't even know what we need. Yeah. Let's wait maybe enough time until then we can build the custom silicon that we need. Okay, so that was a great question from the audience. Thank you very much. I'm just going to clear that, and then I'm going to. Sorry to those of you who didn't have a chance to say questions from. I do appreciate everyone who posted in the chat, and thanks so much to the panelists. Great panel discussion. Thank you for taking the time. Thank you, Pieter, for sticking around. Goldie, Hani, Steve, Sandra, thank you all for spending an extra hour for the panel. And I will now hand it over to Animesh to do the closing remarks. Thank you.
Wonderful. I think we've all had a wonderful day. It is definitely has been a learning experience for me. A lot of new perspectives, a lot of new ideas, a lot of new research exposure. So one of the first things we would like to do is to go over the poster awards. The poster awards are presented by Ocado, and we have James here today with us to walk us through the awards. Hi, James.
Sound check.
Yes, we can definitely hear you. So James and Murtaza presided as our award chairs. They went over a number of presentations and also looked at the material. And I'll give James, if you want to say more, or we can directly go to the announcements. Up to you.
I did want to say a few things.
Yes.
I wanted to say some appreciations. It's the end of the day. I've been through, and I got to participate in most of the workshop here today. And I first of all wanted to actually thank you, Animesh, and also Jonathan for hosting the workshop. I've got some notes here, so I'm looking to the side. I'm going to say you've recruited arguably the best researchers in the world to speak on these areas and provide perspectives on what we are up against in research and in product design. And thank you for inviting Ocado to serve as a sponsor. I'm honored. So I think you've offered everyone a great perspective on the state of the art, and thank you for that. I am proud to be here on behalf of Ocado Technology. I've grown a team in an office here in Toronto as Kindred, and now as part of Ocado. And I just wanted everyone to know and to hear that Ocado is firmly committed to supporting the Toronto area as an emerging global leader in research in this area. So that's the engineering, the product development, and how to make smarter robots for handling things. Our Toronto-based team has doubled since our acquisition about a year ago, and is likely on track, I would say, to do so again next year. So please, everyone on this call, do consider us when you're thinking about your future careers and so on. In approaching the awards for this workshop, I hope you understand that Mortiza and I had a lot of flexibility in how we would define the awards criteria. But if proceeding under uncertainty is something that startup life teaches, I will say the strategy for dealing with that is to appeal to values. So I want to talk a bit about values. So Kindred and Ocado are guided by values in our culture that we create internally, including inclusivity, open-mindedness, collaboration, and asking hard questions and listening. And these are great values for building teams and solving hard problems and creating a culture that I think makes people like working for Kindred and Ocado. And this set of values is admittedly not great for judging things. So I had to appeal to other values that we also hold related to, for example, actually, no, first, before I move on to that, I wanted to say Mortiza and I we did go through all the presentations, and every one of them prompted some interesting discussion in our review. And so I definitely want to thank everybody for putting those together. And I think every single one had potential applicability to engineering challenges that we have seen and faced in one way or another in even just our two views within our two companies that we've been part of for a few years. But we also see other values like craftsmanship, perseverance, courage to innovate, delivering beyond expectations, and quantifying. And quantifying means trying things, seeing what happens, learning from that, kind of going for it. People learn that way, RL learns that way, and judgment goes into what you try. And so I want to offer awards on behalf of Ocado Technology to authors here that have demonstrated these values in taking on hard problems and just going for it and making progress that I look forward to reading about and acting on. So with that as intro, number 3, I'm not sure how this is choreographed. Is there like slides and stuff?
It is number 3.
All right. It's like the Oscars.
Number 3.
Number 3.
Drum roll. Da-da.
We have categorical depth distribution networks for monocular 3D object detection. Thank you, Cody, Ali, Julia, and Stephen. We had an ongoing debate in our group, which I think will continue for some time, as to whether depth estimations should be on the bottom or the top of a neural network. And I expect this to present another entry in that debate, as it will continue for years to come. Next.
Now on to number 2. We have
GIFT, generalizable interaction-aware functional tooling affordances without labels, by Dylan, Turpin, Deepan, Wang, Davos, Dalkus, Tom Dickinson, and Animesh Garg. As someone mentioned, there was a breakthrough in deep learning for kind of bandit-style estimation of affordances in pictures a few years ago. And, that kind of like got the research off the ground, because we were actually getting affordances for getting things off of a table. But, as a product designer and someone thinking about all the interesting manipulations we want to do with robots, it's hard to enumerate them with affordances. And so, lifting away from that and then kind of extending into the more complicated world of all the different things you can do with a hammer, for example, in the poster, is something that we continue to think about a lot. And so I appreciate that these authors went after that problem. And
thank you. And now on to
final
gold medals.
Gold medal is for a robot architecture using context laying to find product in unknown crowded retail environments. From Daniel Borkowski, Christopher Thompson, Michael Kamhan, and Goldie Nejat. This work, I thought was, I mean, Ocado does handle a lot of groceries, so on some level, yes, it's in a grocery store. But I also want to recognize, and I'm going to say also, I'm not sure how big of an effort this is for this group versus the broader research from that group, but to take all that research all the way through into the physical world and to do all the AI and the system integration. And in the photo on the poster, I think what I'm looking at is a robot that's running in a real store. So that's not even just physical world. That's like in a retail environment where you have to collaborate and ask the store manager if that's okay and all that. So congratulations, and I know that I have some idea of how hard that is, and I also have some idea of how rewarding it can be. So please keep at it and don't give up, even though it's hard to make robots work in the real world.
Thank you. Thanks a lot, James. First of all, thank you for creating so much thought, putting in so much thought into each of these rewards, and a lot of work went in to go through all of the material as well. So thank you to you.
I know this. I kind of over time, but I did want to say one more thing, which is that I hope the recipients of these awards will appreciate our congratulations, in addition to award money, and also will think about working for Ocado. I wanted to make sure that everyone knows that Ocado powers Voila by Sobeys here in Toronto. Great product, handled by our robots. You can check it out. And I also wanted to call out that the Kindred Sort fleet already handles, by my reckoning, 5 billion time steps of robot experience per week. So if anybody wants to do reinforcement learning in the physical world with a production robot fleet, we are in that business. And so you do have to work with our engineering team and our customers to actually do that. So you can't do anything you want. But as we look at growing our products, we have 2 more products in the wings for next year. Do please think about research collaborations or open positions that we might have. Please keep us in mind, and feel free to email me personally if you'd like to know more about what we're up to at Ocado.
Thank you. And I do personally say, yes, do consider potentially working at Ocado. It's fun. It's a lot of real robots. Okay. I think moving on, I would like to thank all of the speakers today. It was very instructive to hear from different corners of the industry with different kinds of experience, whether it was Matt from Berkshire Grey, Pieter from Covariant, Ocado, Alex, James, Sandra from NVIDIA. We also had folks from Epson in the audience as well. I think it is definitely a pleasure, and we are fortunate at U of T in Robotics Institute to have all of you guys around for easy access to tap you on the shoulder for asking these hard questions. So with that, I would like to wrap up with some take-homes. I think a lot of questions got asked. What sort of opportunities and challenges exist? I would say one thing that definitely we are taking home is logistics and order fulfillment is definitely a very big opportunity. It's far from solved, even from a research perspective. It's semi-structured, and even simple problems that are on the surface boring are actually fairly rich to begin with. And problems in manufacturing and retail are not all that different if you drill it down to the exact operations. But importantly, for academics, we need to focus a bit more on evaluating systems that are increasingly less structured, potential solutions or problems that we need to work on are dexterous hands, sensing skin and force control. Simulation is something that was a topic reasonably charged throughout the day. One thing is simulation is useful, but not sufficient by itself. We definitely need to design experiments that can excite potential practitioners, that can potentially spark new collaborations. And finally, this is a personal pet peeve. I believe robotic systems research should have the same status as we give to algorithms research. It's not just blue sky research. Building incremental stuff matters. At the same time, during collaborative partnerships, during the panel 2, Pieter pointed out that the pieces of the puzzle include deep supervised learning, simulation, unsupervised learning, and RL. Almost everybody agreed the deployment in real world is necessary to discover real problems, including the long tail. There was a long debate which required end-to-end versus classical techniques, but it seemed like we need to essentially figure out how to leverage these ideas because we need to or we want to use new computing paradigms. As Peter pointed out, that data-driven methods appear to generalize better and are easier to train in principle. But there are questions about modular explainability or interpretability. How do you do model audits? And I believe that they are questions that all of you who are actively doing research, whether inside or outside academia, could potentially look at. And the last thing that we discussed was custom AI chips. And we had a non-controversial answer, which was they can speed up compute, but it's not clear what should we be speeding up. I think before we do end up, I do want to offer special note of thanks to all of my co-organizers, Joan, Hallie, Aiden, Philippe, and June. I think I did less than 10% of the work. All of the behind-the-scenes work was by my fabulous co-organizers, and this would be so hard and so misorganized if it were not for them. So thank you guys, and I look forward to working with you all. With that, I think we come to an end of an exciting day of talks. Thank you all. It has been a privilege to have your time through the day. Many of you stuck with us. We are going to have a social for the next hour. We are all going to hang around, hopefully answer questions, just chat about whatever you want. So feel free to hang around. If you have other commitments, feel free to drop off as well. Thank you once again, and hope we'll see you again at future programming from U of TRI. Bye-bye.